So very good morning to you all, those who have already joined.
গুড মর্নিং স্যার।
হ্যাঁ, গুড মর্নিং।
আমার ভিডিওটা এখানে এই ঘরের থেকে ভিডিওটা কাজ করছে না, এটা পড়া মুশকিল।
ভেরি সিম্পল। এটা হয় জেনারেলি।
এটা কিসের জন্য কে জানে,
হয়তো কম আছে বোধহয়, ব্যান্ডউইথ কম আছে।
হ্যাঁ, এটাই হতে পারে।
বাকি সবাইকে বলো তো জয়েন করার জন্য। অনেক Good morning, sir. Professor Wong.
Hi.
Yeah, hello. Hi.
Hi.
Yeah, good morning, Professor Shum. How are you?
Yeah, fine.
Nice
Yeah,
to see you.
yeah. It is night, I think, in your place right now.
Yes,
Maybe.
yes,
Yeah,
yes.
nice
N-
to see you
So
here.
my time is 9:25.
Good
Yeah,
morning, sir. Good morning.
yeah. Professor Marichal. Let me ask my dean to join.
हाँ
हाँ हेलो सर ज्वाइन कर लिए हैं क्या ठीक है ठीक है ठीक है ठीक गुड मॉर्निंग प्रोफेसर कैसे लो
Good morning.
या मे बी इट इज इवनिंग देयर
Yeah, it is night.
So how the things are going on, sir?
Very well.
Okay.
Thank you.
Okay. I know you are too busy and you have joined. That's fine. Yeah.
Hello, Megha. How are you?
I'm fine, sir. How are you?
Good. Who is it with you?
She is my friend Anshika. Hello, sir. My name is Anshika. How are you, sir?
Good. How are you?
I'm also good, sir. Welcome, sir.
So what are you doing? You're doing PhD?
Yes, sir. I'm her classmate.
Oh, good, good.
Thank you, sir.
Yes.
गुड मॉर्निंग सर प्रोफेसर द्विवेदी जी आपका माइक म्यूट है सर अनम्यूट
Okay. Good morning to all of you. Good morning, sir.
या
Good morning.
Good morning, Din sir. Good morning.
Yeah, good morning.
तो बनारस में बहुत ठंडा पड़ गया
Right.
दो मिनट बचा है
Professor Chaudhary, I think you have visited here in India last time or sometime back.
Who?
Varanasi.
Whom you are talking to?
Professor Roy Chaudhary.
Oh no, I did not visit Varanasi. I just came one time in
Okay,
TIFR.
okay.
TIFR.
Okay,
Not
okay.
Varanasi.
Mhm.
So, we'll start our program.
Yes, it is going to be 9. We can start.
So, very good morning to one and all present here. Obviously, according to Indian time zone. This is Megha Pandey, And this is Anshika. We are research scholars in the Department of Mathematical Sciences, IIT BHU, and today we are going to be a host of this event. So I feel privileged to welcome you all on behalf of our department to the inaugural ceremony of International Conference on Nonlinear Applied Analysis and Optimization, that is ICNAAO 2021. To start our program, we first pay a sincere tribute to a great visionary, Pandit Madan Mohan Malviya ji, who is the founder of this organization. And since it has been always a custom to play Kulgeet before any event, so now I'm going to play our institutional Kulgeet.
अतीव सुंदर ये सर्ववेद की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्ववेद की राजधानी राजधानी
ये तीन लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि, बसी है गंगा के रम्य तट पर। ये
राजधानी मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी नहीं नहीं है ये ईट पत्थर है विश्वकर्मा का कार्य सुंदर रचे है विद्या के भव्य मंदिर ये सर्वश्रेष्ठी की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी
यहाँ की है ये पवित्र शिक्षा कि सत्य पहले फिर आत्मरक्षा। बिके हरिश्चंद्र थे यहीं पर
ये सत्य शिक्षा की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी ये वेद ईश्वर की सत्यवाणी बने जिन्हें पढ़ के ब्रह्म ज्ञानी निराश जीने रचे यहीं पर ये ब्रह्म विद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी
So, this was our institutional Kulgeet. I hope you all have enjoyed it. Now, I extend my warm welcome to our Honorable Dean, Professor S.B. Dwivedi, our guest of honor, Professor M.A. Khamsi, Professor Oscar Caslow, Professor N.C. Wong. I would also like to welcome our organizers of this conference, all dignitaries, all faculty members, and all the participants of the conference. Today, we are honored to have such esteem very close to our heart, and his birthday is really a great reason for the celebration. The one thing in his personality which inspires me the most is his approach toward the life. Like he has always seen the brighter side of everything, and how beautifully he connects everything with mathematics. Like for example, everyone present here knows the story of the taxi cab number. That how we came to know about the cab number. It was his positive vision which introduced us with this interesting number called taxi cab number. So and also we have a special session on him tomorrow on his birth anniversary. So moving forward, a famous quote by Dean William is, "The aim of education is the knowledge not of facts but of values." And also Newton once said that education is not learning of many facts; it is rather the training of mind to think. So the conferences like this are the occasions where we get the opportunities to test our knowledge of understanding. So through this conference, we look forward to get the exposure about what the best of brains think about this very dynamic issues of the conference ICNAAO. Now, I would like to request to the organizer of the conference, Professor Tanmay Som, to come forward and to have some briefing about the conference. Please welcome, sir. Oh, sir, your mic is mute actually.
First, very good morning, evening to all of you who are present here. A very warm and hearty welcome to all the dignitaries and participants joining this inaugural program. In fact, 22nd December being the birthday of Srinivas Sir Ramanujam, every year we celebrate this as an occasion, National Mathematics Day. And taking this chance, we are organizing this international conference on nonlinear applied analysis and optimization with soft computing as one of the focus areas. And I am very happy that today with us we have Professor S.B. Dwivedi, our Dean, Academic Affairs, Professor Oscar Caslow from Mexico, Professor M.A. Khamsi from USA, Professor N.C. Wong from Taiwan, Professor Pierre Marchal from France, and many others of our colleagues from different institutions. We are going to cover in these many areas, in the following areas. Of course, these are the challenging areas nowadays. All the areas have developed like anything. So, major challenges are there in fixed point theory, nonlinear analysis, fractals, dynamical systems, optimization theory, differential and integral equations, soft computing, etc. So these 3 days program, the various talks, about 25 talks are there, and around 75 participants are going to present their papers. So this is a very good gathering, and they are going to exchange their ideas. And I hope that this will be, in fact, we have a gathering, a galaxy of mathematicians all over the world. And they've solved equations on a wide range of topics, kept as a treasure of hidden knowledge in his notebook. His notebook is still, there are a lot of hidden things, and people are still devoting their time to get something new from his hidden treasure. So with these words, I welcome you all again to this 3 days international conference on nonlinear applied analysis and optimization. Thank you very much.
Thank you so much, sir, for clubbing us all here for this innovative international conference. Now, I would like to request Professor M.A. Khamsi to say a few words which will apprise our knowledge.
Hi, everyone. Can you hear me?
Yes.
Yes, sir.
I was thinking yesterday when I got an email from Tanmoy Song that he wants me to say something, and I did not know, to be honest with you. It never happened to me before. I did not know what to say, but then something really hit me, which is how many times I have been invited to speak in India. From Professor Swaminathan in late 80s to Qamar Ansari's, Haruddin and Danaji Gopal, etc., etc. Many times I have been invited, and many times I couldn't go for different reasons. And but it's really amazing how this pandemic, many of us are looking at it as being extremely devastating. I lost my mother to this pandemic, and it's really curtailed our way of life. But at the same time, something positive came out from this pandemic, which is this month, in the last 3 weeks, I witnessed a conference in Romania, and my friend Adrian is here, a conference in Saudi Arabia, and conference in Morocco that was a hybrid between online and face-to-face. And now this conference, so it shows you the ability that we can get humans something positive from something that sounded negative. And this is the way we move forward. So this education, remote education, that I have been pushing worldwide for the last 10, 15 years, I saw it happening overnight. But Google Meet, how many of you knew Google Meet before the pandemic, or Zoom before the pandemic, etc., etc.? So the technology is becoming more and more useful to us to exchange ideas. Of course, some of us may argue, I prefer to have a book than to have a digital copy. Yes, I do agree with that. But some of us cannot afford to buy a book. And the technology somehow makes it at certain democratic level for all to share ideas, etc. So I hope that this conference will be a source for enlightenment and exchanging ideas. Thank you very much for organizing it.
Thank you so much, Professor, for your inspiring and motivating words, and I'm sorry for your loss. Now, I would like to request Professor Oscar Casilio to unmute his mic and say a few words for this conference.
Thank you very much. I'm very happy and glad to be in this international conference on nonlinear applied analysis and optimization. I was 3 years ago in Varanasi, so I was there one time, and a very beautiful place. I remember with the movie at the beginning, the places I visited, so I did like it very much. I miss being in person in many of these conferences, but as the previous speaker was mentioning, I have been able also to deliver many more keynotes or invited talks and so on, and by this way, online way, to many places that maybe I could not be able to go. So it's also an opportunity. And I think this is a very interesting program. I have seen the topics, and I work in soft computing, mainly fuzzy logic, but as you may have been seeing in the last years, most mathematic topics have been extended to fuzzy And so there are fuzzy differential equations, there are fuzzy fractals, there are fuzzy integrals, fuzzy mathematical models. Also, fixed point theory has been extended to fuzzy domain. So I think this is very important, and hopefully here we will discuss this kind of things also. And my talk will be on that area. I would like to thank this invitation by Professor Som and the Department of Mathematics and Applied Sciences and in the Indian Institute of Technology for inviting me. And hopefully this will be very enriching conference. Thank you very much for the invitation.
Thank you so much, sir, for such informative talk. Now, I would like to request Professor N.C. Wong to add some inspiring words to our life. Please, sir.
Hello. So do you hear me?
Yes, sir. Yes, sir.
Yeah, thank you. Yeah, thank you very much for the invitation. I would like to especially thank Professor Shum for this wonderful conference. I was also invited to India several times, maybe 10 times in past years, but I never been in India. I look at the video too, and I like the city. It looks very beautiful, and the culture is very interesting. And I hope all of us can have a second chance to visit the city in person, maybe next year. Yeah, and I also very impressed about the program of this conference. It's about 100 speakers giving talk in a very different subject. In fact, I have some old friends here, and I want to make many new friends too. The organizing is very difficult. I understand that because the pandemic is popular here and also in Taiwan too. So we all as have a very difficult life. But fortunately, Professor Shum and your colleagues work very hard to make this event happening. And I am going to enjoy it. And I'm sure I will enjoy it very much. And I would like to say thank in advance to all the organizers, all the colleagues here. And I am looking forward to a very wonderful conference. Thank you.
Thank you, Professor. We are grateful to you for your time and efforts you took to share your knowledge with us. Now, I would like to request our Dean, Professor S.B. Dwivedi, to come forward and share his thought with us.
Am I audible?
Yes, sir.
Yes,
Yeah.
sir.
Okay. A very good morning to all of you. I am honored to be the guest in the inaugural function of this international conference. I am thankful to the organizing committee of the IIT BHU Mathematics Department, IIT BHU. On behalf of the Dean, Academic Affairs, Indian Institute of Technology, BHU, I welcome the delegates all over the country, particularly Professor Oscar Casillo, Professor Nagai Ching Wong, Professor Khamsi, and many others distinguished mathematicians who came to participate in this conference from all over the country, and particularly the young researcher who came to participate in the conference to share their research and exchange their idea and to get benefit from this international talks and many new things the great mathematicians will discuss in this conference. That being the academics head of this institute, I that take this opportunity to thanks the organizer to organize the conference through which these mathematical problems, particularly this in all these engineering fields, we are using the optimizational technique and nonlinear techniques for solving the engineering problems, and that all these engineering problems, without the help of you great mathematician, we cannot solve that problem. So all these type of discussions last 2 days, what will be shared by the great researchers will be helpful for the engineering disciplines. and that we are welcome such type of move and the organization conference and discussion. And this 2 days discussion, that 2 days conference, I am pretty sure, and that's I expect that you will get many new things, many this outcome will share through your experience that will be helpful for the not only for mathematicians, for our young technocrats, those who are also participating in this conference. And with these few words, because due to the shortage of the times that it is given to me only few minutes, let me close my speech with my blessing, and I wish that this conference will be highly successful. Thank you very much for giving the opportunity to me as a guest to speak in this inaugural function. Thank you.
Thank you so much, Professor. And on behalf of our whole team of ICNAAO, I'm very thankful to you for sparing some time to share your experience with us. Now, I would like to request Dr. Sheila for the vote of thanks.
Yeah, so good morning, everyone. So now we are at the end of the inaugural session, and it is a privilege for me to propose a vote of thanks on this occasion. On behalf of the Department of Mathematical Sciences, IIT BHU, first I would like to thank our honorable guest and Dean Professor S.B. Dwivedi, who gave his vital time to grace this inaugural session. Thank you very much, sir, for sharing your thoughts and encouraging words and for your blessings. Next, I would like to express my gratitude to Professor M.A. Khamsi, Professor O. Castillo, and Professor N.C. Wong for your presence and for your useful and knowledgeable comments. A special thanks to all plenary and invited speakers for accepting our invitation and agreeing to share their knowledge and research with us. My sincere thanks to our Head of Department and Conference Chair, Professor T. Som, for his motivating and dynamic leadership. Sir, you have really worked hard and have given a lot of your precious time for organizing this conference. I take this opportunity to thank the conveners of this conference, Dr. Abhas Shah and Dr. Devdas Ghosh. Sir, both of you have spent a lot of your valuable time to shape this conference so nicely. I also thank to all authors who have submitted their valuable research to this conference. Finally, I convey my sincere thanks to our whole organizing team, student team, and faculty colleagues for their help and cooperation. I once again thank everyone whose contribution have helped to organize this conference.
Thank you so much, Doctor. Thank you so much, ma'am. And
very good, Sheila madam. Very good.
Thank you so much, ma'am. So now our inaugural session is over, and we shall start our event from 9:30. Now, I would hand over the session to the organizer of this conference, Professor Tanmay Som, and I would request him to unmute his mic and announce the beginning of the program by greeting the session chair of our first talk. Welcome, sir. Welcome.
Hello. So these 3 days we have total 6 sessions. In the first session, that is the morning session, we are going to have plenary talks by Professor M.A. Khamsi, Professor N.C. Wong, Professor S. Chakraverty, Dr. D. Datta in the morning session. And in the evening session, we are going to have talk by Professor A. Petruzel of Romania, Professor R.I. Bott from Vienna, Professor P. Marechal from France, Professor S.M. Grad from France, and then Professor B.S. Chaudhary from IIST. Tomorrow, we will have two special sessions, one on soft computing area and another on number theory area. So tomorrow we will have plenary talks, invited talks, and paper presentation. So tomorrow's talks will start with the talk of Professor Oscar Casillo. Then Dr. S. Kerr, then Dr. J. Datta of IIT Kanpur, Professor J. Datta, then Professor S.J. John from NIT Calicut, then Professor A. Shankar Narayan, that is in the afternoon session tomorrow on number theory. Professor A. Shankar Narayan, Professor R. Munshi from A. Shankar Narayan from TIFR, ex-TIFR, now he is in University of Hyderabad. And then Professor R. Munshi from ISI Kolkata, then Dr. Saurabh Kumar Singh from IIT Kanpur, then Dr. M.M. Singh from Northeastern Hill University, Shillong, and the last talk that will be Professor M.K. Roy Chaudhary from USA. And then on the third day, we have similarly plenary talks first talk by Professor Akhtar A. Khan from Rochester, RIT, then Professor Q.H. Ansari and Professor, of course, parallel session, then Professor R.P. Pant of Aligarh Muslim University and Kumayu University. Then Professor D.K. Ganguly from Calcutta University. Then Professor Sannyasi Raju from IIT Madras. Then we have paper presentation, then afternoon session. So we have also paper presentation in the first session as well as in the evening sessions. Then afternoon talk will be by Professor M. Banerjee from IIT Kanpur, then Professor M. Masopost from Germany on fractals, and then Professor S. Mukhopadhyay from IIT BHU, and then Dr. R.K. Vats, and also Dr. D. Gopal, V. Shankar Raj, and D.K. Jana, all from our Indian different colleges, universities. So I welcome you all. Now I hand over the today's first morning talk to be delivered by Professor M.A. Khamsi. Professor N.C. Wong will chair this session. So I request Professor N.C. Wong to come forward and chair the first talk.
Okay, thank you, Professor Shum. Yeah, so I suppose we start the talk now?
Yeah.
Okay, the first speaker of the conference is Professor Khamsi, and he is a professor at the University of Texas at Paso, Texas, USA. And he did his PhD from the University of Paris 6 in 1986. His present research interests include fixed point theory, geometry of Banach spaces, and operator theory, and also discrete dynamical system, discrete mathematics, order sets, and trusses. He is also author and co-author of six published books, and he also published many research papers in the Descent Journal. He is also editor in the editorial box of 5 international journals, including Fixed Point Theory and the Journal of Mathematical Analysis. He have done a lot in education. He had guided more than 8 PhD students and postdoc fellows. So let's welcome Professor Khamsi for his first talk. Yeah, Professor Khamsi, can you show your talk file?
Say it again, Wong. I'm sorry.
Yeah. So can you share your screen so that we can look at your presentation? So you have prepared a PPT, right? So I hope every other guest mouse your mic for this talk. Okay.
So can you see?
Yeah. Yes. Good. So let me read the title for you. So today the first talk will be on recent geometrical properties of variable exponent spaces by Professor Khamsi. Okay, please, your time, you have 1 hour. Yeah, thank you.
Okay. I'm not able to see you guys, but that's fine. I mean, as long as you can see the screen and you can hear me as well. First, I want to apologize to some people, since this is the first time I'm giving a talk in India. And I'm glad that one of my favorite mathematicians of all time were celebrating his birthday in 2 days, or in 1 day, in fact. Again, as I said, I want to apologize to Qamar Ansari, as well as some people like Gopal and Adrian. Some of the ideas I'm sharing with you here, they already heard them. Because since this is the first time, I wanted to share some of the ideas that I'm working on. I'm really right now interested into this and try to understand what's going on. So the talk, the title is a little bit, though the title is about variable exponent spaces, but it's a reflection. It's more than just variable exponent spaces. I will be saying something. And again, many of the ideas are still at the embryonic level. In other words, we did not go deeper yet and understand what's going on, okay? So it has a historical flavor as well as a modern flavor, okay? So you will see. So first, I wanted to, because of for the sake of time, Gopal knows, Dharanji Gopal knows very well what I'm talking about. If I get into this subject, the one I'm talking about right now, this may need about 3 hours, and I have done that before in King Mongkut University in Bangkok, in Thailand. And so I always get scared when you have 15 minutes or something similar, where you don't give a result to the people, what's going on. In other words, you stay only in the introduction and you don't touch on what's the latest. So let me just start first of all to tell you that what got me motivated, me personally, what got me motivated. I had a student, a PhD student from Turkey, who came to spend a year with me in Texas. And by the way, for the sake of, as you have seen, I'm retiring from Texas and I'm moving to Khalifa University in Abu Dhabi. So that's why. So we are only about an hour and a half. I know that Castillo, El Paso is close to Juarez, and we have almost the same time, 1 hour difference compared to Tijuana. But where I am right now is only 1 hour and a half difference with India. So anyway, so this started when this student came to see me, and I was looking at a problem to give her, and they came by accident to meet this example. So here, the original example published in 1931 by Orlich did not have n+1. It had n. Okay, well, I mean, it's no big deal anyway. It's just re-indexing and you are done. So this example really got my attention. Okay, so the article was written in German, and I don't read German, or at least I'm not good understanding the finalities of the German language. So though it's very close to English, but still. So I looked at it, and I asked a friend of mine, Osvaldo Mendez, to help me out with this. And really, it got my attention. This example got my attention, okay? And what's amazing is that the original article by Orlich in 1931 did not dwell too much on this example, okay? I will say more about it in my talk, okay? So it's just an example, and he moved on, that's what you can see there. What was Orlich thinking when he gave this example? I have no idea. I cannot tell you, okay? because he didn't say it. Why? But what's interesting is that we're talking about 1931, a period where we wanted to come up with different vector spaces and Banach spaces. Okay, so remember, Banach spaces were born in 1922, around that period of time. Okay, so what is special about this example? Okay, it was Nakano, okay, who took this example to a higher level. The same example, but he took it to a higher level, and he came up with this now vector spaces. So as you can see here, he replaced n plus 1 by pn, or in the original article, n by p of n. So now you have this p of n, and p of n, you can assume that they are bigger or equal than 1, okay? And because you want to have a vector space, etc., etc. In the sense of topological structure, you don't want to have p less than 1, okay? So I don't want to talk about that right now. Let's just stick to what Nakano was doing. And to these vector spaces, to this function p, and again, look now, because I looked to the original article by our friend Orlich, and he doesn't mention variable exponent spaces. It was mentioned later on, but what you can see there is that the exponent is no longer a number in the classical little LP and capital LP. So now you have the exponent that is a variable, and that's why the name came in, variable exponent spaces. In any case, let's continue now. So it was known to Nakano and others, by the way, that as long as Pn is away from 1 and infinity, you inherit the same properties as the little LPs, okay? So what you want, these two numbers, P minus, which is the infimum, or P plus, which is the supremum, you want them to be away from 1 and infinity. And of course, depending on what you are looking for, okay, what you are looking for, then instead of considering the infimum, you can consider the lim inf and lim sup, okay? But in general, we're looking at the infimum and the supremum, okay? So what happened when P minus is equal to 1 and P plus is equal to infinity? Then the space or the fundamental properties used to establish some of the similar behavior between the classical LP spaces and these variable exponent spaces, they collapse, okay? So people do not touch them, okay? Great. Look at this example, and some in a very simple way will see that, in fact, according to what I was just telling you, that is a simple generalization of the classical LP spaces, okay? LP spaces. So the question becomes, which is really a big dilemma, do we really focus and give it some deep investigation, because it's just a simple generalization, okay? So the question becomes when, oh, I'm sorry, I will come back to that. So here we are. This is the most recent that got me when I started looking into this, that specific example. And I looked at the case when P plus equal infinity, which I told you before, that people were not, they were scared to touch the case P minus equal 1 and P plus equal infinity. So we discovered a lot of things, but still we are, as you will see, I'm concluding with this at the end, that we are still just, at the top of the iceberg, or the forest that hides the, the tree that hides the forest. So you will see it. You will see it in a second, that we are touching. We discovered some stuff, some behavior, some nice stuff, and the people are very excited. The people I'm talking about, the Scandinavian and European schools, working on these variable exponent spaces because they did not know what was going on when p minus equal to 1 or p plus equal plus infinity. So we discovered some stuff that I will, I hope I have time to mention it, okay? In any case. So here is the interesting dilemma. So that's what I did. That was the first one, first result. We still, we have few interesting papers on this, and we're still working on this, okay? So here, let me take you back to the interesting dilemma. What is the interesting dilemma? As I said before, LP dot, which is the variable exponent space, is just a simple generalization of what? Of little LP. And therefore, the question is it worthy of our energy and our hard work? So is this generalization worth it? And the answer is, it depends. So sometimes some of the generalizations are worth it and some are not. So the beauty of it is, what is it exactly that you are trying to do? What is the goal? So for example, here, if you look at something that caught my attention a few years back, when somebody, his name is Nawab Hussain, sent me a paper about what's known as cone matrix spaces. So what is a cone matrix space? It's just when you take a distance and you look at the distance, the value of the distance as a vector. So of course, since you want to have the triangle inequality, so you want to have an order between these values of D, then you have to take an ordered vector space. Once you start working with an ordered vector space, so you are looking at a cone or the positive cone, okay? And that's why we call them, they call them cone matrix spaces. I call them vector valued distances. So the work that was sent to me, and I will give you a reference for it, it was the vector valued distance formulation of the Banach contraction principle, okay? And it was published in the Journal of Mathematical Analysis and Application, which is one of the wonderful journals in nonlinear analysis. And I wrote to the editor-in-chief about this. How did you allow to publish this paper? And he said that was a mistake in his entire career, that he allowed this paper to be published. I mean, it went through and it was published. And that paper, right after its publication, was it triggered something like 300 papers per year in the following subsequent years. I mean, it took like, for example, 3 or 4 years where people just went nuts on these cone matrix spaces. And then I published 2 papers to show to the people that, in fact, what they are doing is not a good mathematical work. So in the sense that, as I said here, the answer, it depends. So sometimes it's worth it, sometimes it's not worth it. So let me give you an example on the same vector value distance where it's worth it to do it, okay? So this example is a work done by Agarwal, who in fact was just answering a question by Lakshmikantan. So Lak was asking, I mean, he had the feeling that that's the case, which is that you get a better behavior for some differential equations by looking at a vector value distance instead of the traditional Euclidean distance. So here is the example. So it's a second order differential equation with boundary conditions, and change it to a first order differential system, and you have this approximate solution. It's not an exact solution, but it's an approximate solution, okay? And the issue is, near this approximate solution, you have an exact solution, okay? Okay, you have an exact solution. And what's interesting is that that exact solution has an attractor around it, okay? And what's amazing is that if you take the traditional Euclidean distance, what you see there is a disk around the approximated solution that you see right here, okay, with the delta, okay? But when you use the vector value distance, you find, in fact, that you have an attractor which is, in fact, unbounded, okay? So it's a strip that is unbounded. It's really amazing. Okay, so what was the distance used by our friend Agarwal, Ravi, using, as I said, in this example, it was Lack that had the idea that this may happen. Okay, and it was, of course, Ravi who carried on this calculation. And so the distance is this one. In our example, in fact, is R2 here, okay, in the previous example. And what you do, the distance now becomes a vector in Rn. And here is the formal definition of what is a vector valued distance. I told you it has to be an ordered vector space. The V plus is the cone, and you have the traditional definition, okay, of the distance, and you generate what's known as a vector valued metric space, okay? And from there, you define the entire topology associated with it, including the sequential topology about completeness, Kaohsiung, and so on and so forth. And then you have this beautiful theorem that was published a long time ago, okay? And this is the theorem that was proved by Ravi, which can be seen as the analog to Banach contraction principle. Here the A is an operator, and a positive operator, meaning that the cone, you send the cone, positive cone into the positive cone, you assume that the spectral radius is less than 1 because you want the iterations to go to 0, and you have what you know of Banach contraction principle, but given in this formulation, okay, in this formulation. And again, the motivation, as I told you, is the idea of that attractor that was bounded if you're looking at the Euclidean distance. But if you look at it from the Euclidean distance to the looking into it using the vector valued distance, then you end up having a bigger domain, okay, a bigger attractor, sorry, not domain. Okay, so the paper I was telling you about that was noteworthy is the one that was published in 2007. By the way, the original paper by Ravi was published in the 80s. So the one that was published, which uses the same formulation of that vector valued distance, the one I gave you, the general formulation, okay, with the ordered vector space, etc., etc. So they gave exactly the same theorem of Banach. But again, if you go back here, what they did, they put k. So d is a vector, but they multiplied by a constant k less than 1. In other words, the same idea as what? As the original Banach contraction principle, okay? The original contractive map. So that's what you have. So in fact, if you think about it, the work by Wong and Xian, in fact, in 2007, is just a simple corollary of the original result by Ravi that was done in the 80s, 20 years prior, okay, 20 years prior. And what's the constant, in fact, even the proof assumes some crazy assumptions like that the cone has to be normal, etc., because some people, when I attacked this case, and they published 2 papers against this, some people in Eastern Europe wrote articles where they put my name in the abstract, saying that I missed the assumption that the cone should be normal and this and that and can't be done, blah 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 blah. But in fact, we know now. I mean, it's nobody is publishing now in cone matrix spaces. So if this really was worth it, it would have survived, but it didn't survive. So first attack, we went from 400 papers, 300 papers per year to almost None. I understand that, as I always say, that some people are tempted because of the pressure that we have right now to multiply publications, but one has to be extremely careful. Yeah, okay, fine. I mean, because of promotions, jobs, etc., but we don't want to just start publishing for the sake of publishing. I'm not going to tell you what Bozami in France once said about people publishing. He never understood why people are publishing, because history will always judge the quality of what you are writing in any case. So in this case, here is an example where to take the vector valued distance, the work done by Ravi and Lakshmikantan, because he's the one who had this initial idea, and look at the work done since 2007 on these cone metric spaces. So sometimes there is a value in looking at certain generalizations, and sometimes there is not. Okay, it's like these abstract formulations. If you think about Banach contraction principle, it's just the theorem by itself was known to Poincaré and to Penaud. I'm sorry, to I always have a problem with this guy. In any case, so it was known. It was known for many years prior to Banach. So what was special about Banach's work in 1922 in his PhD? The idea was to give this abstract formulation using a metric space. Before, it was known in specific cases, mostly in function spaces. So the vectors were functions before. Right? Same formulation, same conclusion, but it was done in function spaces. The case of Banach, he looked at it into the abstract space, which is a metric space, okay? And he gave that beautiful formulation. And again, nobody would have thought that one day fitting, I'm talking about fitting, throwing at you, if somebody needs this paper, I have it, by the way, or a reference, who looked at a logic program in artificial intelligence, stratified program, and explained it. Why do we have one stable model by looking at a unique stable model that we get after omega iteration is because of the Banach contraction principle. So he defined the distance and he explained that the operator involved is a contraction, and that's how we get only one model, stable model, that and we get it into omega iteration, okay? So this is really something I'm passionate about. So what is exactly in this generalization that I wanted to show you here is the concept of a distance, okay? Distance. What is a distance? So this concept, I started working on it around 1986. So we're talking about almost 35 years ago, okay? And it's really puzzling to me, okay? And if you think that why are we doing this? Why do we want to know this? So let me take you back. I want to take you back. Okay, so focus on what you see in the definition. Ignore the fact that D is a vector value. Just focus on the definition 1, 2, and 3. I, double I, triple I. So this is what we teach our students in intro analysis course, whether it's senior undergraduates or first course graduates. And how did we get to this definition? Okay. So if you look and you do a little historical search, you will find out that the people are saying that this definition is due to Fréchet. The way you see it was published by Hausdorff in 1914 in his famous book. It's in German, by the way. that was translated. The third version was translated in 1954, but to English. But the original book, which the title is Basic Set Theory. Basic Set Theory. The second version, I believe, or the third one, he removed basic, and now it's called set theory. Okay, set theory, and it's really amazing how what you see there has to do with set theory. Okay, and you will see the topology, the metric topology coming from there. That's the beginning, by the way, of what's known as topology today. So I have said what I just told you right now. I have said it in many places worldwide. In fact, last week while I'm preparing my talk for both the conference in Saudi Arabia and here, I decided, you know what? Let me read Fresh's thesis, okay, in 1906. So I downloaded the thesis, I found it, and I downloaded the thesis. It's written in French, and I read the thesis. And in fact, there is more to the story. I read the whole thesis in one shot. Okay, I started, I finished it, and now I know what's written in that thesis, and I know what Frechet wrote in his thesis. And what's interesting is that he has two categories. Okay, what he calls class E and class V. Okay. V for voisinage and E for écart. And what we inherited from him as the distance is the class E. Except what? That in the class E, he has condition 1 and condition 3. But he doesn't have condition 2. Now, if you look at all the examples, you will find out that his examples, the condition 2 is satisfied. Okay, but as I told the people before, the condition 2 is not natural. It is natural if you are in Euclidean geometry, the distance between 2 points. But it's not natural if you are, for example, driving. If I tell you what's known as the, for computer scientists, as the flower shop problem, if I tell you I'm driving to get some flowers to my wife and I'm going to the flower shop, I drive from my home to the flower shop, the distance between my home to the flower shop will not be the same as the distance from the flower shop back to my home. By no means. Okay? And to understand why is that is because what is the fundamental difference between this and the Euclidean geometry, where obviously the distance between A and B is the same as the distance from B to A, is because we are not moving freely. We are moving along a weighted graph, along a network. And once you start moving on the network, so you are no longer free to do whatever you want, okay? Especially when you have an oriented graph, in this case, the roads, basically. Yeah? Some of them are one way and some of them are both ways. So you have this oriented graph and you are moving along this oriented graph, and it's a weighted graph because you are taking what? The distance of the edges, okay? That's because I'm computing the distance between the flower shop to my home. And then you find out in a very natural fashion that 2 fails. Yeah. Which brings me to the issue of what's going on here. In other words, what is the distance? Okay. And how can we come up with a concept of distance that indeed is more abstract than what we have learned so far? In other words, that the classical metric spaces that we're teaching and we're learning and we're working with are just a special category. So what is it? Okay, so this is what for many people working in discrete mathematics and set theory is still a problem that is open. And as you can see, what these people did, whether it's Lack and Ravi Agarwal, as well as Long Wang and Xian and others, is just to touch on that question. But they didn't go deeper. It was motivated by other issues that I don't want to discuss here. Okay? So here, 30 years of work with Maurice Puzet from Lyon. And we finally had a paper that we had major problem publishing, I'll be honest with you, in the sense that it's extremely hard to read. And at the end, when it was accepted, the editor-in-chief asked us to cut the length of that paper. It was really a big paper. And we had to cut the length to a certain number of pages. And did we answer the question? The answer is no. We have now an abstract formulation of what is a distance, okay? But just to give you an idea, for example, you can look at graphs as metric spaces, okay? So, and really it's something like, for example, very interesting, how can you define the distance between two texts, 2 points, for example, okay? Stuff like this, okay? So it's just interesting problem. It's still, as I said, is the grail where we are still working on this problem, and it's still an open problem, okay? So let me go to now variable exponent spaces, okay? So before I go into these variable exponent spaces, let me just give you, let's start from the beginning. In other words, what is the roots? So remember, I gave you the example of 1931 that was published in our friend Orlich's original paper, okay? But let's go prior to 1931, the concept of Banach spaces. So Banach spaces, you have to go to 1922, or at least 1920. They knew about completeness, by the way. They didn't call it the word complete. So it's really interesting. If you read articles of that period of time, you will be amazed how they used to say the stuff, okay? But they knew, for example, that the case of, if you look at the case of Q and R, okay? If you look at Q, the rationals, then you can have a Cauchy sequence that doesn't converge. Of course, it goes back to Weierstrass and Cauchy and others, okay? So we're talking about the real topology or the topology on the real line, okay? There are Cauchy sequences which do not converge, and there are Cauchy sequences which converge all the time, and that's your famous construction of the reals as the completion of the rationals, etc., etc. So here, they didn't call them complete matrix spaces, they called them something else, okay? So this goes around the same period of time. So we're looking at the people with major influence on the development of what's known as function analysis, okay? So you have 1902, Lebesgue, with his integration. That was a major revolution of the time. You have the Friedholm and Volterra and so on and so forth for the integral equations. You have Hilbert, of course, who is considered as one who influenced the modern mathematics in real sense. I ask all the students to check, for example, what are the 10 problems that left by Hilbert that he said that these are the ones that will affect and will be the major development of mathematics in the next century. And in fact, the field medalists are the ones who are working in the same areas that was defined by Hilbert in his writing at the beginning there. 1906, Fréchet, okay? And it was a question by Adamov. So as you can see there, you are not talking about some simple names. These are the founding fathers of modern mathematics, founding fathers of modern mathematics, okay? But as you can see, they are all around the same period of time, all of them, okay? So there is absolutely no concept of a distance yet. So they were working with specific examples, okay? Specific examples. Just to give you an idea, capital LP was not born yet. Yeah, right. What you see there, that period of time, they didn't have the concept of capital LP. They had the concept of continuous functions. Yes, of course, with the supremum norm. And there was no norm, by the way. The norm came later on, okay? So this is exactly what the problem is when you look at an integral equation. I was reading an article, a beautiful article, a historical one, of course, where they take an integral equation and they approximate the integral equation by a linear system. And they had a problem because I'm talking about the mathematics of at the time, okay? So they approximate by a linear system, but the linear system was finite dimensional. The number of unknowns was finite. And the beauty is when you move into an integral equation, then you are approximating by a linear system that's becoming bigger and bigger, in fact, infinite. And they had this problem, really they had this problem to work with, which is infinite matrices, infinite linear systems, infinite dimensional stuff. And they were really lost at the moment. It wasn't like a very well, like for example, eigenvectors, as you can imagine, how do you define? They knew before because of the determinant and so on and so forth. That's all what they used to do before was finite dimensional. But now they are talking about what? They are talking about infinite dimensional object. And look what Birkhoff said. I mean, he said that it is my private opinion that Hilbert never mastered the Lebesgue integral. And this is really interesting because to do that approximation, and Hilbert worked with this, to do this approximation, what you can only do is to take a function and approximate the function by its Riemann sums. And that's how you discretize a problem, okay? And that's what they did, by the way, exactly what they did. So now what's amazing to me is that this cannot be done if you're looking at the Lebesgue integral. And this Lebesgue integral really puts a major dent in the fundamental understanding of what is a function. And that's why Hilbert had problem with this Lebesgue integral. Okay, so a function is no longer a function. And this reminds me an article that was published after Einstein's famous article, where it was published by scientists, where the title was "The Second is in Danger." Okay, because when Einstein told them that time is relative, the people they were shocked. And right now, as you can see, to say that Hilbert never mastered the Lebesgue integral is something amazing to me. Of course, if I told you this myself, you would have a little bit been skeptical. But anyway, the point is that as I tell my students, every time that somebody is telling me capital LP and little LP are similar, I mean, I used to believe that, okay? So the capital LP and little LP, one is a special case of the other one by looking at a purely atomic measure. Any question? I heard some noise. I can't see you guys. Sorry. Yeah? I'm almost. You see, I'm.
Well, it should be. It should be okay.
Okay,
so we hear
sorry.
you.
No question. I can see you. I can see you. That's why. I'm really sorry. So again, as I said,
I'm here. Yeah, no problem.
Okay. So capital LP was born in 1907. From the work of Fischer and Ritz. And of course, we all know about the work of Ritz in L2. So as you can imagine, of course, here based on the Lebesgue integral, of calculus. Now we're looking at the Lebesgue integral, because before, as I told you, a function, you have to go to the old traditional definition of what is a function, okay? And now Lebesgue has changed that. I mean, you have some awful functions, they become extremely nice. Why? Because in the Lebesgue mind, f equal g does not mean f of x equal g of x for every x. You understand now? Huh? And many of our students, unfortunately, do not master Lebesgue. And we go and we take them to the abstract measures. That is the biggest mistake you can do for somebody like that. Okay? Please understand Lebesgue first. Try to understand what's going on with the Lebesgue measure, taking you from the Riemann integral to the Lebesgue integral. It's a major change, and fundamental change there, right there. Okay? So in any case, these spaces, what's known as classical spaces or classical Banach spaces, they were born after the people, 1907, okay? And it's amazing that little LP, and that's why, because at this stage, no measure, no abstract measure, we're just looking at the Lebesgue integral. And what's amazing is it took another 6 years before we saw what? Little LP. So when somebody tells me little LP and capital LP are the same, I lose it now. Now, of course, when I was a student, I accepted that. And as you can see, quickly, little LP enjoys properties, especially, the weak topology. The weak topology. Now we're talking about Banach's school in the 30s, where we started to have this fundamental and Banach theorems and all the fundamental theorems of function analysis. Then we have now something called the weak topology, which, by the way, what's his name? Fréchet worked with, but he did not know it in that formal stuff that we teach to our students that was born in the 30s. So the weak topology between capital LP and little LP, guys, I'm telling you, it's an ocean between the two. When you say capital LP and little LP are the same, you are really hurting whoever is learning these materials, hurting him. They are totally different, okay? When you look at the weak topology in capital LP and the weak topology in little LP. The weak topology in little LP is more connected to the pointwise convergence in capital LP, okay? But has nothing to do. The other one, you have other convergence, like the convergence in measure and so on. It's really complicated. It's really complicated. Anyway, so what is exactly I want to talk about? Let's go back to the Hilbert space, and you have the famous parallelogram identity, okay, that you have in capital L2. It comes from the real line. It comes also from R2 and Rn. And it's very simple to obtain this one, which is not known by the student. And here, this one is interesting. It has a property that, hold on, control, how do I exit? Okay, so this one here, okay, this one, it's interesting because what it tells us is, if you take the unit disk, okay, and you take, I'm talking about vectors, okay, and you want these vectors to be far from each other, okay, not too close. Then, if you look at the middle point or the middle vector, it's inside. But it's not just inside, it's really inside. So you have a control here. You are far from, see, the control is right here. You are far from the surface. I'm sorry, the sphere. And this control, the calculation here, this control here, is given with how far the two vectors are. Okay, the two vectors are. If they get closer, the middle one will get closer to the sphere. But the uniform control, is the one who did it is Clarkson, and this is you see it right here. Huh? So if you have the norm less than 1, norm of y less than 1, and they are far from each other, okay, there is a control, then you have the vector, the middle one is inside but far from 1, which is the sphere, okay? And that was done by Clarkson in 1936. He's the one who noticed this. Okay, now, if you want to do it for LP, okay, so you need an inequality that is satisfied that he's going to use, and that's the one you see right here now, okay? And what I want you to understand is the control is coming from here. See, this term here is what will give you the control, okay? And this is just a property on the real line, huh? So here you get this, and then you get this. So that will give you similar control, and that was the paper published by Clarkson where he proved this in capital LP and little p, and he called it uniform convexity. Huh? That's what he called it, uniform convexity. Okay? So what happened when P is less than 2? By the way, if you go back here, what happened to LP when P is less than 2? They got it by duality, because the dual of LP is LQ, and if P is bigger than 2, Q is less than 2. So I'm not gonna talk about the geometry of Banach spaces, where it shows that uniformly convex, the dual is uniformly smooth, and if you are uniformly smooth, the dual is uniformly convex. So what you want to show is that capital LP is in fact, for P bigger than 2, is in fact both uniformly smooth and uniformly convex, and that's how you get that LQ for Q less than 2 is also uniformly convex and uniformly smooth. But if you want to do it by hand for other reasons, including the issue of variable exponent spaces that Sandhya-Rasan worked on, okay, then you need another inequality. Complicated. I mean, this inequality is not simple. I'll be honest with you. It's a challenge. And again, look at the middle. The middle is right here. And this one is what's going to give us, again, that control to be inside. You see, this part here. Okay? But what happened here is this part, though it has a minus b over 2 here, the same as the other one before, but now you have this p times p minus 1. This is terrible. Why? Because when p is close to 1, this control dies. So when p gets closer to 1, this control dies. As long as p is not close to 1, you are okay. Do you see it now? Do you understand now why we got that idea that p minus bigger than 1? That's coming from this here that you see here. Okay. Okay. So Orlich, what did he do? Orlich, I'm going to go a little bit faster because I want to touch on something else that's also interesting for the younger mathematicians. Orlich, in his paper, he gave that famous example I showed you, that amazing example. But quickly, he moved away from it, and he came up with another example. That example took off, and that example became extremely popular, okay? Where you have a school in Poland around that, and of course, even a school in China, and I'm referring here to Chutao Chen, which, by the way, I published a paper with him, and we wrote in the paper Chen Chutao. It should be Chutao Chen. He did work on this because of his advisor who got jailed during the anyway. Well, I'm not going to tell you the history of the Orlich group in China. That's for another day. In any case, so what is the example? What Orlich did, he said, okay, let's take the LP spaces. And what defines the LP spaces is the function t to the power p. Okay? So he replaced t to the power p by a function phi. And he assumed that similar to t to the power p. Let's not open the subject. It's an ocean there. Let's not even open it, okay? Let's just stick to simple to understand, and then we can talk about complicated. So look at a function, a graph function, that is as simple as t to the power p. Same behavior, same properties, okay? And now consider this. That was in his paper, by the way. The integral from 0 to 1, you can put it in any integral between any sets you want, that's fine. But look at now this, okay? Of course, if you take t to the power p and you go back to capital LP, there is no lambda. Why? Because lambda will come out as 1 over lambda to the power p, and then you are okay. Then you don't need lambda. But in fact, it was done by him. I'm talking about by Orlich, okay? So this is the LP spaces or Orlich spaces. Okay, so he went away from the amazing example I told you about. Okay, now, what is the norm? So the norm, we call it the Luxembourg norm because of his work with Zenin on the function spaces. He has a fundamental work done with Zenin on functional analysis or functional spaces. But in any case, this is just a Minkowski functional. Okay, the norm that you see there is just a Minkowski functional of a balanced convex set, and you have it. But what I want you to understand, this is the classical Orlich norm. So you have Orlich space and the classical Orlich norm. What's the difference now? Right there, 1930s, we have a major problem. What's the problem? The problem is that the norm and the integrals are defined in a complicated, indirect way. And that's why when the people, they wanted to study properties for Orlich spaces, all the properties that we know in the classical case, they are really, it's extremely complicated. You have no idea, okay? Including, like, for example, the work by Clarkson, which is the uniform convexity, okay? It's complicated, extremely complicated. We are going into a different dimension, going from the classical LP spaces to the case of Orlich spaces. Okay, so what's amazing is that Orlich did not see something. He did this, yeah, and also the Orlich school, including Mushilak, because they developed the whole school in Poznan, in Poland, but they did not see something. It was Nakano saw something in this work, okay? So the idea is that integral that before gave us the norm, and that's it. Now, it was Nakano 1950 who saw this tool that he called the modular. He called it the modular. Don't ask me why, guys, okay? And that's why you see that famous book, modularity semi-ordered linear spaces, okay? So he saw the concept of a module, which is that integral that you see there. You see what you see here, right here, okay? So the norm is coming from this object, yeah? And he said, okay, so now he came up with a concept known as the module or the modular defined on a vector space. So again, what do we have? We have vector spaces that was known before. We have the distance, 1920s, the norm formal by, and he called them spaces class B. I'm talking about Banach and his friends, and that's the norm, okay? And now we have this concept of what? The modular. And that was done by Nakano, which, by the way, is more general than what? Than the norm. The norms are a special case of regulars. So what is the fundamental problem is number two. This is terrible. Number two tells me what? That I don't have homogeneity of the norm. Yeah. Homogeneity of the norm plays a major role. We don't. Because if you go back here, you don't have it. Because phi can be any functional, yeah. And any function. And here, you don't have the triangle inequality. You don't. Yeah. Yeah, you don't have the triangle inequality. Neither 3 nor 3 prime. It doesn't matter whether it's convex or not, but you don't have the triangle inequality. You don't have the triangle inequality, you are in trouble. Why? Because what is rho of 2x? The rho of 2x is going to be rho of x plus x. And if you were having the triangle inequality, it will be less than rho of x plus rho of x, and that will be 2 rho of x. But since you don't have it, then you may have a problem with rho of 2x. So in other words, rho of x may be finite, and the rho of 2x may be infinite. And by the way, it's an extended function. Huh? So rho can take the value infinity. All this was known to, by the way, Nakano. Okay. So to a modular, we have a vector space, and we have a norm that we also call the Luxembourg norm, but in fact is not. It's the Minkowski functional, and you have this norm. So you have a normed vector space, okay, from the modular sense. And the example, of course, was the Orlich spaces or modular function spaces. In 1988, when I met this object, I worked with Kozlowski, I worked on modular function spaces, okay? So remember I just said rho of 2x and rho of x, and the people quickly, they saw that, including Nakano, by the way, that central concept for the study of modular vector spaces is what's known as the delta 2 condition, okay? And that's, you have different types. They are all falling under the same type and the same idea, which is that rho of 2x is controlled by rho of x in some ways or some other stuff. So, okay, here, and if you go back here to our example now, okay, and I'm going to stop right here, is the fact that this example, amazing example by our friend Orlich, if you take the vector space x equal r to the power n, and you look at sequences, and you define this object, you generate a modular. And what's interesting about this modular now, this one here, is it doesn't satisfy the delta 2 condition. Why? Because if you put a 2, you are going to have 2 to the power n plus 1 out, and it may become infinite. Yeah. Do I have more time, or shall I continue, or shall I stop here?
I think your time is up. So
Okay.
Can you make a conclusion?
By the way, Professor Som, I have the entire paper, which, by the way, I am just at 52 slides. I still have about another 57 slides left, but I can send it to you, and you can share it with the people, okay?
Yes, please. You can certainly send
I talk about this new modular uniform convexity that we discovered with Chen Shutao, and the usefulness, and how some cases where p plus equal infinity is okay, where we fail the delta 2 condition, but we still have some amazing behavior. Yeah, some amazing. So I will stop here. There is more to it. There is more to the story. Okay.
Yeah, thank you. Yeah, it's a very interesting and very informative talk. I think every one of us learned a lot from the speaker. So is there any question or comments from the audience?
It is, in fact, a very thought-provoking talk, and really very interesting, and giving a very, very deep understanding of the distance concept in different spaces. Really, I am sure that all the participants are benefited largely. And I hope that Professor Khamsi will give some other time to finish his another 50 slides. In some other session, we will have him over
Why
here.
not?
And I am certainly thankful to Dr. Gopal, who has given me this opportunity to invite you. And I'm really, but I know you from a long back, but I have never met you or whatever it is. So really, really wonderful talk.
Oh, yeah, please, Professor Sai, do you have a question or comment?
Good morning,
Yeah.
sir. Myself, Hardeep Singh from Aligarh Muslim University, India. Sir, I have a question.
Yeah, go ahead.
Sir, you have given the definition of the uniform convexity. How the convexity is linked to the uniform convexity? That is there any relation between the definition of the convexity and uniform convexity?
You mean convexity and uniform convexity, right?
Yes, sir. Yes, sir. Actually, in uniform convexity, term of convexity is used.
Yeah, the terminology is coming from, as I told you before, from the convexity of the unit sphere. Okay, but the problem is if you just stick to the the convexity of the unit sphere, you end up into what's known as the strict convexity. You need that uniform control, and that's why you have what's known as uniform convexity. And in the original, some of the original work, it wasn't called uniform convexity, it was known as uniform smoothness of the sphere. Yeah. But there is more to it. There is more to all this. At the end of my talk, I talk about what's known as uniform convexity in every direction. That was Karkavi's work, and strict convexity and the connection between the two, and so on and so forth. There is more to the story. There is more. I wanted just to go to the beginning where things were simple. It got complicated, but if you understand first the beginning and you have solid understanding of the beginning, then you can do complicated stuff. That's what I try to do.
Okay, sir. Thank you.
Okay.
Yeah, please.
Yeah, please.
Dhananjay, I know you're gonna say something. I would have been surprised.
Professor Khamsi, it's our pleasure to, by any means, to listen you. We understand, especially the people who really have been, heard or witnessed your lectures and the stuff. Only thing I by interest myself, I just wanted to little bit know if it, what about the best one, the ordering, if we can do something there, please, if anything in your mind, please, for us.
Again, Dhananjay, say it again.
My point is some kind of the order structure or some graph theoretical aspect in modular sense. Is there any possibility for us?
Yeah, we did. In fact, again, I'm so sorry to take time from you guys, but keep in mind, okay? What I wanted to say is that if we don't have a better understanding of the original part of what you learned today, all the modern mathematics, all of it, from computer science, I'm talking about mathematics, working with computer science here, or fuzzy mathematics, etc. If you don't understand the foundation, okay, or you have a confusion about the foundation, you will keep carrying this confusion all through. So my point is, what do we do now? Yeah, we do some amazing stuff. Like, for example, the idea of what I called order uniform convexity. So I only assume that the middle point is inside the ball for comparable elements. Okay? So why? Because all the natural classical BARC spaces are ordered. Okay? There is a natural order there. Okay, I'm talking about function spaces, etc. You have a natural order, and therefore we have this concept known as order uniform convexity. And what can we do with it? Okay, so yes, we do have that, and we published a paper on this, but to the best of my knowledge, it's fairly recent. So the best of my knowledge, it still did not pick up a little bit more attention. Yeah. But I can send you the link, Dhananjay, okay? I will send you the link or the paper itself, okay?
Yeah, thanks a lot. Thank you.
Oh, Kamar, I see Kamar. I'm so sorry, guys.
I have a question.
I'm really sorry.
I have a question.
Sure, go
So
ahead.
both of you and Professor Wong.
Oh, yeah,
Okay.
sorry, please.
So when you both will be coming to India?
I swear, Kamar, I knew you were gonna do it to me. I knew that.
When can I see both of you in India?
Okay.
Yeah, before. Soon.
We should get them, certainly. We should get them sometime next year.
Thank you, Kamar. Thank you.
Okay. I think maybe we should end this section, and you leave the private communication to you later. Okay, so we thank the speaker again. Let's just say thank you. Yeah, thank you very much, Professor.
Thank you very much, guys. Thank you.
Yeah,
Thank you.
Okay, so Professor Shum, I return it to you.
Yes. The first talk is now over. The overwhelming and very thought-provoking talk by Professor Khamsi. Now I invite Professor D.R. Sahu to chair the next session or next talk to be delivered by Professor M.P. Wong.
Thank you, Professor Som. Professor Wong is professor in National Yat-sen University. He did PhD from Korea University. Professor Wong has his specialization in functional analysis, operator theory, in particular operator algebras. He has many contributions in several international journals, and he's also editorial members of various reputed journals. He has published about 216 papers, and he has contributions in some like journals. So I welcome Professor Wong for your talk based on semigroups and fixed point theory. Professor Wong. Hello. Please unmute Professor Wong.
Please unmute, sir, Professor Wong.
Hello, Professor Wong. Please unmute yourself.
Sir, your mic is mute. Unmute.
Hello. Please unmute. Maybe it can be handled from the control side.
Let me check. Let me check.
Okay. Megha, I think.
Hello, Pankaj. Megha. हेलो अंशिका, देखो वो प्रोफेसर वोंग का माइक म्यूट है. चेक इट फ्रॉम द कंट्रोल साइड.
Hello, Megha, are you listening me? Hello.
Hi. Can you hear me?
Yes.
No.
Okay. Yeah, I need the authority to share my window. I cannot share my window, so I need authority.
Okay, you can mail the slides. We will share from here.
Okay, yeah. No, I think you need to assign the authority to me. Something wrong. Yeah, I cannot share my window. Let's see. No, I cannot share it.
Megha open mic and some other activities?
Maybe I log out and log in again to see if it works. Okay.
बहन ये तो वॉल्यूम बंद कर ले या फिर वॉल्यूम लो कर
I do not have the authority to share my window.
You can share it.
So please
cannot
share screen with us.
Okay.
Then we'll share for you.
I see. Okay. Let me. How can I send you to you?
Through email.
Email. Yeah. You are right. Good email. Okay. Just a moment. Let me send it to you. Okay.
मेघा ये नॉइस कहाँ से आ रहा है? देखो तो.
So still,
just a moment.
now it's okay.
Hello.
Hi. I'm working on it. Yes, just
Yeah,
a minute.
yeah.
Yeah, sorry. Okay, for Zoom, I have sent the file to you by email. Yeah, maybe someone can try to assign me the authority to share the window. Maybe assign me to be the co-chair, then I can open it. It's amusing.
Hello, we are going to share it. I'm sending it to Megha. Yeah.
Okay.
Hello, Megha, you have received, please check, you have received the file, open it and share the window.
कर दिया उन्होंने.
अभी आया नहीं है. It is not yet visible.
Yes, sir. I'm sharing my
Okay.
screen. एक ही बार तो बोला, गलती से हो गया, मुझे ध्यान नहीं था कि मैंने ऑफ किया था.
So I wonder how Professor Khamsi can do this just in last talk. So maybe the network in Taiwan is not quite good. I'm sorry. So, no, I keep on trying, but the system said I do not have the authority. Oh yeah, I said something. Okay, I see my file now. Can you make it to be full screen? Yeah. Okay. But unfortunately, I have no control on my file now. So, but I need the full page view. So can you make it to be a full page view?
This is the full page view we are getting.
Well, but when you can, yeah. Okay. Let's let me begin. I'm sorry to. I have only half an hour left now. So I am going to speak on some job work with my student, Dr. Moy, on the amenability of semi-topological semigroups and fixed point property. I would like to thank Professor Shum for this wonderful chance. And also I would like to thank my friend, Dr. Sawu, for the introduction. Okay, will you please go to the next page? So this is not the full page view. So something will be very amusing later. You will see that. Okay, suppose that we are given a semigroup. So there's a algebraic object with a multiplication, and MM define the amenability of the semigroup in the following way. He said a semigroup. Oh, here we do not have any topology on the semigroup. So a discrete semigroup is called the left amenable if there exists a left invariant mean on the banana spaces of bounded scalar sequence. So could you go to the next one? Yeah, that is not interesting. Okay, in fact, they prove that every left amenable discrete semigroup of continuous alpha map divided on a compact convex subset of a locally convex space will have a common fixed points. Next piece. Yeah, please, yeah, next one. So this reduced the study of the existence of a common fixed point of a continuous alpha function, alpha action of a semigroup to that of the existence of a left invariant mean on the balance space of the scalar function on S. So we are interested in the problem of the existence of a common fixed point of a family of action. And this, in fact, depend on the algebraic structure of the semigroup. Oh, that's the point of he want to make. Okay, will you please go to the next page? So now we want to get at the topology to the semigroup. So we say that as semi-topological semigroup, which is a semigroup with a Hausdorff topology, such that in the topology, the multiplication are separately continuous. That means for any fixed t, S to Ts and S to St are both continuous functions from S into S. Because S is not a group, so this multiplication does not have an inverse. So it's only continuous function, not necessarily homomorphism. Okay, it's different from the group setting. Oh, please, next one. So we denote CBS, the banana space of continuous and bounded value function on S with the supreme norm. In case for the discrete group or the group without topology, CBS is just a L infinity S, those bounded scalar function on S. So this is a generalization from the discrete case to the semi-topological case. Please, next. Now we said that a mean of CBS is in fact a bounded linear functional of norm 1, and yet have the norm pit at the element constant function 1. In other words, a mean is a positive linear functional of norm 1. Please, next one. Now, equivalently, a mean is a linear functional on the continuous bounded function on S, such that is something in between the mean infimum and the supremum of the function. So anything in between the maximum and minimum can be considered as the mean of the function, right? So there's the term mean come from. Oh, please, next. And we call that the mean is well, we call net translation. There is we define a new function from F. There's a LSF. The action of LSF T is the translation of S of T by S. So we have a f of st. So that's called the left translation of the function f. Now a mean is called a left invariant mean if is a left translate. Could you please go a little bit downward? Okay, if yes, an invariant under the left translation. So example is the Haar measure. So if you're working on the locally complex Hausdorff group, the Haar measure is divided to be the mean left translation mean. Okay. Okay, please. Well, I think this will be a problem. I cannot finish in time. Maybe I send you another file so that this file will be easier to handle. Okay, just one moment. I send another file to Professor Shum so that it will be easier to handle. I'm sorry for this trouble. Yeah.
Sir, you're not audible. Professor,
Yeah. There's some trouble here.
now
Okay. Yeah, because in this case, I cannot have time. I do not have enough time to finish it. Okay. Anyway, let's begin. Let's continue. So we have example of discrete group of the integer. So the discrete group of integer under addition is a left amenable. Okay, what the left translation mean? In fact, we define in this way. We just think we take the average of the function from the function value of the function from -n to n. So we take the average of this 2n plus 1 value. So this local mean of the f around 0, and we take n going to bigger and bigger, and we notice that all such a local mean have norm 1. Okay, and also the limit of the local mean will be left translation invariant because of this equality. So in this way, any cluster point, any V-star cluster point of this bound sequence Mn will be a left invariant mean, although we cannot exactly write it down. Well, we do not know the formula. But we see that any cluster point will be a left translation mean of norm 1. Okay, another example is the f. Could you please just let all the letter appear in? Okay, well, you just keep on, click on it, and you will see that all the stay here. So another example is the real number under the addition. There's also a left amenable group. Now in this case, we do the same thing. We take the local mean of the function f from -n to n, and then any cluster point of this Mn will be a left translation invariant mean. Okay, please, next. Now, in general, every compact topological group is left amenable. Well, everyone knows that we have a Haar measure here, so it's left amenable. Yeah, please go on. Okay, and then the Haar measure define the mean in this way. Now, for locally compact group, we have some trouble because the Haar measure may not be finite, so we cannot take the average like this. So, in other words, a locally compact group is not always left amenable. That's the whole theory of extract harmonics arise. Okay, please. Next one. Oh, please, the next one. Yeah. Now, if we look at the free group of two generator, which is locally compact discrete group, and this is an example of not net amenable group. And this free group is generated by two netter, so that every element is a finite work of A, B, A minus 1, and B minus 1. Oh, please go on. Could you go to other pages? Thank you. Okay, an action of a semi-topological semigroup is on the Hausdorff topological space K is a mapping from S time K to K, so that you can think that is a family of map TS with index from S, and that is TS is a function from K into K, and we assume that this kind of index satisfies the semigroup property. And also, there's a continue the separate sense. So you can fix one S, and then it's continue function of X, or if you fix X, is continue function of S. Okay, we said that point X0 in K is a common fixed point if it is the fixed point for all mapping TS from this action. Now the problem is, do we always have a common fixed point? Now, there's a condition to ensure this. So if the action, if a mapping T from a convex subset of balance space into itself, we call it non-expansive. If the norm of Tx minus Ty is less than or equal to the norm of X and Y, then T need not have a fixed point. If K is a compact convex set of balance spaces, then we will have a fixed point. But in other case, if K is only closed and bounded, we may not have a fixed point. Now, there's an extension of this result by Demar. He said if K is a non-empty compact convex subset of balance spaces, then every commutative family of non-expansive mapping will have a fixed point. Now we know that every mapping have a continuum mapping have a fixed point. Now, if the family is a commutative, then you will have a common fixed point. Okay, in this way, we want to combine this together to make the following concept. So, an action of a semigroup on a subset of balance spaces is called non-expansive if every mapping TS is non-expansive. Now, Antonio Lau suppose that if K is a compact convex set of balance spaces, if S is a left amenable, that means you have a left amenable left transformation mean, then every continue non-expansive action of S on K will have a common fixed point. Now, if you look at the proof, you will see that the author made use of the normal structure of the compact convex set. We know that every non-compact convex set have a normal structure, but the convex is not true. And also, really compact convex set may not have normal structure. So the result of Tony Lau does not necessarily extend to V-star convex set or really convex set. So he raised a problem in the following. He asked that if whether the left amenability of a topological semigroup S will ensure that every V-star continue non-expansive action of S on a V-star compact convex set K has a common fixed point. If you could stay here, not move too fast. Yeah, thank you. Now, if we embedding the balance space into a double dual space, then we can make another consequence. So he asked, is every weakly continuous expansive action of S on a weakly compact convex set has a common fixed point if the semigroup is amenable. Okay, so now we want to answer the low question in a little bit more general context. We will ask what happens if the action is not expensive, it's not non-expensive. Now, in this case, we can construct an action of a commutative and thus a left amenable discrete semigroup on a convex set without fixed point. In fact, it's Du Bois. He said that if we have two continuum functions and they are commutative in the following sense, fg of x equal to g of fx, but they have no common fixed point. Therefore, the assumption of non-expansive lab cannot be dropped easily. We need to find some substitute. Okay, please, next one. Okay, so we need to go back to the algebraic structure of the semigroup. We said that a subset I of a semigroup is called a left ideal. If you have the properties that S times I on the left will be absorbed into I. A left ideal, okay, remember that we have only multiplication. We have no addition at all, okay? A left ideal is called supported by some element T if it can be written as something like IT for some other left ideal I and the I element T, okay? Now an action of a semigroup on a subset K of balance space is called super asymptotically non-expansive. If we have the following property, TSX minus TSY, we have the norm less than or equal to then the norm of X minus Y for all S in a left ideal supported by T and for all Y in K while X is given. So this is a condition weaker than the non-expansiveness, right? But it's quite strong. It's stronger than other asymptotically non-expansiveness. Okay, let's see what we have. Craig and Shrew introduced a concept called point-wise eventually non-expansive. It said if we have a single map T and T and all its power n will be non-expansive, then we call it, but here X is fixed, but Y is arbitrary, okay? Now, in this case, we say that T is point-wise eventually non-expansive mapping. Now, suppose that you have a family, commutative family of finitely many point-wise eventually non-expansive map on K. Then the semigroup generated by this family, there's the finite product of all such mapping will be acting on K super asymptotically non-expansive. Okay, so there is this is not a very new rare extension because someone else has used it in other paper. Okay, please next. Now, following this idea, we saw that the super asymptotically non-expansive net is strictly weaker than the non-expansiveness, even for compact or commutative semigroup. Yeah, please go on. Now we need another property. We call it a right reversible. So suppose that we have a semigroup S. Then we said S is a left reversible if we have for any two left ideal, any two co-left ideal, the intersection is non-empty. In other words, the causal SS intersection, the causal ST will be non-empty for all element S and T. Okay, if S is a group, that's automatically left reversible. So this is not a very string condition. Okay, please. Now, for example, all commutative semi-topological semigroup, all topological group, and all discrete inverse semigroup are right reversible. So it's a very common condition. Yeah, please. Okay, now here's the theorem. Let S be a right reversible and left amenable semi-topological semigroup. And K is a weakly compact convex subset of Banach spaces. Then every weakly continuous and super asymptotically non-repressive action of S on K will have a common fixed point. So this is extension of Antonello problem. Yeah, please go on. Okay, but we need to remark the converse of this theorem is not true. That means that the condition is not necessary and sufficient. For example, for the free group of two generator, we have a fixed point property. We have a wide reversibility, but we do not have the lab amenability. So the lab amenability is somehow not equivalent to the fixed point property. Yeah, please go on. Now another result us say that if S is a right reversible and left amenable topological semigroup, and K is a restart compact convex set, so yes, now from the weakly compact to restart compact is even weaker. But we need another condition that's non-separable. Then every restart continue and super asymptotically non-repressive action, we have a common fixed point. Yeah, please, next one. Here, we have an even weaker condition like the random negative property. We will see that if the action satisfies the random negative property, then we also have fixed point. Please skip this one. Yeah, please go on. Yeah. Okay. Okay. Now, please go on. We skip this one too. Thank you. Yeah, please skip this one. Yeah. Okay. Now we enter into another phase. So we want to extend this Banach space result to the locally convex metrizable space setting. So from the Banach setting to the Fisher setting. Now we record that a locally convex space is metrizable if there is a counterfamily or semi-norm defining the topology. Please go on. Now we said that the metric is a good metric. Okay, the metric may not be good, but we can always replace the metric with a good metric satisfy the following condition. So the metric can define the topology can be assumed to be translation invariant. So the distance between x plus y and x plus c will be equal to the distance between y and c. And also all the metric ball is open and also absolute convex for all R. So absolute convex means if you have 2 points in this ball, the line joining them will be in this ball. And also if you have x in here and alpha is modulo 1, is complex number, EI theta, or modulo 1, absolute value 1, then lambda x will also belong to the ball. Okay, someone call is balance. Okay, in this case, balance and convex. Okay, if tau is a locally convex topology, which is weaker than this D topology, then and D is a tau lower semi-continuous. Now we will have something good here. We call tau a D admissible topology. Okay, so we have 2 topology. The locally convex topology is divided by a good metric D, and also we have another topology. We have something compatible with the dual pair. So the tau topology will be called the D dimisible if it's weaker than the D topology, and but the D is a tau lower semi-continuous. For example, the weak topology is a D admissible. Yeah, please go on. Okay, so the weak topology or the restart topology are all admissible with the norm-top metric. Okay, now in this case, the norm metric is a good metric. Okay, now we assume that XD is a complete locally convex metrizable space. There is a Fisher space, and let K be a convex set in X. In action, we call it super asymptotically non-expansive if it satisfies the condition we present before, but with the norm repeated by this metric. Okay, so with respect to the metric, all the mapping TS are not expensive. And in the following sense, okay, they're too technical. I do not want to go into this part because I do not have enough time. Please go on. Yeah, please. Yeah. Yeah, please. One more page. Okay. So okay, that's it. So we have this film for the locally convex space. Let X be a right reversible and left amenable semi-topological semigroup, and tau is a d-immiscible locally convex topology of a Fisher space with a good metric D. Then S, we have the following fixed point property. FV super asymptotically D non-expansive and jointly tau continue action of S on a D separable and tau convex subset have a common fixed point. Okay, I know that it look too awful to you, but for the Banach space setting, you can think the D metric is the norm. Okay, it's the norm metric, and the tau topology is the width topology or the width star topology, and you go back to the result I presented just previously. But here we have a generalization to the locally convex space setting. Everything will be very abstract, I know. Okay, please go on. Okay, now we go to another phase. This is I want to apply our result of fixed point theorem of semigroup to the quantum physics. So in physics, in particular in recently in quantum information theory, they are interested in something called Bradman distance. Okay, let U be a non-empty open set of a Banach space, and let G be a Gödel's differentiable function at Y. Then we will have a bounded linear functional in E star. There's a Neper G Y. We call it the gradient of G at Y. Satisfy the following condition. In other words, Neper G Y is the derivative of the function G. Okay, please go on. Okay, we say a function G is strictly convex if we satisfy this strictly convex inequality. Please go on. Now, if G satisfies these two conditions, we can define the Bradman distance dG, which is a Gx minus Gy minus the bilinear form of x minus y, and is the dual functional Neper Gy. Okay, please go on. Now, in recently work of the quantum information theory, they define the Bradman distance between the so-called quantum data. There's the positive matrix with trace 1 in this way. Okay, please go on. Now, I have two examples for you. One is the classical divergency. Suppose that A and B are matrix, and we define DGAB in this way. You'll see that D in this case, G is given by trace FA and F is the square function. Okay, please, the next one. And then another function used in quantum physics is the so-called Yamagaki relative entropy, defined in this way. Okay, please, next one. And next one. Okay, now we will see that from this picture, what is the distance mean? Okay, suppose that you have a function G, this is in the red line, and then at the point Y, you have a tangent line using the blue line, and then away from Y, you have another point X, and you look at X, you correspond to 2 points. One is the image on the red line, another is the image on the tangent line. Okay, and we define the distance between Y and X and Y to be the distance between the red line and the tangent line. So you see that if for the classical case, the Bradman classical divergence, you exactly end up with the square of the distance of X and Y. Okay. Now in this case, X and Y is symmetric. Okay, please go to another page. Now, but in general, they are not symmetric. In this case, you use the function x log c log c. You will see that if you measure x to y, there's on the left-hand side, the distance is bigger than you measure from y to x. So it's the distance on the right-hand side. So in this case, the Berman distance is not equal. It's not symmetric. Okay, please go on. Yeah, please go on. Go on, please go on. Just keep on until you finish. Yeah. Okay, stop here. So the Berman distance have some good thing and some bad thing. The deficiency of Berman distance is that they are not necessarily symmetric as we see from the picture, for example, and not necessarily satisfy triangle inequality, and not necessarily translation invariant. So very bad. But you have also some good property. For example, you can always have the Berman projection. So you can, for a convex set, you can co and convex set. In this term of the Berman distance, you can always find the closest point in a set to any point outside the set. So that you can define the Berman projection. And also you have a very good property. There's a very wonderful property. You call the Berman OPA property. Well, if you work on the fixed point theory, you will see that we use the OPA property very often. But unfortunately, not every balance space have the OPA property. But for Berman distance, you always have the Berman OPA property. So that means you have many good tools in doing fixed point theory with that Berman distance. Okay, please, next one. I hope to finish it in time. Okay, please go on. Next one. Please go on.
Oh, sir, you can take 5-7 minutes more. No problem.
Oh, thank you very much. I appreciate this very much. Okay. I have a friend who just passed away, unfortunately. He is a Wataru Takahashi. And Wataru studied fixed point theory, and he had contributed about 400 papers in this subject. And there are two interesting properties he usually mentioned in his paper. He said that if we have a mapping T from a convex set C into itself, we call it non-spreading. If we satisfy the inequalities that the 2 of the square of the distance of Tx and Ty is less than or equal to the sum of the square of the distance between Tx and Y and X and Ty. And also, it defines the general hybrid mapping such that we have a two real number, alpha and beta, some of them can be 0, satisfy the following inequality. So there's a very complicated setup because R and beta can be negative numbers. So you have some surprising property. But anyway, Wataru studied these two mapping very often, and generally I wrote a paper about fixed point of this mapping. Okay, let's go on. Please, next one. Now, okay, please, we have 4 of them. Please go down, go a little bit. Okay. Okay, so we want to extend this result to the Berman setting. Well, remember that in the Berman setting, we have Berman OPA property. So that's very good. So we just replace the norm with the Berman metric. Then we have Berman non-spreading mapping, Berman general hybrid mapping, and 2 more. Please cut on. Please, yeah. And 1 more, maybe 2 more or 3 more. Okay, stop here. Yeah, thank you very much. Okay, so and also we can have other 2, the Berman non-expansive and the Berman lab asymptotically non-expansive. So you do not need to remember the detail. You just think we replace the norm or the metric by the Berman metric. Then you get all such goodies. Okay, so they are just natural generalization of the common use of terminology. Okay, please, next one. Thank you. Okay, we consider action of a semigroup on a subset C of a reflexive balance spaces. Now we say that point C the orbit of a point C is OC. That is, you keep on working on C by TS. Okay, usually we think TS is T to S, the power S power of T. So it's in fact exactly the orbit of C under T. But now we do not necessarily have this kind of action, but we use the same terminology. So we said that if we have a action and then we have a bound orbit, and then from S to this orbit is continue in the norm topology, then we have something good. Oh, please go on. Okay, now then we can consider bounded linear functional. We call it the barycenter of this action. Okay, here the notion mu S standard for mu acting. Well, we have a mean, right? We have a mean of the semigroup. Let the left translation mean. We have the mean, and then the mean add on the function S to TSC X star. So S is a variable. Okay, so S is a variable. And then we add on this one, and then we get a functional, and this functional will be bounded linear functional on the on E star. Okay, please go on. Now, if you work on the abstract harmonic analysis, you see that it usually give you the barycenter. So we call this functional define an element, okay, in E. Oh well, in fact, it should be element in the double dual of E, but we assume that E is a reflexive banana spaces, so it become an element in E. And because we assume that C is a cosine convex, then in this case, the barycenter belongs to C itself. Okay, we call this is the mu barycenter of the bounded orbit. Please go on. And next one, please. Okay, thank you. Now we pretend for a moment that mu is a probability measure. Of course, it's not a probability measure in general, but we think, just imagine that it's a probability measure on S. Then we could write the barycenter C mu in this way. So TSC is the orbit. So we took the average of the orbit, okay? Because it's a probability measure. So it's the average of the orbit. So the average of the orbit is the barycenter, yeah? And because C is closed and convex, so the orbit, the barycenter of the orbit belongs to C. Okay, now if you have another, you have any T in S, we consider T mu at this center, you will see that the action of TT can be moved into the integral. Now we use the left translation invariant mean property of mu. We will see that C mu, the barycenter, is in fact the fixed point, common fixed point, or sub TT. Right? Yes, wonderful, right? But remember that we in general we do not know if mu is a probability measure or not. Usually it's not. It's unbounded measure. Okay, so we need some other technique. But the basic idea is here. So okay, if we have this, we want to just go through these pages with some technique. Okay, please go to the next pages. Yeah, please go on. Yeah. Okay, please. Okay. Yeah, thank you. So if C is a closed and convex subset of reflexive banana spaces, and S times C to C is the action of a this action is a Berman generalized hybrid or Berman on spreading, such that it has bound orbit. Okay, bound orbit is necessary, and then the map is non-continuous. Okay, and also the semigroup have a left translation invariant mean. Then the barycenter of this orbit will become a fixed point. Just as we imagine the case if mu is a probability measure. But here, mu is not probability measure. Mu is any arbitrary left translation invariant mean. Then we get this. In particular, mu S can be unbounded. Okay, please go on. Yeah, please. Yeah. Okay. A mean is called faithful if it is positive on non-zero positive on positive element. Okay. So if mu F equals 0 and mu is positive, then it might be 0. Okay. Now the result is this: if C is a co-convex subset of reflexive balance space, and the action is a Bergman left asymptotically non-expansive with a bound orbit, and also the action is non-continuous, and we have the conclusion, please. Yeah, please. Next one. Hi. I want the next page. Yeah, thank you. Yeah, then we have a common fixed point, and the common fixed point is the barycenter. Okay. I think I need to skip some of them. Otherwise, okay. Now the problem is, does the barycenter depend on the mean? Not quite so. Suppose that if we have two orbits, so we have a two barycenter. Maybe we have two mean. Okay, we have two mean. We have two barycenter. Then assume that the action is a Bergman left asymptotical non-expansive or Bergman generalized high bit or Bergman spreading satisfy some Dutch condition. We will see that no matter what mean you use, you have the same barycenter. Okay, so the barycenter basically depend on the action, not the mean. That's what we expect, because this is the fixed point of the action, right? It happened that if we have a mean, then we have the common fixed point to be the center of this orbit, right? But if you have a fixed point, no matter what mean we use, we have the same fixed point. Okay, so that is a reason why we have we have this result that the barycenter does not depend on the mean. Okay, please go on. Yeah, next page, please. Yeah, hi. Okay, please. Yeah. Okay, I think it's a very end. We can but sometimes we do not have a mean. The problem is okay, if you have a mean, you have the barycenter, but if you do not have the mean, then so what? Like okay, look at the example about the integer or the real line. The mean is defined by the cluster point of the local mean, right? We do not know how to write down the mean, but we have the local mean. Okay, there's the sum from minus n to n, and then we take the average of this, and then the local mean will have a cluster point, and the cluster point will be a mean. Okay, but we do not have the mean in hand. So what happens if we have only approximate left array mean? Okay, then we will see that we can use the left approximate mean, the approximate left invariant mean, to construct the barycenter, and then the barycenter will oppose to the barycenter of the mean. So we still get it done. So we can do it in the asymptotically approximation way. So even you do not have the mean, you only have the sequence or a net approximate mean, you can do this approximation. Okay, please next. I'm very sorry for this trouble. Yeah, I am. Yes, a very real experience to me. But I thank the colleague on your side to help me to finish this talk. I also appreciate to give me some few more minutes. Okay, this is a reference of this talk I would like to bring to your attention. MW123 are recent work of my student Dr. Moy and I. And I hope you can give us some comment and suggestion. Yeah, thank you very much.
Thank you, Professor Wong. You don't have the command on your slide, but you explained a really nice way. And you have explained the existence of the problems of the common fixed points of the non-expansive type mappings, particularly with the semi-groups. And you have explained also the Bergman distance. So I would like to ask from the participants for some comments.
Oh, by the way, I need to thank Dr. Sawu. In fact, I learned this Bergman distance concept from Dr. Sawu. So he teach me this. So he's my teacher. So if you have any question, you can also ask Dr. Sawu.
No, I don't have the correction, but if there are some comments from the audience, then we can definitely learn.
Sir?
Yes?
Yes, yes.
Sir, in the beginning, you have defined topology on the semi-groups. Then you have considered the topology to be Hausdorff. Then it is necessary to consider Hausdorff topology?
Well, usually, if we have a topological space which is not housed off, we can take the quotient space such that the quotient space is housed off. And all continuous function on the topological space will be isomorphic to the continuous function space on this quotient space. So in this way, you can always assume that a topological space is housed off for many questions. So if it is not, then you can replace it by its quotient space. The quotient space is housed off.
Okay, sir.
By the way, Professor Wong, I have seen that you have nicely handled the common fixed point problems for particularly continuous operators. So,
Yes.
We have some possibility. Is it possible to handle for the class of the pseudo-contractive type mappings? Because it is wider than the class of the non-expansive mappings. And you have also presented the things that the Brigman distance has nice property, the open condition. So what will be the possibility of the normal structure? So I have two remarks.
So you mean can we replace the continuity condition with some other condition, right?
Yeah, yeah.
Yeah, usually we can expect that the same result and the proof will work for lower semi-continuous function or upper semi-continuous function.
Okay.
Right? Because usually, for example, to apply the Ampere inequality, we are dealing with lim sup or lim yin, right? So in this case, the lower semi-continuity will be sufficient. Yeah. And another thing is about the non-expansiveness, right? Well, we are looking for some weaker condition.
Oh.
But for example, I skipped some slide. It's about the Roydam-Nikodym property of the space, and also we have something related to the geometry of the Banach space. But it's too difficult to present here. Maybe if you have time, you can look at our paper MW3. Yeah, I think it should be online very soon. Yeah, in this paper, we have some more condition which is weaker than the non-excellent. Yes. Yeah, I think I probably went out of time, right?
Okay. So, okay, thank you, Professor Wong, for your nice the talk.
Yeah, thank you. I'm sorry for this trouble. Yeah,
But
I'm
you
very
have
sorry.
presented in the nice way, and what Professor Ansari said that we again invite you, India. To
Yeah. Okay, next time I will present in person so that we don't have this kind of trouble.
Okay.
Okay, thank you very much. Thank you.
Okay.
Thank you, Professor Wong,
for
a very nice and innovative talk. And I'm sure that sometime you will be able to visit, maybe next year, when the pandemic is over.
Okay, thank you very much.
Yeah. Professor Khamsi, are you here, or probably it is night there? He might have gone to sleep. So, okay, thank you, Professor Sahu, for nicely sharing the session.
Okay.
I'm here, Islam. I'm here.
Okay, sir, because your another 55 slides are left. Without disturbing the whole schedule, I have already sent you a schedule, and if you can deliver your remaining slides, maybe on 23rd in the Indian time evening, but you are now in Saudi, that is in a place just we are 1.5 hour difference, I think, timing.
Okay.
So can you deliver around 6:15 p.m. on 23rd?
India time.
India time.
Yeah.
Okay, so that will be very nice, sir. we'll be grateful to you for having you and all the participants, also those who have attended today, they will also attend.
Okay. But please send me a reminder, please. But I will. Yeah, okay. I can finish talk. Yeah,
definitely.
Okay. No problem. No problem.
So I'm really thankful to the first session, all the speakers, all the chairpersons for these nice and talks. Now I will hand over the next session to Dr. D. Datta for having the plenary talk by Professor S. Chakraverty. Dr. D. Datta. Where is he gone? হ্যালো চেয়ার করার আছে তো Okay, he is joining. Just wait 1 minute. Yes, please. Yeah. Hello, Professor Ansari. I'm very happy that you are also here. Though you have another program tomorrow in your campus also. তাহলে অ্যালাউ করছে না আরে এটা তো
आप कर दीजिए ना सचियारसी
আমি শুরু করিয়ে দিচ্ছি हाँ just 1 minute. Just 1 minute, we'll start. Hello. না দেয়া আছে উনি ঢুকতে পারছেন না ডি দত্ত ঢুকতে পারছেন না কি ব্যাপার হয়েছে আমি দেখি আমি এটাকে শুরু করিয়ে দিচ্ছি মেঘাকে একটু বলে দাও তো কেন এরকম কেন হবে Megha, you allow Dr. D. Datta to enter. Hello?
Yes, sir.
The Datta is not able to enter.
We're not getting any notification
Not
from
able
his
to
side.
join.
We're not getting any notification from his side. Are we getting any notification? Sir, he has added as a guest. Sir, he has even added as a guest, so we don't need permission.
Hello?
नहीं ये नहीं होता तुम ट्रायल करोगे कैसे डी दत्ता के साथ कैसे करोगे
नहीं ट्रायल तो सब देते हैं ना
Subhi, sir.
बस लॉगिन
यस
Sir, please mute your mic.
अरे भाई तो ये तो अभी थोड़ी लेक्चर चल रहा है अभी तो ऐसे ही मजा ले लो
Just wait.
अरे मेगा ask
Yes.
Professor Wong to chair na why you are delaying
Yes, I'm
Yes,
going to share.
And sir, next lecture is of Professor D. Datta itself, so he has to join.
Anyway, announce कर दो, मैं chair कर देता हूँ.
So okay, thank you, Professor. Now I would like to request Professor Tanmay Som to chair the next speaker. Sorry for the inconvenience to all of you. Please, sir.
We have our next speaker, Professor Snehashish Chakraverty from NIT Rourkela. He is an expert in fuzzy modeling, fuzzy mathematical modeling.
So I have joined now.
Okay, please introduce the chair. Please
Okay,
introduce the speaker.
Okay. Biodata is with you or me?
No need of biodata, just
Because I know that, so I can just send that the Professor Snehashish Chakraverty is well-renowned mathematician in country as well as in the international area, and he has done a lot of work on the fuzzy mathematics, neural network, and many other branches of soft computing. The very important fact is that he was associated with BARC through a project, and for several times he has been visiting the BARC for demonstrating his work, and it was an excellent work which he had delivered in BARC, and that was the great association with him. And in a mathematical circle, I can say he is one kind of set theory of fuzzy mathematics and as well as soft computing person. Being a mathematician, going into that the work in the field of the computer is a really a you can say that it is a path transaction or that the direction of the path. So today I think he will deliver his keynote lecture, and I hope that all the participants as well as the faculties, those who are in the business of the fuzzy mathematics, they will be benefited. So with this short introduction, and I am very much sorry that his biodata is not with me. Otherwise, he has got a lot of award also, and I know that one of the award is that in the Science Congress he has achieved. And I think that there may be many more awards and a lot of publications. He is a reviewer of the many international journals. So with this short introduction in these August gatherings, I am handing over my mic to the Professor Snehashish Chakraverty to deliver his keynote lecture. Chakraverty sir, please.
Yes, first of all, very good morning to all of you, and thank you, the chair, Professor Datta, Devabrata Datta. And I am also thankful to the entire team of IIT BHU, in particular Professor Som, Professor Das, and other faculties, Professor Bhattacharya and all, whatever. And thanks for giving me opportunity to present my, whatever I am doing little bit, that I'm going to present now. So thanks to Professor Datta also, telling about me, although it is not needed the biodata in this. Nowadays, biodata is available everywhere. So anyway, Thanks for this. So, okay, let us then start the presentation. So, let me share my.
Of course, the biodata was mailed to Dr. Datta in his mail. It is there.
No problem, no problem, no problem, no need. Yeah, so let me share my entire screen first. So whether my screen can be seen?
Not yet, sir, not yet.
Yes, now?
No.
Not
Yes.
yet. Yes, it is coming,
Yes.
sir.
And now it is coming.
Yeah, okay. So anyway, without wasting further time, let me start my presentation. So this is the title that I have already communicated, although, and maybe the participants know, but anyway. So this is the Fuzzy-Affine arithmetic in overestimation problems. So, and the case studies will be of fuzzy system of equations I have written, but it will be, I will be discussing on linear system of equations. So main thing is that affine arithmetic that is recently actually has been proposed by some other authors, and we are using and proposing various methods. So a little bit about all those things and what is the connection between interval affine, affine interval, and fuzzy affine, etc. I will be discussing with very, very simple examples so that author or this audience can a little bit understand or have the it may ignite their minds to work on these areas. So with this, so these are the outlines of my lecture. So it is already introduction, then preliminaries, interval dependency problem that I will be discussing. That is the important thing when we are computing with intervals. Then affine arithmetic, then fuzzy affine forms, fuzzy affine arithmetic. I already told fuzzy system of linear equations, and then the proposed methodology, numerical examples, conclusion, and bibliography. So in mathematics, although everybody knows about the means use of these linear system of equations, there are various applications. Professor Datta already told about that. We had around one or two projects and where we have developed many linear system of equations with uncertainty, means uncertainty in case of interval and fuzzy. For actually in linear system, or if you take eigenvalue problem or differential equations, where actually we have different softwares, different methods to handle when those are actually in the crisp environment. That means the involved parameters or variables are considered in terms of deterministic or exact form. But practically, in practical sense, we have all these as uncertain. So these variables or parameters may be imprecise, incomplete, insufficient, or we may have vague information about the parameters because of several errors, etc. So, and even the initial conditions, boundary conditions may also be uncertain. So actually, traditionally, this uncertainty or vagueness, people handle by probabilistic approach. That is a very good approach, although. But for using this probabilistic or stochastic approach, we need a large number of data. So when your experimental procedure or the data that you are obtained are in small amount, then we may not have the PDF, etc. to use in the stochastic processes. So then when we have a small number of data, then one should go to the interval or fuzzy. So I'm not telling that always you should use this interval and fuzzy, but when you have large number of data, you must use this probabilistic approach. So so with this, here we will be using fuzzy numbers. So that also I will be explaining, although many few of the audiences know what are these fuzzy sets, fuzzy numbers. But for the sake of completeness, I'll just light up on these very fast. Okay. So fuzzy linear system of equations we present as this Ax is equal to B form. So if you see this Ax is equal to B, I have put tilde over those Ax, B. So that means those A elements of this matrix, A is a matrix, X is the column vector, B is right hand side vector. So here all these vector will have elements depending upon your system. Okay, number of unknowns or whatever. All these are in uncertain form. Uncertain form means I already told it will be either interval or fuzzy. So where this A tilde is fuzzy coefficient matrix that we call, and X tilde is the fuzzy solution vector, and B tilde are the fuzzy column vector. So, but because due to this interval fuzziness, it is not easy to find directly this X tilde fuzzy solution vector using your known method or the available softwares.
Sir, where is the uncertainty?
Here, this A tilde fuzzy coefficient matrix, here all the elements will be in terms of fuzzy number.
It is due to the nonlinearity or some other?
No, not nonlinearity. Suppose you are going to solve a electrical, that resistive network. So their current, voltage, etc. by Kirchhoff's law, you are going to write the equations. So when you are measuring, no, I'm telling. When you are generating those current or resistance or volt, so you are measuring. So when you are measuring, you will have some uncertain form of those data.
But that will be inbuilt.
Yeah, inbuilt means no. It depends upon who is doing the experiment. Okay. So then you all elements will be in an uncertain form, either in interval or fuzzy form. Okay. So that is why Ax equal to B may be in terms of uncertain form. So now dependency problem and overestimation problem. Usually interval and fuzzy analysis, we have done a project and there are several papers also published. So there we handle the uncertainty using interval and fuzzy computation. So these when we use this interval or fuzzy, we have seen that we are getting wide range of the solution. Means the interval range, width of the interval we are getting more. Actually, the solution should not be -infinity to +infinity or a large range. So how to reduce that? That is our aim here. So here just we will use this affine arithmetic so that we can reduce that width. Okay. And that range, wide range, is called the overestimation problem or the dependency problem due to the dependence of one parameter and onto the other parameter. So affine arithmetic is a self-validated numerical model that deals with the dependency problem in the case of the standard interval and fuzzy computation. I'm going to discuss on those things. So affine arithmetic based approach has been developed to handle fuzzy linear system of equations more efficiently. Okay. So just to have the practical problems, how it comes actually, again, I already told about the circuit. This is Ri equal to V. So there also we get the linear system of equations. And when it is structural vibration, okay, so this is ms double dot plus cs dot plus k is equal to ft. It is well-known vibration equation. And from their vibration equation, I can get eigenvalue problem if it is dynamic, and if it is static, then we may get this mx equal to f. So this is your linear system of equation, where this m is the mass matrix and x is the unknown vector is equal to, actually those are displacement, and is equal to f is the force, where m is the mass matrix and f is the external load vector. Okay. So, and when it is resistive circuit, so it will be forming. So there are many applications of this linear system, or depending upon nonlinearity, it will be nonlinear system of equations. So if it is nonlinear, then it will be more the complex computations we need to do. So with this fuzzy set, just for the sake of completeness, it is an ordered pair. If you see, we have two elements x and mu f. X is the element and mu f called its x membership, and this membership belongs to your 0, 1. So this is the beauty of this fuzzy set, that we can have the infinite number of points between 0 and 1. And if you see, this is a closed interval, so I have 0 and 1. So if it is fully true, so it is 1, and fully false, it is 0. And in between, we have different numbers, 0.1, 0.2, or 0.0, depending upon the user or the practical application. Now, after fuzzy set, this is fuzzy number definition. A fuzzy number, f bar, is defined as a special type of fuzzy set that obeys the following properties. So I'm not going to define each and everything here, because f, this normality, this convexity, this should be there. This fuzzy set should be normal. F bar fuzzy set should be convex, and this membership function mu f bar x should be piecewise continuous. So this is the definition of fuzzy number. So we have different types of fuzzy number. Actually, depending upon your application, one may use triangular fuzzy number, trapezoidal fuzzy number, then Gaussian fuzzy number. We have different types of fuzzy numbers. Okay. So this TFN, actually, if you see the figure 1, that is triangular fuzzy number, the shape is triangle, that is why its name is triangular fuzzy number. So this fuzzy number usually we define by 3 components, T1, T2, T3. If you see the figure, T1 is the left-hand side bound, and T3 is the rightmost, and T2 is the center, or at T2, if you see that this is the membership, y-axis is the membership degree. So at T2, the membership degree is 1, but at T1 and T3, the membership degrees are 0. So this figure or this function I can give like this. If you see, mu T bar x is equal to 0. So when it is T1 less than T1, and when it is greater than T3 is equal to 0, and similarly for other values, I have these two. Okay. So in this way, the triangular fuzzy number is defined. And this triangular fuzzy number I can have in interval form also, like it is called interval parametric form of the given TFN. So then I can write this triangular fuzzy number in terms of an interval. So if you see TA lower and TA upper, where A belongs to again 0 to 1. So that means that triangular fuzzy number I can define as a union of all these intervals, where these intervals can be written in terms of A like these intervals. Okay. So that means if you want to solve this TFN means when TFN is in the differential equation or the system of equation, then you need to use this interval form with a parameter A. So then you have to compute symbolically and find the solution, etc. Okay. So this is, I told that we have different types of fuzzy numbers. So this is another type of fuzzy number. This is trapezoidal. If you see, the shape is again a trapezoidal, where the function is given by like this. And this we actually denote by 4 elements, R1, R2, R3, R4. And this R2 and R3, the membership degree is 1. And at R1 and R4, I have 0, 0. And in between R1 and R2 and R3 and R4, I have these values. Okay. So this is the function. Again, in interval parametric form, I can write this in terms of interval using the parameter A, and then you play with this interval in your problem or the model. So 2 fuzzy number already I discussed. So there are others. I am not discussing all those. So in standard fuzzy arithmetic, so how to add, subtract, divide, etc. So if I have 2 fuzzy number F1 and F2 in terms of interval with the parameter A, I have already introduced. So now F1 star F1, this should be F2 actually. Okay. So F1 star F2 tilde. So this star may be addition, subtraction, or whatever. We write like this. Okay. Now addition, if you see, it is very simple. F1 tilde plus F2 tilde, just lower and upper. So the addition is simpler. But if you go to subtraction, so it is lower minus upper and the first element, that is left, and it is upper minus lower, that is subtraction. The scalar multiplication is given by this. Multiplication, again, I have different combinations of lower and upper. Then you take the minimum of that and maximum of that, put in the left and right. Division is also same, 1 by F2, and you can have lower and upper accordingly. But remember, this 2, 0 does not belong, should not be belongs to F2 lower, and minus infinity, infinity also. Here, it is the minus infinity when 0 belongs to F2 tilde. So these are just arithmetics. And then now I am coming to the interval dependency problems. So you see, standard interval arithmetic assumes that all the operands of a computation vary independently over their ranges while performing any interval operations. But we may not have every time these operands independent with each other. So that is the actually problem. In the cases when the operands are partially dependent, standard interval arithmetic overestimates the resulting interval solution into a comparatively wider interval than the exact range. So this situation is known as interval dependency problem or interval overestimation problem. So for several complex calculation and long iterative, when we are solving problem, we may use iterative methods also. Already we had actually developed those methods for interval computation and fuzzy computation. We have seen that there we get overestimation range of the solution, and it increases as the iteration proceeds. So for instance, you see the operation of subtraction. I have already defined the subtraction. In standard interval arithmetic, cannot assume that the 2 operands may denote the same ideal quantity, as there may be some cases where two independent operands may have the same range. Thus, the operation subtraction of standard interval arithmetic may cause an interval dependency problem, and this I will show you in the next slide what is happening. So you see this example. Let us take one interval x lower and x upper and subtract with itself x minus x. So what we are getting, as per the definition of the subtraction, lower minus upper and upper minus lower. So you are seeing that in real system, real number system, we are getting a minus a or x minus x is 0, but here we are not getting 0. So that is the problem actually. Here the width of the given interval x is x lower minus x upper, and the width of the resulting interval is c, it is doubled. 2 into x lower, x upper minus x lower. So this way we are overestimate. So this is just to show you what is the problem. Okay. So therefore the width of the resulting interval is twice the width of x instead of being 0. First of all, we don't get 0, but that too we are getting double the width. Okay. So the interval dependency problem is a major hurdle while handling uncertain real life problems, because we have many computations inside. So in this regard, affine arithmetic has been introduced to handle uncertain parameters efficiently. But again, there are also limitations in affine arithmetic. But we may get less small range, but there are problems also. So we'll see that. Okay. So now affine, what is affine arithmetic? So in 1993, Combine and Stoll introduced this affine arithmetic. So this affine arithmetic is a self-validated numerical models that records the range for each of the ideal quantity, and besides this, it also keeps track of first-order correlations between these quantities. So due to these additional information, the approximation error has been incurred in each operation of affine arithmetic, and affine arithmetic can overcome the extreme increment of the width of the, so whatever I have written here, so that I'm going to discuss in the next slide, that I will go to there, then I will discuss this. So now you see notations of the affine arithmetic. So this is actually represented by a linear polynomial of real variables. You see this x, which belongs to this one, x naught plus minus summation of this in the left, and summation of xi, minus of summation of xi in the left, and plus summation of xi in the right. So if I open this, so explicitly what is x? This is actually the x naught, one element, plus you have this summation. And remember, this epsilon I, actually for I equal to 1 to n, and these are called the noise symbols. These epsilons are called the noise symbols. And this x naught is called the center value. So now I will connect with this affine arithmetic with interval, then it will be more clear. Okay. And these noise symbols, remember, is lying between this interval -1 to 1. So that means these epsilon i's that I am introducing, those are noise symbols, and these are in -1 to 1. Okay. So you see the next slide, and this each associated coefficient xi that I have taken, x1, 1, 1, x1, epsilon 1, x2, epsilon 2, etc., of the respective noise symbols epsilon I is called the partial deviation of x tilde. So you see x naught was the center, and this xi, x1, x2, x3, these are all were respective noise symbols, is called the partial deviation of x. And this total deviation of x will be what? This dx is the summation of absolute values of all those partial deviations. Okay. So let us take one example, then it will be more clear how it is happening. Okay. So let x tilde, it is in affine form. So this is 57 plus 21 epsilon 1 minus epsilon 2 minus 4 epsilon 3 plus 10 epsilon 4. So I have how many noise symbols? 1, 2, 3, 4. So this is in affine form. So here this 57 is the center value in the affine form, and there exist 4 noise symbols which lie between -1 to 1. So in the affine representation, x tilde and associated partial deviations are what? Partial deviations I already told, those xi's. So this is 21, this is -1, this is -4 and 10. So these are the partial deviations. The total deviation, this is the total deviation. Total deviation is this. Dx is 36. Now, using this, I can write this in terms of interval form, that you know, that I will. So the partial deviation xi are finite real numbers. All the noise symbols of an affine form representation are unique, and independent to each other. In two different affine form representation, there makes it some common noise symbol or maybe different also, common or different. It depends upon the problem or the method. Now, new noise symbols may also be generated during the affine computation, because when you want to multiply, so there may be epsilon 1 into epsilon 2. So then you are getting a different noise symbol. Okay. So in this way, those computations will be more, but you will get the less smaller width. So now conversion of affine to interval. So till now I have discussed this, that this x tilde is given by this affine form. So now in interval form, if I have this x is equal to x lower and x upper, so lower bound of x I can write as x naught I know from here, this is the center, and dx I know, this summation of absolute value of x1 to xn. So x naught minus dx will be your x lower, and x naught plus dx will be your x upper, where dx I have already defined. So this is the total deviation already defined. So in this way, from affine I can write in terms of interval. Okay. So similarly, conversion of interval to affine I can write. So if I have an interval like this, so I can have the center, I can have the half width or the radius like this, and then I can have this as affine form. So in this way, I can have from affine to interval, and if interval to affine, actually for the validation, etc., we need this. So whether our solution method or solution is more or less correct or not. Okay. So then, now this is very important. Actually, this arithmetic is given by this Figueredo and Stolfi in 2004 and Iskalna in 2009. They have defined this addition, subtraction, and scalar multiplication. So in this way, so those I am not going to discuss. Okay, so these are given multiplication. This is very lengthy actually. We have different computations we need to do, and this is your division. Okay. So now take another example. Now, how to find a function? See, we have a function, nonlinear function. Okay, 2x square plus 5y square plus xy minus y. So where this is just an assumption that for all x belongs to 0 to 10 and for all y belongs to 3 to 8. Now this x, when it is 0 to 10, I can write this x tilde in terms of 5 plus 5 epsilon, and you know how to write this in affine form I already discussed. Okay, from interval to affine. Similarly, when this y is 3 to 8, so I know how to write in affine form. So now let us see the both cases, standard interval arithmetic operation and affine arithmetic operation. What is happening? So now you see this by standard interval arithmetics, putting all these xy values, these intervals 0, 10 and 3, 8. So what we are getting from standard interval arithmetic, I am getting this as the width. I mean, this is the interval, minus 143 to 517. Using affine arithmetic operation, using those subtraction, addition, or whatever. So what we are getting, this is the interval form that I am getting. So see the range, this width of this computation for this function, simple function, although nonlinear, this is reduced. Okay, although and it belongs to this belongs to here. You can see from here. Okay. Now, Fuzzy-Affine form, similarly, I can write. I have shown the connection between interval and affine. Now, with fuzzy, how we write? So we know that suppose I take TFN, triangular fuzzy number. So I have already discussed the triangular fuzzy number. I can write in terms of an interval using this A. Okay, this is actually parameter or alpha cut or A cut. So the above parametric form further may be transformed into affine form. So from interval I can write in affine form. Okay. So then this from affine form also I can write in terms of this interval form. So this way I can write these two. Okay. So using this I can handle the given problem. So Fuzzy-Affine form TRFN for triangular fuzzy number. Similarly I can write in terms of interval, and then I have the this TRAR and in terms of affine, and then this TRAR I can write in terms of like this. Okay, where A belongs to 0, 1, and these are noise symbols belongs to -1 to 1. Now Fuzzy-Affine arithmetic, how to add, subtract, etc. So this is the form I have taken. F tilde equal to F1 cap A epsilon 1, where is the parameter introduced in those fuzzy numbers. epsilon 1, suppose we have these noise symbols, and for F2 I have different noise symbols. I have told that I can have different noise symbols also. So using that, I can have this F1 cap star F2 cap. So star may be multiplication, subtraction, and all those. So in this way, I can have the arithmetic for these affine forms. And where you know that minimum and maximum I can take and have the left and right values. Okay. So there are bit calculations. I am skipping all those anyway. So let us take again the example this 4. So where fxy is given like this, 2x square plus 5y square minus 3xy minus x. Now you see earlier I had taken x tilde or the uncertainty as interval. Here I am taking the uncertainty as TFN, triangular fuzzy number. Now how to find those fxy? Okay. So now again x tilde a I can write, because this is in TFN, this is in TFN, I can write in with introducing the parameter a like this, here also introducing parameter y tilde a. So I can have in interval parametric form is by using the standard fuzzy arithmetic where we have the a parameter, I have this is the solution. Okay, you see interval solution, and put for different values of a you will get the fuzzy solution. Okay, so this is standard interval. Using interval parametric form, I have the fuzzy solution. Okay, now let us come to affine form of this. So in affine form, again this x cap and y cap I have written in terms of affine form. You see epsilon 1 and epsilon 2. Okay, so using this, that same function I have computed. Okay, so then we are getting this. This is the expression. This expression. Where you see I have epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 5. See, from the 2 noise symbols, I have got now 5 noise symbols. Why? Because I have different multiplication, means I have epsilon 1 square, I have epsilon 2 square, I have epsilon 1, epsilon 2. So that's why I have epsilon 3, epsilon 4, epsilon 5. So using this and those that arithmetics, I can have the solution or the for this minus 6. 264 and 51 189. Okay, the outer enclosure of the functional value of the fuzzy nonlinear function by using parametric fuzzy arithmetic and fuzzy affine arithmetic are. So this is the first one you see. This is from fuzzy arithmetic standard, and this is your from affine. You see the width here, it is reduced 51 to 189, and by standard this is minus 6 to 264. Okay. So we have plotted this to see in more clear form. So if you see this one, this is fuzzy parametric fuzzy, fuzzy affine arithmetic. So you see 52, that 151 or whatever. So this is the range you are getting for using fuzzy affine, and parametric fuzzy arithmetic you are getting this from year to year. So outside that, so range is reduced. So this is the for different a for the fuzzy solution, we have just computed lower and upper values. Okay, lower and upper bounds. This is just to show you clearly in terms of pictorial form and tabular form. Now let us take another example where I have taken TRFN. You see TRFN. So I have 4 elements. So this is the now a linear, just an example linear function I have taken, and using your standard fuzzy arithmetic, I have this is the solution. Okay, this one. In terms of a, which is the interval, which may be converted to again TRFN for a and for different a's. So but in the fuzzy affine arithmetic, you see here it is epsilon 1, epsilon 2, epsilon 3 I have got. Okay, so where this again belongs to -1 to 1, this is the affine form, and then I can put it here in fxyz, means the function, and I can have the solution for these 2 functions. So this is the solution. I have not given all those digital values. So if you see fuzzy affine arithmetic gives this range, and the standard fuzzy arithmetic, this gives this range. Okay. Okay, now come to, so this idea now we will use in the fuzzy system of linear equations. Although this can be used in other type of system of equations, maybe eigenvalue problem or this. Actually, eigenvalue also we have solved. I'm not presenting here. So anyway, so I have taken now Ax is equal to B form, where it is already I told that A tilde is the fuzzy coefficient matrix, X tilde This is your fuzzy solution. In the first or second slide, I already told. And B tilde is the fuzzy column vector. But this A tilde, now somebody was telling. So this is the A tilde coefficient matrix. A11 tilde, A12 tilde, A1P tilde. Similarly, A21 tilde, A22 tilde, A2P tilde. So this is P by P matrix. Okay, this A tilde. Okay, this A tilde is a P by P matrix, and X tilde I have X1, X2 up to XP tilde. Okay, and right hand side I have B1, B2, B2 tilde, and up to BP tilde. So I have now the uncertain system, and this uncertain system, these elements A11 tilde or A12 tilde may be given as interval, may be given as fuzzy form, means fuzzy numbers, maybe TFN, TRFN, Gaussian fuzzy number, whatever. So using those now techniques, the BPS techniques, now we can convert this to affine form or interval form, and then we can solve and compare the results. Okay. So let us see. So proposed methodology. So here you see I have written AX is equal to B, simple form. So this is your coefficient matrix A tilde, and this is your right hand side vector, right? So now, because if these are in TFN or TRFN, so introducing that A means that parameter A, I can convert into interval form. So that is why here, if you see this A tilde A in equation 5, I have written in terms of interval all the elements. Similarly, B tilde, I have written in terms of interval all the elements. And again, A cap, I can write, this is for using fuzzy or interval computation we can do, because fuzzy, why? Because A is there, that parameter. Now,
excuse me, sir.
Yeah.
You are in the lecture you have confined yourself in the solving non-linear equations, linear equations.
Yeah.
Only linear, not
only linear. Okay. Till now, actually, we have solved non-linear also. I am not presenting. Okay, non-linear also we have solved. Yeah. Here I am just actually non-linear function I have shown you. Anyway, one function. Anyway, so now this is A tilde, that is fuzzy form. Affine form, fuzzy affine form. So here you see I have these symbols there. Okay, this noise symbols. So right hand side vector also will have. So same procedure, whatever I saw shown you with very simple example, linear and non-linear functions for different fuzzy numbers and in affine form. Same procedures are extended here. So here AM, etc. I can write BM, etc. I can write in terms of these noise symbols, and then finally I can have this the system where you see fuzzy affine system. Okay, and this can be solved very easily. Okay, because in symbolic form I can solve, and I can have the fuzzy affine form of the solution. Okay, so I'll similarly this I'm not going to. There are many calculations because I have to have left and right. There are okay. So just I'm skipping. So I will go to the numerical example. Okay. So let us take a simple 2 by 2 to make you understand. See A tilde, I have TRFNs. Okay. So I have 4 elements here. Similarly, the first element, second element, first row, second column, again 4, here 4, here 4. Okay. And right hand side vector also having 4 elements. So these are TRFN, triangular trapezoidal fuzzy number. So from TRFN, in fuzzy affine arithmetic, using those methods that your center and width, I can write in terms of affine form. Epsilon 1, this is in epsilon 2, this is in epsilon 3, epsilon 4, and B also, B tilde rather. So I have epsilon 5, epsilon 6. Then I can handle this using this system A tilde AX equal to B, and after doing all those computation I already told. And for different A means your that parameter that is introduced in the fuzzy from TRFN to interval. Okay, so using this I have this solution. So this is fuzzy solution plot for x1 tilde, fuzzy solution, and this is for x1. This is for x1, and this is for x2. Okay, so this is for fuzzy solution bounds, lower and upper bounds as you get you put different values of A. Okay. So this is your leftmost, this is your rightmost. So these are the values of x1 and x2 that you are going to get. Okay. Now coming to example 7, that is a 3 by 3 fuzzy system of linear equations. Again, same procedure. I have taken here TFN, that is triangular fuzzy number. Same procedure. I'm not repeating all those. So these are the solutions for your x1 tilde, x2 tilde, and x3 tilde in TFN form. Okay. So with this, I will now conclude that Fuzzy-Affine arithmetic is developed here actually to overcome the overestimation problems. So again, there are some limitations I already told due to that multiplication and division. Okay, actually there are many computations there, but okay, we can write the program and we can have those. But Fuzzy-Affine arithmetic is found to be better enclosures than the standard fuzzy arithmetic, whatever examples we have taken. But we need to again simulate many problems, and really we have to see that whether yes it is giving. But whatever problems till now we have done, and yes, theoretical proofs also we need to do. Yes, the Fuzzy-Affine based approach has been proposed for computing the solution of fuzzy linear system of equations having uncertain and non-probabilistic model parameter in the form of different fuzzy numbers, and several numerical examples are proposed, solved. And powerfulness and efficiency of these methods are shown by comparing with your traditional fuzzy and interval arithmetic. I just see I've written, though affine arithmetic is more complex than classical interval arithmetic, but it yields better and tighter enclosures of the solutions. Hence, affine arithmetic is a good compromise between complexity and reliability. Okay. Yes, so these are some papers that we have followed. So anyway, so thank you. I hope I could ignite your mind a little bit in this direction. And yes, there are many challenges here. Means if you have some parameter as probabilistic, some parameters as fuzzy, and how to combine using this fuzzy, this affine, those are the challenges, and we are doing slowly. So anyway, these are whatever we have done till now. So thank you very much. So if you have any simple question, or okay, so
I think that it is a nice lecture by Professor Snehashish Chakraverty, and it is a complete. I think that for the participants, those who are working in the direction of the fuzzy affinity part is maybe that the new to you. In fact, it is new to me also.
Yeah.
So I could understand that the main contribution of the affinity is to reduce the uncertainty. But there may be many questions from the participants. 1 or 2 questions I may allow. So participants, including the faculties also, those who are interested to put the questions to Snehashish Chakraverty, they can raise their questions.
But simple questions, because complicated hard questions Anyway, if anybody wants to discuss later also they can discuss.
Later also they can discuss.
Yeah, you can ask. Yeah, some doubts, some queries, something. Yeah.
Sir, where is the uncertainty you have told?
I already told, I have already taken in the examples that interval. Suppose I want to, can you see me?
Sir, can you come to slide number 41? Then
no, just I am explaining. See, this I want to measure. This I want to measure, maybe 9 centimeters. So you can say, no, sir, it is 9.1. So Professor Som may say, no, it is 8.9. So Professor Datta can tell, no, it is 9.01. So how many answers you are getting? So which one to take? So then I can write this length as from closed interval 8.9 to 9.1.
Okay,
So
you are considering the uncertainty in different way. Okay, it's okay.
Yeah, because you are thinking about probabilistic uncertainty. That is why
it is a probabilistic uncertainty.
Yeah, I told initially that probabilistic. If you have more number of data, you should use probabilistic.
Yeah, so that is not the system's uncertainty. Another thing is that sir, you are considering the 2 by 2 matrix, correct? No? For validation of the method, you have considered 2 by 2.
No, just to show you, we have taken higher.
No. That I'm saying.
Okay.
If you increase since it was interesting, that's why, sir.
No problem. You are always welcome.
If you consider the higher order matrix, I think result will be more better.
More
better. I think.
Better means what sense? Actually, again in uncertainty, that Professor Datta knows.
Probabilistic uncertainty.
Yeah. So
generally, my feeling is that.
What about the stochastic nature?
Of what?
Suppose you are considering the system in one place, and if I consider in other place,
No, that is why I told that
irrespective of place and irrespective of time.
No, that is why I told that it is a challenge how to combine this probabilistic uncertainty with interval or fuzzy uncertainty. Till now, means few people have done, but you may be asking this is how to combine this. Suppose one parameter is fuzzy and another parameter is probabilistic.
You are saying that this interval, fuzzy interval, what you are considering, is it related to the confidence interval? You want to
No. You can play with all those things also, but here we are not taking like that. I told you that suppose differential equation, simple dy by dx is equal to y. I have the differential in the first order, with subject to y0 is equal to 1. Okay, so now y0 equal to 1. Practical application, you may not have that y0 is equal to particular exact value 1. You may have that 0.9 to 1.1. Suppose I take the corona case, how many are infected? Again, this is an interval. One cannot have, because we may have mistake in the measuring or whatever. Again, those are in terms of interval or fuzzy. Okay, that maybe the 1000 to 1000 to maybe 1000 to 1100. So there you are taking an interval. That okay, understood?
Okay.
So those uncertainties.
Okay. I think other participants should. I should give them opportunity.
Okay, yeah. Thank you for your doubts. Yeah.
From the desk of participants, you people should ask the questions as a because author is in front of you, so you can ask a lot of questions. But definitely you can, because of the time constraint, that the questions can be put back into his desktop by emailing and all these things.
Yeah, always.
So,
sir, can you come to slide number 41?
Slide number
41. Yeah, 41. Let me see. I have 1 minute. 41, no?
41.
41. Yes. Yeah. Yeah.
So here you have the matrix A, that is your A tilde. Now the value, these are the coefficient.
Yeah.
The value say A11 or A12, they lie between with A and say with that what is called vibration or whatever.
Yes.
Okay. So this is going this is giving the flexibility that how much this variable can
yes.
take.
Oh, you are telling about uncertainty. Yeah.
And therefore, that uncertainty is going to play an important role in
then
finally getting a solution.
Even in B also.
So for every coefficient. Okay. So suppose you are getting a solution. So that solution is actually for which value that we cannot say, I think.
Which value means?
Means for which coefficient, because for a particular coefficient I have one solution, particular set of, it is not the coefficient which is changing and then we are getting a solution.
No. Suppose 1 minute, there is a confusion. 1 minute. This, suppose I remove this tilde. Okay, I have the exact values of this. That means constant values. I have no upper, no lower. I have A11, A12, A1P.
So this is a linear system of equations and you are getting a solution.
Yeah, I am getting a solution. So this solution should lie, whatever solution I will get this by this using this interval. Understood?
So in this case, we are getting a solution lying between. Okay.
Yes,
that will be the thing.
Yes.
Yes.
That is the validation actually.
Yeah.
The solution should lie. Yeah.
That's fine. So this is linear case. If it is non-linear, what?
Non-linear also there are methods we have developed actually, because non-linear is little bit tricky because they are so we have to actually have linearizing and getting the solution. And actually see, we had just started this, so there are many challenges. Non-linear also we have solved, but I will not tell that is the last or whatever. Means we need to do more. Yes, we have solved non-linear. We have solved eigenvalue problem. Non-linear eigenvalue problem also we have solved. Okay, using this method.
Good, fine, sir. Please.
So it is very good presentation. I think that now my responsibility is to hand over the responsibility to the organizer for starting the next session. And at the same time, I would like to give a thank to the organizer to give me an opportunity for chairing this Snehashish Chakraverty's keynote lecture session.
Thank you.
Thank you very much.
Thank you. Thank you.
Thank you, Dr. Datto. Now I invite Professor S. Chakraverty to chair the talk of Dr. Didat.
Okay. So thank you again to the organizer. But again, I didn't know that again he has sent, but I could not download the CV of Professor Datta.
Doesn't matter because
But
we
again,
are the Cooper pair.
again, I know, and organizers also, most of them knows, but the audience also may know. He was a very senior scientist in BRC, Atomic Research Center, Mumbai. So I am also surprising that after retirement also he is doing research more than us. So he is means seeing different fields and all. I have seen his lectures in several places, that he is still active, and we hope that he will be active from for the coming years also. And he has worked with me, as he had already told. Good collaboration we are having, where I am in NIT and he was in BRC. He wrote good number of papers, then book chapters, and also organized training courses, conferences, etc. He was the head of that division, physics division, no?
Radiological physics and advisory
division. So anyway, he is again renowned scientist throughout India and also world. So anyway, so with this small introduction, I will now invite Professor Datta to present his talk.
Okay. First of all, good afternoon to everybody. And once more, thanks to the Professor Snehashish Chakraverty, now as a chairman of this session. And at the same time, I would like to thank the organizer to give me an opportunity. And I will try to put a new topic. Maybe that the people have done a lot of things, but to me it is a new, and maybe that the audience also will like it. So before going to that, let me share my screen. So is it visible now? Just to respond to the
Yeah, it's coming. Yeah.
It is coming. No?
Yeah.
Okay,
Yeah,
so I can go from here. So this is the way that I would like to present my talk. The title of the talk is the optimization methods using music-inspired algorithm and its comparison with nature-inspired algorithm. As the title of the conference is the optimization technique included, then I thought that many people, they do the optimizations by a lot of method. So why not that there is some social behavior which is nature inspired, and some musical instrument behavior which is a music inspired can be brought back into this optimization technique. So my presentations will be based on these guidelines, that we will introduce the optimization, though people know that what is optimization. And I would like to point it out that as far as optimization is concerned, there are two sets. One is the deterministic and another one is the stochastic. Then we will jump to the music inspired algorithm, where we will mention that the harmony search. We have just heard music by radio or mobile or many area, but we do not know what is inside into that. I will try to bring some little bit of extent, because there is a very complicated field. Then nature inspired optimization algorithm like bat algorithm, the behavior of the bat, and then bee colony, and then we will conclude that. But I will bring that a lot of applications, then you will know that how we can do. Fine. So let us start with this, that what is optimization, though people know, but we would like to say that for the sake of again completeness, that optimization is a procedure to make a system or design as effective, especially the mathematical techniques involved, where we introduce a meta-heuristics consideration. Because it is soft computing, whenever we try to do the soft computing or any other computations with the artificial intelligence, you require to have the heuristics, but sometimes heuristics are very, very complicated and having a lot of ambiguity. in order to overcome that, we would like to bring the meta heuristics. So in the field of optimizations, our aim is basically to find the best solution. Now this has a very ambiguous answer, that best solution means what? It may be a minimal cost where the design consideration will be there. It may be a minimal error where some parameters, if they are calibrated. Maximal profit is a management oriented problem, and maximal utility, it is an economics oriented problem. So in the all field, this optimization is present where it will address the best solution in a different format. Now, if you look at this particular slide, the total optimization is categorized into these different tasks. If it is objective, maybe having single objective optimization or multi-objective optimization. If it is a constraint-based optimization, you may have unconstrained or constrained. If you have a landscape-based optimization, you may have a unimodal, which is called as a convex optimization, or multimodal. Same way, if it is a functional form, you may have a linear and non-linear. In the non-linear mode, you have a quadratic and many other area. If it is a variable and response-based optimization, you may have this category. And if you have a determinacy, then you have a deterministic, all these above, as well as stochastic. Then from every part of the optimization, it is guided by some kind of algorithm, which is known as an optimization algorithm. So classification of the optimization algorithms are there. If the optimization is deterministic, then algorithm will be definitely deterministic. In that case, you have a linear programming, non-linear programming, maybe the gradient based and gradient free. And if it is a stochastic optimization, then the algorithms corresponding to that is known as the heuristics or meta heuristics. What we are interested in meta heuristics, and meta heuristics optimization, which is basically stochastic in nature, and they are population based as well as the trajectory based. So having this concept, let us just have a brief note about the heuristic. What is heuristic basically? It is basically a computational procedure which will determine an optimal solution by iteratively trying to improve some candidate solution. So basically, you are proposing some kind of hypothesis, and by the computational procedure and some other physical laws, you are going changing your direction. So that is the heuristics. But many of the time, it is a biased. So we try to have some unbiased solution, where again that the uncertainty we try to reduce. So in that case, we try to bring the meta heuristics. So in the case of the meta heuristics is nothing but some other heuristics which will be around that actual main hypothesis, which is based on the heuristics. So meta heuristics can address both discrete and continuous domain optimization problem. We have the strategies that guide the search process, and it has got a huge range. One of the meta heuristics is nothing but the hill climbing, in the sense that if you go to the trekking, how do you climb the hill? What kind of mental order or disorderness is going on in your brain and cognition task? So that is nothing but your meta heuristics. At every step, you are taking the decisions with respect to some little bit of uncertainty, ambiguity. So that kind of, and you are going to success also. So there itself, we are applying the meta heuristics. Now, in the case of the classical optimization algorithms, it has got some drawback. Drawback is that I'm not discouraging, but there are some lot of drawbacks, like mathematical algorithm, simplex algorithm. If I take the BFGS, which is the NLP, natural language processing, and data processing, so everywhere some kind of drawback is there, and drawback is due to the hypothesis depending on the solution towards the problem. Then we also have a drawbacks of mathematical algorithms, which I mentioned here. What is that? If you take a linear programming, it will be too idle. Many times, nonlinear solution is available in practice. There, I cannot apply this linear programming. It is a too complicated task. Same for the natural language processing or nonlinear programming, NLP, where they may not be discrete or many other conditions are there. If you take the DP, which is the exhaustive enumeration, and some kind of wrong direction it guides. So therefore, in order to have the drawback, we have to think about some optimization algorithm, which may be the nature-based as well as social-based. Okay, so the existing meta-heuristic algorithm from that angle, these are the existing meta-heuristic. Swarm intelligence, everybody knows, where particles swarm. Taboo search, which is an animal's brain basically. Simulated annealing is a metal annealing. Genetic algorithm, which is an evolutionary algorithm. You may have the ant algorithm, artificial, and so on. So therefore, every such meta-heuristic algorithm, what is our task? We are trying to draw the mimicking behavior of the natural phenomena. So one of the mimicking behavior is the music performance, which is known as a named as a harmony search. Okay, so let us just discuss about the music inspired algorithm. It is nothing but when you go to the orchestra, if you see that there are many instruments are playing, and before that they are trying some rehearsal. What they do, they try to harmonize that one particular instrument pitch to the other particular instrument. The player who is playing the guitar, he is trying to make the harmony with the harmonium, and the harmonium fellow will be trying to make the accordion or any other musical instrument like tabla, setar, if it is there. So ultimately, music inspired algorithm is trying to generate an optimal harmony, and when the harmony will be set, that will be the best music which you will be hearing. So that is the basic idea of the music inspired algorithm. So the background is that each one of these, that's why sets of values is called a harmony. And during this optimization process, we require to have a number of harmonies which will be equal to the harmony memory size. That will be stored in the harmony memory. You have to generate the harmony memory, which will be a database, and this database will include for the set of solutions production. Then this algorithm will be end when the predefined total number of iterations has been achieved. Okay. Now, if you look at that, whenever you try to implement this music-inspired algorithm, we have some music side, we have this kind of variable, and in the mathematical, when we try to convert, so that's why mapping I have given. If you have a musical instrument, that means you are having a decision variable. For any musical, you have a pitch range, which will be a value range in this mathematical domain. When you have a harmony in the music, you have a solution vector. If you have a aesthetics in the music, you have an objective function. If you have a practice in the musical side, you have the iteration. And when you have an experience in the musical domain, which has a memory matrix. So that means a musical space is transformed into a mathematical space by transforming this or analogical corresponding variable. So the algorithm of the harmony search is that you prepare a harmony memory, then you improvise a new harmony with experience, that is your harmony memory size and some randomness. Then if the new harmony is better, include it in the harmony memory. And then you repeat the step from 1 to up to 2 until the goal is achieved. So this is the algorithm of harmony search. And then for every algorithm to be implemented, you require some mathematical techniques. Here in this harmony search, mathematical techniques are known as operators. So operators are nothing but the random playing, memory considering, pitch adjusting, ensemble considering, and dissonance considering. Now you see that the dissonance is nothing but the one kind of uncertainty. When you are trying to reduce that by doing the meta heuristics, so you are getting the harmony. So that means again inbuilt in this case, uncertainty is involved, and this uncertainty is stochastic uncertainty because it is a randomly playing here. So I will try to apply the harmony search in this kind of function. This is a sphere function, and you are seeing that when you apply that implementation in this spherical functions, this is a sphere function, single objective. So you are getting the optimal value of the decision variables, say 2.0, 2.0, and 3. Because I have taken the 3 dimensions. So I equal to 1 to 3 for every part you are getting. So that means this is nothing but your center. And with the help of that, when you try to put that, the optimal solution, you are getting this, and the figure showing here this. So this is your optimal solution you are getting here.
Sir, one thing is that you're saying that uncertainty, stochastic uncertainty, which is very, very hard to control.
Yes, yes.
How you are still using the algorithm, you will get the stable solution.
Yeah, because what happened when you are doing that, it is a meta heuristics, and meta heuristics time to time you are changing, and since you are repeating for a large number of times, because uncertainty in this domain cannot be reduced, cannot be eliminated. In the probabilistic uncertainty, it is known as the aleatory uncertainty.
But again, at the same time, you have to take care of unbiasedness, correct?
Unbiasedness also. So that is why when you see that in many cases, when musical instruments are just played with a harmony, but because of the speaker, which is giving some harm, at the same time, locally we may say that their harmony is getting damaged. Again, they are asking that the monitor fellow, "Arey Baba, you try to adjust the monitor, we are not getting." So that means uncertainty is there in the many musical instruments. So when you are trying to repeat again and again, not one rehearsal, 2, 3, 4. So automatically it is coming that way, minimal solution. There may be also uncertainty, but that uncertainty can be neglected or maybe not significant with respect to that problem domain. That's all.
Okay.
So again, we are trying to apply a benchmark function, which is a Rosenberg function. Rosenberg function is defined by this mathematics. Okay, we are trying to optimize this function. Pictorially, I have shown it here by taking the minimum of this function, which is a 0, and the search domain is given from this domain minus 2.048 to 2.048. And we are repeating here, you see that for 30 times to get your minimum and number of local minima, you may have several local minima here. Okay, if I open this function, you see that there are several local. And the iteration is coming down this. So when you are applying the harmonic search for this function, we got the optimal decision variable x1 is 9.55, 10 to minus 1, and x2 is a 9.13. And with the help of that, when you submit back into this, so we got the best estimate of the function. Okay, so the harmonic search with the help of two mathematics is giving me a optimal solution. So this flavors me that it may be a good algorithm for doing some more complicated task or more practical. So again, when you do the one algorithm, it should be validated with another algorithm, whether this algorithm is better or new algorithm is better. So that way we are trying to compare the nature-inspired algorithm. And as you know, the nature always is an optimizer. We try to adjust because you can see that our human body is a nature and which is an optimizer. You cannot take any amount of food in your body because body will reject whenever it will be optimized. So similarly, birds has a minimized drag. If you take the humpback whale, which is a maximized maneuverability, and then if you take a box fish, minimize the drag and maximize the rigidity of exoskeleton. Kingfisher, if you do, they minimize micro pressure waves. So these are the naturally available, and every object has got the minimization and maximization problem inbuilt. So therefore, we can take the chance of the nature-inspired algorithm, which are basically in the domain natural evolution, search and optimization, hill climbing, as I mentioned, which is a gradient descent, local search, population-based algorithm. It may have an advantage and disadvantage also with respect to the evolutionary algorithm. And then we can do a lot of material and resources. When you try to book how optimally that the book can be written, how optimally that the questions can be answered, all these things can be understood not by simple mathematics, but by applying the natural inspired algorithm. 2-3 applications I will show you. So what nature-inspired algorithm computation is, means what kind of computation? Basically, it is a pattern recognition. So it gives a pattern, and that pattern, when it is optimized, that itself is a solution. Therefore, I mentioned that the nature-inspired computation results a pattern recognition problem. So whenever we have a pattern recognition technique, we can always take the route of this nature-inspired algorithm. Problem-solving techniques based on how the social behavior of the systems can operate, and also we can take the problem-solving techniques based on the natural swarm behavior. Basically, it is a biological orientation we can take. Okay, so that means whenever nature-inspired computation we will try to do, we have to apply the social behavior of the system, naturally available or biological oriented system. So this is one BAT algorithm, which is a nature inspired algorithm. That means the way that the BAT behaves, it is basically a nature inspired algorithm. So BAT algorithm is proposed as a bio-inspired meta-heuristics method for solving hard optimization tasks, and it also tries to mimic the behavior of the bats which are hunting for their prey. Okay, so bat always trying to hunt for their prey. In that case, bat is basically predator and prey is nothing but their food. So these are the pseudo code of the BAT algorithm. I'm not going to the detail because it has to be implemented in a programming format. Nowadays, children are very smart, so they can immediately convert into a Python code and they may be implemented also. When you try to apply that algorithm, you see that again for the Rosenberg function using the BAT algorithm as a comparison, we are taking the various dimension of the function that D I had shown. If it is a 10, mean value for the 10 number of iterations, we got this result. For 20 dimension, we got this result. That is for the sphere function, and for the Rosenberg function, we got that result. And if you compare for the 3, you will see that the BAT algorithm based value is slightly disturbed from the harmony search. That means here that the computation is slightly complicated compared to that. So computationally, this may not be that efficient with respect to a complicated function. So similarly, in the swarm-based optimization algorithm will be there, where anti-colony one can apply genetic algorithm. Already people have a lot of applications they have done. So we are trying to bring also the bees algorithm, the behavior of the bees with instead of BAT. So bees algorithm here, bees are again in nature. They are basically trying to search the flower patches or pollens of from the flower, and with respect to that, they are the food of that. So that how they are behaving to, or how they are foraging the food, that is nothing but the proposed bees algorithm. So bees algorithm is basically an optimization algorithm. People short in called the BA, and that is inspired by the natural foraging behavior. Foraging behavior means they try to, all the bees are going to the flower to seek their food, to search their food. How their foraging behavior, that is an optimization process, and therefore their behavior we can apply to find the optimal solution. So this particular figure I have mentioned there, but figure I have purposeful because figure means always that lot of problem it will be there because it is giving that lot of animation. Then only that. So instead of that, we try to put here algorithm. So you initialize the population with random solutions. You evaluate the fitness of the population, and while stopping the criteria which is not met, then you generate the new population. Select the sites for neighborhood search. You recruit the bees for the selected sites, and then you select the fittest bee from each batch and assign remaining bees to the search randomly. Then you evaluate the fitness. That means ultimately you are trying to get the optimal solution with respect to a fitness function. And fitness function may be the single objective, maybe multi-objective. That is why this nature-inspired algorithm, including the harmony search, can be applied for multi-objective optimization technique also. So this is the proposed bees algorithm. See, you are giving some parameter, number of scout bees, you can take 100. Number of sites selected, you can take out of n bees, that is say 10. You can select the number of base suite. These are your parameter choice. You can vary that. And with respect to that, you will, when you go for when you implemented the algorithm, so how many repetition steps or which other uncertainty will be bring, that you can always give in as your choice, and then you see whether it is a conversion or not. If it is that, then you may require the change of the parameter. So these are your writing the algorithm. You initialize the population, evaluate the fitness of the population, you select how many sites for the neighborhood search, you determine the size of the neighborhood, then you recruit the bees for the selected site, you select the fittest bee, and then you assign the n minus m remaining, how many bees are remaining, and then you go for the new population. The same thing you go on repeat till your convergence exists. So therefore, you can go for this this kind of situation, and now we'll see that all these things are bringing into this animation mode. So then we are trying to show first some of the applications in the harmony search, because this is newly developed for many applications. And you see that our internet routing can be achieved by the harmony search algorithm. That means how to connect which one. When you try to give a search in the Google, the way it is searching in the web is basically harmony search. So if you can understand, we can develop our dashboard for data repository or the data bank can be followed by the harmony search, because searching may be the optimal. Otherwise, you may have the two answers for one question. Then similarly, harmony search we can apply for the truss structure design, because this is very important for civil engineering people. They always try to have the truss structure. So instead of doing their physical laws or the finite element technique, of course, finite element technique will be there, but how to put which beam to where, so that can be done by the harmony search. And when you do for the either genetic algorithm or harmony search, you see that the harmony search gives the optimal solution 484.85, whereas the genetic algorithm gives the 543. That means the harmony search is a better solution corresponding to the genetic algorithm. And what is the solution means? Solution means that the how many nodes and which center point that the structure will be there, so that the system will not be collapsed. It will be in the equilibrium mode. Then again, you see that a large scale network, water network design, which is very, very essential, can be done. So all these things can be connected to a mathematical function where a huge number of variables will be there, which is nothing but the 454 pipes here for doing this problem. And the genetic algorithm, it will give the costing of that 2.3 million euro, whereas harmony search will give the 1.9, because it's a management problem. So the cost is involved. So now you see, we will definitely try to apply the harmony search because the cost is much lower than this. Okay. Second is the hydrologic parameter calibration. Hydrologic parameter calibration is governed by this equation, which is a nonlinear equation. So we try to the sum of the square error by objective and then estimated objective. That is the target and then. So this is one channel we try to optimize. So same problem we put into the harmony search algorithm, and we got the mathematically, if I try to do by linear programming, we got that the 143.60. Genetic algorithm, it is giving 38.23, whereas harmony search algorithm is giving 36.78. So harmony search algorithm is much better compared to these two optimization technique. Again, another interesting point is that recently the WHO is always connected to me for doing a lot of work on the COVID. So you try to find it out that can genome sequencing be applied by harmony search, including the graph theory. So graph-based optimization technique, if we try to do, harmony search give the RNA structure prediction. And it has been very recently done. And in doing that structure, we can easily find it out, the variant of the COVID virus, which is recently a Omicron. We are trying to find it out, what could be the structure of this is the structure of the RNA simply, where you see that the A for adenine, C for cytosine, uracil, and guanine. So how nicely that RNA structure can be graphically generated by the harmony search. So this structure prediction can be varying depending on their combination, which is a genome sequencing that we are trying to do at present to understand that the can graph be applied for doing this one. Okay. So let us see that another application, which is a harmony search in the field of radiation oncology. This is very often we do because in hospital, it is really required. So this is the various kind of beam, and when you try to take the image, we will get the optimal image into this form. Okay, we will explain this thing in the next slide. So our idea is that we wanted to do the cancer treatment using the radiation therapy. One possible way to treat the cancer is that you are looking the external beam. Treatment machine, that is a CT machine or MRI, is used to pass radiation through the patient's body. Damages both cancerous and healthy tissues because of the heat involved in the radiation. Typically, multiple beams of different dose strengths are always applied. So we have to decide what kind of beam dose strengths you are required to achieve that your damage of the tumor. Now here you see this is my tumor. I have to apply a beam from this direction. I have to apply a beam from this direction, so that what is the necessity? That volume of the tumor I have to understand. To understand the volume of the tumor, these three beams are equal. And once you understand the volume, then I can apply easily how much of dose I can deliver to damage the tissue. So we have to have an area, healthy anatomy. For the beam 1, it is a 0.4. For beam 2, it is a 0.5. And there are some restrictions which have to do the restrictions, nothing but the minimize the average dose. Then if it is a critical tissue, beam 1 will give the 0.3, the dose value, and beam 2 will give the 0.1. Dose value means the gray, 0.3 gray and 0.1 gray. So this minimal should be the restriction 2.7. Tumor region, you have to give the beam 1 0.5 and beam 2 0.5, and that has to be equal to the 6. Center of the tumor, these are the beams should be applied. So these are the general data for that machine involved for the beam 1 and beam 2. So the decision variables here, that the x1 and x2 represent the dose strengths for the beam 1 and beam 2. Having that, we can govern that equation. Minimize this equation, 0.4 x1 plus 0.52. It is a dose to the healthy anatomy. Subject to these are the constants. This is the dose to the critical tissue. This is the dose to the tumor and dose to the tumor center. Then when this consideration we apply by harmony search, we got the solution that optimal solution for the decision variable x1 is 7.5 and x2 is 4.5. And this, when we apply in this equation, we got that the radiation dose to the healthy anatomy should be 5.25 gray. So this was not known by many doctors, many radiation oncologists. So when we try to give that, even in Tata Memorial Hospital, they are applying this technique now because of this behavior. So optimization technique can play a role through this music inspired algorithm. Another problem is that the air pollution problem. Here you see steel plant has been ordered to reduce its emission of 3 pollutants: particulates, sulfur dioxides, and hydrocarbon. Plant uses 2 furnaces. Plant is considering 3 methods for achieving pollution reduction. One is taller smokestacks, filters, and better fuels. So 3 methods are expensive. So the plant managers decide to have minimize the cost and at the same time achieve the required emission reduction. With respect to that, various data we can segregate from the plant for the pollutant, particulates, sulfur dioxides, hydrocarbon. These are the required emission, million pounds per year. And then emission reduction is given here. Pollutant F1 for the taller, filters, and better fuels. Particulates is given here. Sulfur dioxide, these are the various data we given. So annual cost of the complying method, implying a method, then if it is a method applied taller, you get that the F1 is 8 and F2 is 10. Filters, it is a F1 7 and 6. For better fuels, you have 11 and 9. So when you go for then decision variables is nothing but here. F1 is the x1, F2 is the x2. For filters, it is x3, and for F2, it is the x4, and for better fuels, it is x5 and x6. So these are my decision variables depending on this data. Now what we'll do, we'll try to construct the situation, this governing equation, which have to be minimized, because this is the equation which will give me the total cost, subject to the constants which I've shown for with respect to the data. So these are my constants, and these constants are nothing but the emission reduction, which will requirement for the cost reduction. So this total system we apply in the harmony search, and harmony search will give me the optimal solution. And here you see that the optimal solution for the decision variables it gave. And with respect to that, when you submit into that, we got that the cost is the $32.16 million. So therefore, for any plant, depending on its emission and production, we can optimize by using the harmony search. So another is the function optimization, because here we try to apply now B's algorithm. So this is my function. B's algorithm I have already mentioned previously. We apply the can B algorithm be applied. So now you see that the D algorithm, when we apply, we got the solution x0 and y0, and current best estimates also for this solution will give that. So therefore, B's algorithm also function optimization technique we can apply. We try to put that the more complicated function is the Gaussian function, and Gaussian function is taken into this format. This is the 4 Gaussian function summation. So when you apply into the B's algorithm, so we got the best estimate there. That means B's algorithm can do, but computational load is much more compared to the harmonic search. Another is that the harmonic search is gradient free. So we'll try to apply the optimization which is gradient free, because when you take a gradient, you have a direction.
What is the need, sir? What is the need of considering the Gaussian?
No, actually here what happened, I am trying to find it out that simple Gaussian function is a nonlinear, but when you have a many more Gaussian function, because if you have a many more data cannot be scaled by a single scale. So for a certain domain of the data, it may be one Gaussian. For another certain domain of data, you may be another. So that is why we are trying to.
If we consider that these are all the random variables are independent.
Yes.
We have no problem.
Yes. We are independent, because when you have a normally random independent variable, we can add that. If it is not, then you have to give the correlated variables also here. Okay. So with that, we can apply the B's algorithm and can initially optimize. So this process can be applied in any physical process where lot of stochasticity will be present there. We can apply the
even you can add the T distribution. There will be no problem.
Yes, we can apply, and not only that. Another beautiful point is that nowadays
long tail is there. Long tail
is there. Variable distribution, maybe that the Poisson driven variable distribution can be optimized.
Having long tail.
Having long tail, that we do not know, and many of the financial part, you know that the long tail is there, which we do not know.
So because you are working with the big data.
Yes, big data. When you have to have a big data, and recently I got a system from, basically I will say that the contract from the Delhi to have the air pollution, because they do not know, they are having a lot of sensors, but many of the time, the sensors are damaging, that they do not know. Sensors are damaging due to the humidity. So they wanted to know that what is the remediation process for the air quality at Delhi. So that's why they have sent the data. So like that only, these 2-3 jobs I am involved, so to do that the contribution.
So I think one interruption here.
Yes.
Dr. Datta, can you conclude, because our paper presentation is due just now.
It is concluding now. You are having a lot of applications further which are not required to here, but just name itself is sufficient. And then you have some kind of any algorithm, some advantage and disadvantage. Advantage I mentioned here is the efficient overcoming. Disadvantage are there. Huge number of tunable parameters are required to deal with that. And then I'm really concluding. We discuss optimizations, which is a music-inspired harmony algorithm and nature-inspired. We compared both the optimization, and we understood that the music-inspired optimization can do a much better compared to the existing algorithm. And then nature-inspired also can be put back into the back end of the music-inspired to expedite the system. So music-inspired based harmonic search innovates a new optimization algorithm. And one new technique I would like to announce that recently I have received a project from ICNAAO, which is based on music-inspired harmonic search. Okay. So with respect to that, a big thank you to the organizer again to give me an opportunity to explore my this innovations music-inspired algorithm. And recently, ICNAAO has accepted this project for optimizing the COVID process with respect to our Indian data by harmony search. Thank you.
Thank you, Professor Datta, for your exciting presentation. It was very nice. So as per the information from organizers, we are actually being late. So questions, if you have, you can write directly to Professor Datta. If the audience have any question, or in the chat box you can write, he can reply later or whatever. So with this, let us conclude the session for this Professor Datta's presentation. And thanks very much to the organizer for again giving opportunity to become the chairman of this session. Thank you all. So Professor Datta, thanks again for your presentation. Nice presentation. Thank you all.
Thank you, sir. Thank you.
हाँ, पेपर प्रेजेंटेशन अब शुरू होगा प्लीज. हाँ, आप शेयर करेंगे, है ना?
So Professor Som, now you
Yes,
can continue.
thank you very
Now-
much. Thank you, Professor Chakraverty, for nicely chairing the session, and also Dr. Datta for a very nice and elaborating talk, talking about that particular harmonizer, and that particular module is very nice. I think applicable in many areas, in multiple areas. Now I request Dr. D. Gopal of GGSU to chair the session for the paper presentation on the area of fixed point theory. Dr. D. Gopal.
Thank you very much, sir. First of all, very good afternoon to all of you. And I must say that the conference is now started very well. It is indeed, we hope that it will continuously continue with our expectation, more than that. So here,
Excuse me,
I would
sir.
like, yeah, please.
Sir, it would be great if you will switch on your mic, switch on your video also.
Okay.
Thank you, sir. Thank you, sir.
So may I call to the first presentation? The name is Biswas. The surname is Biswas, actually.
Yes, sir. I'm present.
Yeah, Jayanta. Yeah. Okay. So the time is about around 8 minutes to 10 minutes for your presentation.
Thank you.
No, I think the presentation time will be around 12 minutes and total 15 minutes they can finish.
Yeah, fine, sir. Yeah. So now all of the participants in this particular session who are going to present, the time now is consider the particular time, 12 minutes to 15 minutes. 12 minutes is per presentation, 2 to 3 minutes is per discussion. So
Thank
please
you,
proceed.
Okay.
Yeah, please.
Is it visible, sir?
Yes, but little bit you can zoom it, then it will be very fine.
Okay. Now it has been zoomed.
Yeah, fine.
Okay.
Please proceed.
So, good afternoon, everybody. Myself, Jayanta Vishwas, prepared this paper together with Himanshu Pandey, who is his next speaker of another paper. Here, the title of the paper is a generalized rational type fixed point theorem in I-generalized metric spaces. The concept of I-generalized metric spaces is a new one introduced by myself and my sir, Dr. Somil Suman. Here, a new fixed point theorem under more general rational type contraction conditions has been established in generalized metric spaces first, and then establish an analogous version of this theorem in the frame of the newly introduced concept of I-generalized metric spaces. The concept of I-metric spaces has been introduced by myself, given in this reference list at number 12, and gave fixed point results using different types of contraction and mappings. And it is very well known to us that in 2000, Branciari introduced generalized metric spaces. In short, it is called GMS for generalized metric spaces, replacing triangular inequality by rectangular inequality, and subsequently we know that several fixed point results have been developed in this context. In 12, which is my paper together with my sir Dr. Sunil Suman, the concept of I-metric space has been introduced, and some generalized fixed point results for various contractive type of mappings in the context of I-metric spaces are presented there. In 11, the concept of I-generalized metric spaces has been introduced by myself and my sir Dr. Sunil Suman, and some general fixed point theory results for various contractive type mappings in the context of I-generalized metric spaces are presented there. Ahmed J established the existence and uniqueness of fixed point for a rational type contractive mappings in GMS, that is generalized metric space, short form of that, which is a generalization of rational type fixed point theorem in metric spaces established by Khan. And Khan's paper is very old paper. And Ahmed's result is given here, stated in this form. So XD is complete GMS and A is a self map of X, satisfying these contractions, where E, F, G, Is are given here. E is D of X, X, F, G are given, and A, B are non-negative fractions, together with the condition that A plus B is less than 1. Then he proved that A has a unique fixed point in X. That was the result of Ahmed J. Professor Tiwari and Pandey, given in 13, established a fixed point theorem using the more general rational type contraction conditions, which is an extension of the fixed point results of Olantino, given in 10, in the context of two metric spaces. And the statement of the result of Professor Tiwari is given here. And first part is rational type, and it is a kind of general rational type expression. And he added some more terms, B into this plus C into this, and so on, under these constants on the real constants A, B, C, E, P, Q, mu, nu, which are positive real constant, together with this condition. And then he proved that A has a unique fixed point. Here we shall generalize both the contractions of Ahmed J's result and Professor Tiwari's results by means of rational expression of some control functions. And I will see that here I have introduced 12 control functions and established new fixed point theorems in the context of GMS, and then establish an analogous version of this theorem in the context of the newly introduced concept of IGNS. So firstly, we shall consider these newly introduced preliminaries introduced by myself in 12 and in 11. So it is the generalization of uniqueness of 2 points or 2 elements of a non-empty set called I-uniqueness. So X is non-empty set, F is a self-idempotent map of X. 2 elements of X and Y are said to be I-unique with respect to F if Fx equal to Fy. Otherwise, X and Y are called I-distinct elements. So come to this concept of I-generalized metric space introduced by myself in 11. So X is non-empty set and F is an idempotent self-map of X. A map D from X cross X to 0 infinity is called an I-generalized metric on X if only if it satisfies these 3 postulates. For all xy belongs to X, D of X Fy equal to 0 if only if Fx equal to Fy, that is X and Y are I-unique points, and D of Fxy equal to 0 if and only if Fx equal to Fy. Condition 2, D of X Fy equal to D of Yfx and D of Fxy equal to D of Fyx. And this is the last condition. For all xy belongs to X and for all I distinct points UV, which each of which is I distinct from X and Y, these rectangular type inequalities hold. D of xy less or equal to D of Fxu plus D of Fuv plus D of Vfy. And the order triple XDF is called I-generalized metric space, in short, IGMS. And this is an example of IGMS given here. Let us take the concept of Cauchy sequence in IGMS. So a sequence Xn in an IGMS XDF is said to be I-Cauchy sequence if for any given epsilon positive quantity there exists a positive integer n naught, or D of Fxm xn less than epsilon for all mn greater or equal to n naught, and this is another form of the condition. Sorry, there is another definition. Sorry, yes, this one. Convergence, concept of convergence of sequence in IGMS. So a sequence Xn in IGMS XDF is said to I converge to a point X if for any given positive quantity epsilon, we have a positive integer m, such that d of fxn x less than epsilon for all n greater or equal to m. So this is the concept of convergence, and this was Kaohsiung, I have told, and obviously this is the concept of completeness, complete IGMS. So an IGMS XDF is said to be I complete if every I Kaohsiung sequence in X I converges to some point. Okay, otherwise XDF will be called I incomplete. So this is the concept of that is generalized concept of fixed point called I fixed point. I have introduced in 11. Let X be non-empty set and F is an idempotent self map of X. A map which is self map of obviously is from X to X is said to have an I fixed point X if fh of X equal to fx. And this is an obvious result, comes from the definition of IGMS. Let XDF be an IGMS, then d of xx becomes 0 for all x. D of x fy will be equal to d of fxy equal to d of fxfy equal to d of fyfx, and each of them greater or equal to d of xy as well as d of yx for all xy. And d of x fx becomes 0 for all x. And this is my first result of this paper. Let phi and phi I varies from 1 to 11, that is 11 plus 1. There are 12 functions we have considered here, from 0 infinity to 0 infinity. And T is a self map of a complete GMS XD, which satisfies these 6 conditions. 1, phi I, all are continuous on R plus. Phi t becomes 0 if and only t equal to 0, and phi I t equal to 0 if and only t equal to 0. And such types of functions are also called phi functions. We may call it as phi functions. But here, there is an exception in condition 2. Phi I becomes 0 for t equal to 0, except for phi 4. I equal to 1 to 3, 4 is skipped. Okay, that is not required here. So I have skipped that. Phi 4t need not satisfy this condition. And condition 3 is the actual contraction condition. Okay, rational type contraction conditions. For any given positive real number p, for all xy belongs to x, or phi of d tx ty less or equal to this rational type of expressions. And here 7 control functions are there. P plus phi 1 of this plus into phi 2 of this into phi 3 of this into phi 4 of this by this. And I have taken some more additional terms by means of phi 8, phi 9, phi 10 and phi 11.
Please try to conclude it.
Yeah. And number 4, it is a very crucial and typical restrictions here. For all T1, T2 belongs to R plus, phi T1 less than minus phi 10 T1 less or equal to phi 8 T2 plus phi 9 T2 implies T1 less or equal to Q T2. For all proper positive fractions Q, for some fixed proper positive fractions Q, and phi 10 less than phi 8 plus phi 11 less than phi, then T will have a unique fixed point in X. And let us keep this note. It is my realization at the proving of the theorem. And this is the analogous version of the last theorem in IGNS. The conditions 1, 2, 4, 5, 6 are same, and the contraction conditions is generalized here. Just there is difference between condition 3 and of both the theorems. Okay. And then our conclusion is that then T has an I unique I fixed point in X. So, okay, further study may be continued, and these are my references. Actually, I have generalized the result of Ahmed J given in 1 and of result given in 13, Professor Theory. Okay, thank you all. Any question?
Yeah, please. Anyone, if you have any discussion for one to 2 minutes.
I have one question.
Yeah.
So, is there any applications of these fixed point in fractals?
That need study and trying. Okay. I may try or you may try. No problem. That may be. But I have not thought till now.
Dear Biswas.
Yeah.
I have one just, I mean, a point. Just wanted to know if it is possible. The rational expression, how it is different. If we try to establish the fixed point theorem, how you got it motivated, or from where you got motivation for a rational expression, please.
Yeah, actually, rational expression. Actually, let us come back to the history. To Banach, it was just a linear type of inequalities. Then Carnot's and so on. Many types of inequalities are that is contraction conditions was linear type of inequalities. I think that rational type of inequalities are non-linear. Okay. So these are the motivation, and time to time generalization or weakening the rational type of contraction conditions is needed for broad type of applications. That is my motivations, and instead of come back to the theory's result. Look at this.
Okay,
result.
okay. Anyway, it's fine. It's fine. Actually, if we recall that the complex valued metric, although there are something more on it.
Yeah.
So there is the idea which work well. We take the rational expression. Anyway, thank you very much.
Okay. Okay.
Thanks. So I hope. Is it completed? If anyone else.
May I stop sharing?
Yeah, please.
Okay, thank you.
Now, please, next one is going to present is Himanshu. Please, you can proceed for your presentation.
Okay, sorry, my microphone was muted. Is my screen visible to all, sir? Good. Hello.
Yes.
Yeah, it is visible. Yeah.
Good afternoon, sir. Himanshu here from University Department of Mathematics, Magad University campus. Sir, one of the also topic on fixed point, which is also in a rational contraction in B2 metric space. In a B2 metric space, this is actually some restriction with on a 2 metric space on the definitions of in a triangle inequality of 2 metric spaces. Fixed point theorem under rational contraction in B2 metric space. Sorry, my screen is not working. Just a minute, sir. Okay.
Himanshu, just zoom it.
Okay, sir, my screen is not working. I am trying to.
Okay, you can go ahead with it. This one, no problem.
Sorry, sir, my screen is not working yet. Yes. My screen is hanging right now, not responding. Sorry for inconvenience. Please wait. Hello, sir. Hello.
Yeah.
Can I resume our presentation? Can you continue? I want to just chapter 1 because my screen is not working properly. So I wish.
Okay, no problem. You need some time, then we'll call the other person who is
yes,
going
yes.
to present.
Yes, sir. Okay. I am checking my laptop. So thank you, sir.
Okay. So please next be prepare yourself and then Archana.
Yes,
Archana
I want to continue. My topic is fixed point theorem in rational contraction in B2 metric space. And first, I shall describe something about the abstract of my paper. I am generalizing in this paper of BARC, stabilized fixed point theorem and new types of rational contracting mapping. In this paper, we have extended the BARC type contracting mapping in B2 metric space in more general form. Actually, BARC type contraction is the generalization of Fisher, and in this paper, I have joined the work of BARC as well as Fisher into more generalized form in B2 metric space. So this is the introduction. The Banach contraction principle has the number of generalization and extension using the various types of contracting mapping in our generalized metric space. One of the such generalization is rational contraction over by Das and Gupta introduced the new types of contraction principle as follows. For d of tx dy is the first times of this. This is the rational contraction for a metric space xd. Further generalize and extend the above rational inequality as follows. D of sx dy is less than equal to b of dtx dy square, and this where the denominator part should be not equal to 0. There is a restriction over the bc greater than 0 and b plus c is less than 1. If one of the s or t is continuous, then we have get there a common fixed point. After that, in 2009, Vatsa proved the following into two metric space. But in our result in B2 metric space, let PQ STR4 map self map on a complete metric space to itself, the satisfying the following conditions. If they satisfy this, we get a the pair should be SP and TQ with compatibles map or the common fixed point in X. Later on 2001, he extended the above idea as the rational contractively condition as follows. For 4 map also, with one of the any one of the pairs should be continuous, and pair SP are semi-compatible and TQ are weakly compatible on X. After these restrictions, we have established the unique fixed point theorems. Unique fixed point theorem for this. Recently, Mustafa introduced the concept of two metric space. This is the small change in the definition of two metric space by triangle inequality, and this is the simple. In this paper, we have extended the result of Fisher and Vatsa into B2 metric space for two map and self map with generalized parameters. We have some preliminaries to recall. For proof this theorem, we need frequently in this paper. Mustafa introduced the notion of two metric space, B2 metric space. This is a generalization of both two metric and B metric space. For a pair of distinct point x, y, there exists a point in the dx, y, z is not equal to 0 and dx, y, z is equal to 0 if at least any of two of them points are constants. And this is the symmetricity property, and all the possible permutations of x, y, and z are equal in the metric over the metric D. And last one, the triangle equality. This is the D of x, y, z is less than equal to S of D. This is the for all x, y, z, D belongs to x. Then if we put S is equal to 1, then this definition is nothing. This is the only definition of two metric spaces. B2 metric space reduces to two metric space. This some topological study in B2 metric space is also here the definition of convergent, B2 convergent, B2 Cauchy sequence, B2 complete sequence. And this is one of the examples by B2 metric space. And let XD and X dash D dash B2 mapping, B2 metric spaces, and Fx to X dash be a mapping. Then F is said to be B2 continuous at a point Z belongs to S. If for a given epsilon greater than 0, there exists a delta greater than 0 such that for a small x belongs to X, then D of X, XA is less than del for all A belongs to X, imply that this. So this mapping F is B2 continuous or not, if it is a B2 continuous at all point of X. Primarily is continuous. Let XD and X dash D dash B2 metric spaces, then a mapping Fx to X dash be B2 continuous at a point of X, if and only if B2 sequentially continuous at X. That is, whenever Xn is B2 convergent to X, then F of Xn is B2 convergent to X. One of also definitions is here B2 metric space, and this is a mapping, and this is the if unique point of coincidence, then U is called a coincidence point of F of G. Self map F and G are said to be weakly compatible. This is the definition of weakly compatible. Commute with at a coincidence point. If they commute at their coincidence point, that is, if Fx is equal to Gx for some x belongs to X, then Fgx is equal to G of X. And this is the definition of compatible mappings on a B2 metric space for a map F and G, self map F and G, and a metric space B2 metric space over XD, then satisfy limit tending to infinity D of Fgxn, G of Xn A is equal to 0 whenever Xn is a sequence in X such that limit of F of Xn is equal to limit of G of Xn is equal to X for some X in X. Now we have some lemma about B2 in the context of B2 metric space. In this paper we have used here 1 of S square is less than equal to limit of infimum of this. This is supremum of this. This is less than equal to Fs square of this. In particular, if yn is equal to y is constant, then this reduces to this. After one of the also, this is the theorem established by me here. Then F1 and F2 have unique point of coincidence with the help of our previous definitions. This is our main result in a B2 metric space. Here we generalize the result of our main work is here. Generalize the result of Fisher and Warza in a B2 metric space. This is a for 2 map. Let S and T be 2 self mapping of a complete B2 metric space XD, such that D of Sxtya, this is less than equal to alpha times of this, D of Sxa cube, and this square terms, and this is the square terms by the single linear terms, and restriction is this, and should be then S and T have a unique common fixed point. In a proof, first we consider let arbitrary point X, and this is the system in a sequence, and we may assume that X of 2n is not equal to F. First we shall show that D of X to n plus 1, X to n plus 1 barabar 0, using our above contraction, rational contraction mapping. Then we here see proof, we have so that to D of 2xn, 2xn plus 1, 2xn 2xn plus 2 is equal to 0. Now our next procedure to see to prove that this is a Cauchy sequence.
Himanshu,
Yeah.
can you conclude it?
Okay, ma'am. So this is a after I will prove this is a Cauchy sequence. Now we show that this is a Cauchy sequence by the definition And so xn is a Cauchy sequence. By taking the two sequence xn and x2n plus 1 and x2n plus 1 2. For generalization in this way, since x is a complete, then there exists a point. So every xn is a Cauchy sequence. Since x is complete, this is our statement. Then there exists a point z in x such that limit of n tending to infinity xn is equal to z. Now so that this z will be the common fixed point of our both of map S and T. Now again using with the help of our rational contraction, here with some restrictions we stabilize the Sz is equal to z. Similarly, we can prove the z is a fixed point of T also. So this z will be the common fixed point of S and T. Now our further procedure to see here the uniqueness, z is the unique common fixed point of X and T. Again with the help of this contraction, here we stabilize. Let us assume the W is the another fixed point of, if possible, to W is the another common fixed point of S and T. But this W is nothing. This is exactly equal to Z is equal to W. So we can say that Z is the unique common fixed point of both of the map S and T. We have some corollaries with claim related to our theorems. This is for single maps, and this is for another double map. And also analogy for B2 metric space. This is also corollary. This is a Fisher result. Fisher result was only this on B2 metric space, but our result is more generalized than the Fisher result. Extension of our previous result for 4 maps. Our previous main result was 2 maps. Now I am going to prove for 4 maps for A, B, S, and T. And this is with also some restrictions here. A and T have a coincidence point, B and S have a coincidence point, and any one of the pairs should be continuous. Then we say that A, B, S, and T have not only common but unique fixed point in X. Proof is almost same as previous. First we shall show that there is a sequence of the with relation d of dx to n plus 1 to n plus 2 is equal to 0. Now our further work on Cauchy sequence. After that, limit can be extended up to a common fixed point, and this proof is already same as the previous. Our contribution of our result is if we put beta is equal to gamma is equal to 0 in the previous theorem, we get Fisher, and the beta is equal to 0, we get the result of Paso. And this is the analogy of Banach's contraction theorems in B2 metric space. And this is the references. This is the main difference with this is the Paso and one of the Fisher's results. So 1 and 6 are main, and this is the Das and Gupta result. This is which is BARC on rational contraction mapping, and this is the. So thank you.
Yeah, now is rightly this slide. Any questions? So please, anyone who wishes to have a question or comments or suggestions, please.
I have one question.
Yes.
Is there any application of this common fixed point?
There is lot of application. This is not. I am not working on application currently, but I am seeing the application part like the digital on the digital metric space, on the graphical metric space. But currently, my work in on the theorem and stabilizing a fixed point on either a B2 metric space, complex value metric space, 2 metric space, also in a S metric space. And,
okay. Okay, thank you.
Yeah, any more question and comments? Okay, so thank you, Himanshu, for your presentation.
Okay, thank you, sir.
Okay. Archana Yadav, are you ready now? Archana?
Can I stop my presentation?
Yeah, please.
Okay, thank you. Thank you, everyone.
Archana Yadav. Are you here?
I think no, I could not see her here in this link.
I think she's not here.
Yeah. So now may I call to the next one? Someone is Vatanjit Singh. Are you
Yes,
there?
sir. Yes, sir. Good afternoon, sir.
Yeah. Very good afternoon. Please proceed for your talk.
Sure, sir. Sure. Sir, is my screen visible to you?
Not now. Now is going to be visible.
Okay, sir. So good afternoon, everyone. I am Vatanjit Singh, working as a junior research fellow at Thapar Institute of Engineering and Technology under Dr. Sumit Chando. So I am going to present my...
Vatanjit,
Yes,
you
sir.
have 12 to 14 minute time.
Sure, sir.
Just try to be with that and use proper this time. No need to hurry. Please.
Okay, sir.
Continue.
Thank you, sir. So my topic, title is Gornicki-Proinov type contractions in asymmetric spaces. And first of all, I will define asymmetric spaces. So asymmetric spaces were introduced by Sedghi in 2012, and these are non-continuous spaces. And if we consider any x to be a non-empty set, then if we consider its mapping from x cubed to 0 to infinity, we say that it is an asymmetric space if these two conditions hold, which is ABC for a equal to b is equal to c, the asymmetric is 0, and here is an inequality which is visible on the screen. Then we say that a pair S of x and S is called asymmetric space. Now this asymmetric space is not continuous like the metric space, and we will discuss the Gornicki-Proinov type of contractions on these asymmetric spaces. So here is an example of asymmetric space. If we consider x to be 0, 1 close interval and define asymmetric space to be S of A, B, C is equal to 0 whenever A and B is equal to B is equal to C, and maximum of A, B, C otherwise, then we say that the pair x and x is asymmetric space. Here are some preliminaries. This lemma will be used in proving the further results. If we consider A&N to be an asymmetric, if A&N to be a sequence in asymmetric space, and if this sequence is not Escauchy, but it is asymptotic regular, which is limit n tends to infinity, S of AN, and AN plus 1 is 0, then we can say there exists an epsilon greater than 0, such that for any two subsequence, these four conditions hold, which will be helpful in proving the results, mainly the contradictory part of the Cauchy sequence. Okay. And we define the alpha orbital admissible mapping. And if we consider any x to be non-empty set, then self-mapping T from x to x is called alpha orbital admissible. If alpha of TU, U and TU is greater than or equal to 1 implies that alpha of TU and T square U is greater than or equal to 1. Here alpha is a mapping from x cross x to 0 to infinity. Okay. Now, similarly, we can define triangular alpha orbital mappings, which is alpha orbital mappings with an additional condition, that is alpha of UV greater than or equal to 1 and alpha of VTV greater than or equal to 1 implies that alpha of U and TV is greater than or equal to 1 for all UV in X. Now, here is a lemma which will be used in the proving the main results of this presentation, which is if for any triangular alpha orbital mapping, which is self-mapped from X to X, if there exists any A naught in X such that alpha of A naught and TA naught is greater than or equal to 1, then we can say that alpha of AN and AP is greater than or equal to 1 for all integers N and P. Now here is our main results. So Karpiner introduced the Gornicki-Proinov type contraction in metric spaces, and we are generalizing this results in asymmetric spaces. So asymmetric spaces are not continuous. So in this structure, we are considering x and y to be same, so that we can apply the lemma proved by Sedghi, which is limit n tends to infinity S of A and B and is equal to S of A and B, where A's and B's are the limits of A and B and sequences. So the Gornicki-Proinov type contraction, here we introduce the Gornicki-Proinov type contraction as an example. Here is the first main theorem. Let X to be a complete asymmetric space and T to be a self-map on X. We say that this self-mapping has a fixed point, which is with respect to Gornicki-Proinov type contraction, which is this alpha of UV, and psi and phi functions are introduced, where psi and phi functions are from 0 to infinity to reals. And we consider this asymmetric as positive inside the psi and phi functions. And if it satisfies these 5 properties, which are phi t is less than psi t, and these 4 additional properties, we say that T has a fixed point. Now, here we are considering T to be orbitally continuous. We also can consider it to be P continuous. And Now here is one more example, a theorem, which is slightly generalization of the Gornicki point of type contraction. Here we consider the alpha mapping under the psi function, sorry. And if we say that this mapping is, or we are already considering this mapping to be asymptotic regular, so that we can help, it will help us to prove the contradictory part of the Cauchy sequence, which is helpful in the theorem. And these are same results. Then no conditions are changed, but please note that there is a condition 2. We are approaching from t going from epsilon positive to epsilon positive, which is very much important. If we consider it to be t going from epsilon, there will be a lot of contradictions according from the example point of view. Here are some example to prove our valid our results. If we consider x to be a closed interval 0 to 1 and define the S metric to be 0 if A is equal to B is equal to C, maximum of A, B, C otherwise, then we say that the X of S is a complete S-metric space. Okay. Now, if we consider phi and phi function to be 2t and t, then clearly t is less than 2t and first conditions are also satisfied. Since these are continuous functions, all the conditions of the lower semi-continuous t are already satisfied, and we define the self-mapping to be x t from x to x by t of x is equal to x by 2, and we choose the alpha mapping to be uv alpha of u v is equal to 2. Then we say that t has a fixed point x is equal to 0 with respect to Gornicki point of type contraction. And similarly, here is one more example. It is not little bit not trivial. If we consider psi t is equal to e of t, and the metric is S-metric is same in this example also, and psi of t is equal to e of t and phi of t is equal to t plus 1, then we say that the self-mapping t from going from x to x, which is t of x is equal to log of ex plus 1, has a fixed point at x is equal to 0 if we consider alpha to be 1. Yes. Here are some references from where have we taken the. So we have generalized the results of Karpinar, and the S-metric was introduced by Sedgi. So these are the 2 references. Thank you. And any questions, please? You can ask any questions if you have.
Yeah, I have one question.
Yes, sir.
Being new to this field,
yes,
I don't see any physical meaning of your S-metric. I don't see.
Yes, sir. This is a very good question. The physical significance to finding these metrics are very much difficult, but we can't say that there is no physical significance.
No, physical. If you see metric yes, shows you something. And if we work in Euclidean space, we can see some physical meaning.
Yeah, I agree with that.
So, is there any similar type of physical interpretation of S-metric or not?
Like, if you have you ever worked in fractional differential equations?
No.
So there are a lot of results of S-metric in fractional differential equations published by HK and Ashin. You can study those results. And I think that these are not generalization of line. Like metric is a generalization of distance, like distance between 2 points. Okay.
Yes.
At G, and these 3-point structures are generalizations of sometimes parameter, area, and different things, depending upon how we want our structures to be defined. Okay.
Okay.
So there are a lot of applications. There are a lot of applications in the differential equations. Also, I'm thinking to work in like in the physics side of these applications in the physics portion.
Okay.
So there are a lot of applications. It's just that it's not very much. Motivations are not very much there. So we need to find the motivation point, these metrics, why they are introduced and what they represent. Since S-metrics is not continuous, so it is quite challenging to introduce the topologies in this matrix. Okay, sir.
Okay. So the example which you were showing, something as maximum of A, comma B, comma C.
Yes, this is all a very common example.
Physical meaning of this or?
Physical meaning, what do you mean by physical meaning? Can you explain?
Any something, can we visualize this as in some sense?
Okay, sir. So first of all, this is in x cube. So it is if we consider it to be like r, we can visualize it in like r cube.
Yes.
Yes, here it is x from 0 to 1. So it is very small structure. We can consider any point and it will be a singleton point. That okay. So distance as A and B and C, we say that it is A or B or C. Okay.
Yes.
So
I have one more question. This T you have taken here.
Yes, sir.
This is contraction actually.
It can be contraction, but it also satisfies Gornicki point of type contraction. Okay, sir. It is also it will
have similar types of results.
Yes, sir. This is more generalization of the. I will not say the direct generalization, but it is more refined version of all earlier established results of S-metric spaces.
So can we have some results in fractal also using this
Sir,
fixed point theory?
I have some papers in my booklet which are in fractals, but I have not studied them very thoroughly. I will.
Could you suggest some references?
I have not the research in my mind. Okay, sir, those researches in my mind. I'm sorry for that.
Okay, nice. Thank you for your explanation.
Thank you, sir. Okay. Any other questions, sir?
So I think Megha, this one is the last for this particular session. Hello, Megha.
Yes, sir. Yes, sir.
So,
Sir, should I stop presenting?
Yeah, sure,
yeah.
Vatan.
Please.
You can stop your
Thank you very
presentation.
much, Vatanjit, for your nice presentation.
Thank you, sir. Thank you so
And
much.
please keep this remarks and comment in positive way to improve your further research work. So from here I would like to close this session, and I must say thanks to all the team of the conference for giving me this opportunity to be a part of this conference on this particular session. So thank you very much, sir. Over from my side, Professor Sam, sir.
Yeah. Thank you, Professor Dr. Gopal, for nicely chairing this paper presentation session. Please join again after lunch. We have two important talks, or four important talks. Professor
Thank you, sir.
Petruzel, then Professor Raduyan Bott, then P. Marichal, then SM Grad. I hope that you will be there. All of you will be there.
Yeah, sure, sir. Thank you. Thank you.
Another good session. Another good session.
So thank you, everyone. Thank you, Gopal sir, for chairing the session, and thank you all the participants for your contribution. So now we'll have a lunch break, and then after the lunch break, we'll start our session from 14:45. So
Mega, 1 second.
Yes,
Mega,
sir.
1 second.
Yes, sir.
Tanmoy, can you send me an email about the time for my talk Thursday?
So will it be fine, say, that is 16:15 on 23?
That's fine, that's fine.
Yeah.
No, I have no problem. It's just I need a reminder and I need an email. Can you send me an email?
I will mail you, sir. I will mail you, certainly.
Okay.
I will mail you.
Perfect.
Yeah.
Thank you.
Megha, one thing I just wanted to know, this is the Megha.
Yes, sir. Yes, sir.
The keynote speaker or invited speaker, the major speakers, their lectures, we are recording it.
Yes, sir. Yes, sir.
Yeah,
And,
very nice.
and sir, we are streaming on the YouTube also. So there's
That's
a live
nice.
streaming also. So that will also be saved on YouTube.
Oh, thanks. Yeah, very nice. Thank you.
Yes, sir. So thank you, everyone. So we'll meet at 14:45. Thank you for joining us. Thank you so much.
Professor Imdad, are you online? इसको रख देना इनटू फाइल को. अच्छा बाहर के स्पीकर का वो आ गया क्या, कुछ ज्वाइन करने का देख लेना अगर कहीं मांगता। अच्छा ठीक है सर आ गए हैं, कोई बात नहीं है, अभी हम लोग ज्वाइन कर सकते हैं जल्दी ही।
Sir, actually we have added all of them as a guest, so now they don't need the permission.
Okay. Good morning, Professor Petruzel.
Good morning, good afternoon in India, probably.
Yeah. It is afternoon here, certainly. Just 1 or 2 minutes, we'll be starting, sir. Okay, yeah.
So now we can start. Actually, it's 2:45.
Should we wait 1 or 2 minutes? Because some more participants are there. They have not yet joined.
Okay, sir.
Just 1 or 2 minutes.
We can wait, of course.
Yeah.
Sure, sir.
It's not easy after lunch to come back to work.
Yes, sir.
Sir, have you visited India?
Unfortunately, never yet. Even I had some invitations at certain moment, even from your colleague, Professor Sahu.
Okay, yes. But now the pandemic time, we cannot move anywhere. Hopefully, I think by next year it will be all right. Maybe at the end of next year or after July.
Yes, we do hope.
Go to that control room. That room, last room.
Okay.
There is, footing is there.
So should we start, sir?
Yeah.
So very good evening, obviously from India, and welcome you all again in the evening session. So now I would like to request Professor Tanmay Som to chair this session, and please come forward, sir. Thank you, sir.
Thank you, Megha. So we have now the first talk in this afternoon session by Professor Adrian Petruzel. Professor Petruzel is a professor of mathematics at BEPS Bolai University, Cluj-Napoca, Romania. He received his PhD degree from the same university in 1994. His research areas are nonlinear analysis, particularly fixed point theory, then differential equations, and multi-valued analysis. He has a very good teaching experience, and he has several publications and very high quality publications, including in the journals Mathematical Analysis, then Fixed Point Theory. He is also in the editorial board or even editors of many reputed journals such as Math Analysis, then Convex Optimization, Journal of Nonlinear and Variational Analysis, applied analysis and optimization. And he's a chief editor of the journal Fixed Point Theory and Algorithms for Science and Engineering. So I don't want to be any hindrance between the actual talk of Professor Petruzzel. Recently, we heard his talk at Serbia. It was really a very nice talk last month, 2 months back. So I invite Professor Petruzzel to take over the mic and deliver his talk.
Thank you very much for your kind introduction. First of all, of course, I would like to thank the organizer and especially to Professor Som for his kind invitation to join this important international event. I do know that Banaras Hindu University has a very strong mathematical school. I know some people there, and I am very honored to be part of this international conference. Okay, so I will try to share my screen for the conference. It's okay now? Can you see my screen?
It is coming, sir. Just yes.
Okay, so I will speak about step-by-step contraction principle for the case of so-called abstract Volterra operators. And mainly in this talk, we will use two important results in fixed point theory, namely the so-called weakly Picard operator theory and the fiber contraction principle, in order to generate step-by-step contractions for the, let's say, special case of abstract Volterra operators, but considering the spaces of functions of several variables. Going a little bit back, I will mention some historical notes about the subject of Volterra operators, and the first bibliographical title that I would like to mention is from 1930, when Leonida Tonelli considered the following equation. You can see it here: x of t, it's equal f of t plus a, depending on t, and x0 of tfs on 0 capital T, where x and f are continuous mappings, and a of t and y stands for an operating taking continuous functions y of s into continuous mappings, where the notation that I use here, x index 0 of t, means the restriction of x to the interval 0t, and it was used for the first time by the Italian mathematician Vito Volterra. So Tonelli considered this paper in a publication in a paper from Bulletin of Calcutta Mathematical Society, and with respect to the above, let's say, abstract equation, he considered the following examples. The first one is, let's say, a integral equation, which it's also known as a Volterra type integral equations. And the second is a similar equation, but involving two kernels, k and h, and of course the values of the unknown functions on 0t. Okay, with respect to this general equation, Tonelli proposed some results, more precisely an existence and also uniqueness results. For the existence result concerning this equation, Tonelli worked with the well-known Ascoli-Arcela theorem, and the idea is to construct approximate solutions in steps, and then proving the compactness of the set of these solutions, which leads to the existence of a solution on some interval 0a included in the given interval. For the uniqueness, he obtained also the uniqueness, but under some extra assumption on the data. Okay, later in 1938, the Russian mathematician Tikhonov considered the following notion, the following definitions. If we denote by capital E and capital F two function spaces and V an operator from E to F, then Tikhonov said that V is an abstract Volterra operator. And we will also find in the literature the term of causal operator or non-anticipative operator. So capital V is an abstract Volterra operator if the following implication holds: if x1 and x2 are equal for every t on 0 t1, then V of x1 is equal with V of x2 on every t for all t1 strictly less than t. The paper of Tikhonov was published in the Bulletin of the Mathematical University of Moscow in Russia in 1938. Some examples of equations with abstract Volterra operators considered by Tikhonov are the following one: x of t is equal to V of x of t, x prime is equal with V of x of t, or a kind of coincidence problem for abstract Volterra operators. V of x of t is equals with W of x of t, t on 0 capital T. We can notice the following fact: if we consider a Cauchy problem associated to this Volterra type of equation, x prime equal V of x of t, x in 0 it's x0, then by integrating the both sides of the given equation, we get an integral equation of this kind, of this form: x of t is equal to x0 plus the integral of Vx s ds on 0t. And if we denote the right-hand side of this integral equation by calligraphic V of x of t, then if V is an abstract Volterra operator in the sense of Tikhonov, then calligraphic V is also an abstract Volterra equation. Thus, the above Cauchy problem can be reduced to an equation involving a abstract Volterra equation of this form, so we can study these types of problems. And something similar can be said about the coincidence problem that I mentioned before. Some results for equation with abstract Volterra operators I will mention now, and here we are focused on this problem, find the solution x of the equation x of t equal V of x of t. And I mention here a result, an existence result of Corduneanu. He has several papers and even books written on the subject of Volterra operators. So if E is a space of continuous of or LP function from 0t to Rn, And V from E to E is a completely continuous abstract Volterra operator, completely continuous in the sense that it is continuous and sends bounded sets in relatively compact sets. Then there exists an A in 0T such that the given equation has at least one solution in the space where the equation is considered. So this is an existent result, and the approach, the idea of the proof is to apply a fixed point theorem, namely the fixed point theorem of Schauder. Another result for this kind of abstract equation was given by the Polish mathematician Kvapisz. In this case, we have an existence and uniqueness result, and the result is the following one. The underlying space E is LP. V from E to E is an operator satisfying the following Lipschitz type condition. And we have here the condition on almost T on 0, capital T, and XY from E. We notice here that the abstract Volterra operator assumption does not explicitly appear, but you can easily check that this condition implies that V satisfied the abstract Volterra condition given by Tikhonov. So if V satisfies the Lipschitz condition, it is also an abstract Volterra operator. Under some assumptions related to the function capital E, L, let's say the Lipschitz function of this condition, there exists a unique solution X star of this problem, and in this case, because we have existence and uniqueness, as you can imagine, the approach is based on Banach contraction principle on E, where the space E is endowed with a special widened norm. Some generalization of the concept given by Tikhonov on abstract Volterra operator, and the first one is that given in this paper from 2008. So we have B, an abstract set, and for each gamma from 0, 1, we denote by V of gamma a set of equivalence relation on B, such that V of 0 is the Cartesian product B of times B, and V of 1 means that none of the elements of B is equivalent to another. And of another assumption is that if gamma is greater than V, then V of gamma is included in V of nu. Then the operator V from B to B is called an abstract Volterra operator with respect to this system if the following implication holds. If the pair XY belongs to V of gamma, then V of X, V of Y belongs also to V of gamma for any gamma from 0, 1. In particular, if we consider the family calligraphic B composed by equivalent relation V of gamma defined in the following way: XY belongs to V of gamma if and only if X of T is equal with Y of T for any T from this interval, then you can obtain the above mentioned Tikhonov concept of abstract Volterra operator. Another definition was given in 2019 by Roos in this paper, and in this case is the Volterra property with respect to a sub-interval is proposed. More precisely, if we have a Banach space B and see a number between A and B, then V from the space of continuous functions with values in B to itself has the Volterra property with respect to the sub-interval AC if the following implication holds. if xy are continuous functions such that they are equal on this interval AC, implies that v of x and v of y coincide on the same interval. And we say that the operator capital V has the Volterra property if it has the Volterra property with respect to any subinterval AT with T between A and B. Now some preliminary notions and results which are needed for the main results, and I will recall here the notion of weakly Picard operator, and the context here will be for metric space XD. And we say that f from x to x is a weakly Picard operator if always the sequence of Picard iterates for any x from the space, the sequence of Picard iterates is convergent, and its limit, which may depend of x, it's a fixed point of f. If this property holds, if this condition is satisfied, then we can generate a set retraction related to the above condition. And this is denoted by f infinity from x to the fixed point set of f, defined by f infinity on every x from the space is the fixed point, which is the limit of the sequence of Picard iterates. In the case of a unique fixed point, we will say that the operator is Picard, and in this case, of course, the f infinity is a constant function. The mapping f infinity is constant. Also, I would like to recall some contractions notions. If XD is a metric space and J, capital J, is a subset of x times x, then f from x to x is a J contraction if there exists a constant alpha strictly less than 1, such that the contraction conditions, the usual Banach contraction conditions, holds for every pairs from this subset of the Cartesian product. Of course, if J is x times x, we get the usual notion of contraction, and in this case, we know that if the space X is complete, then we have a unique fixed point. And we have in this way an example of a Picard operator. A contraction in the sense of Banach on a complete metric space is an example of Picard operator. Another example, if we consider J the graph of the operator F, then F is also called a graphic contraction with constant alpha, or in some papers, the name is used the name of orbital contraction with constant alpha. And in fact, the contraction condition takes, in the case of graphical contractions, this particular form. And if F is a graphic contraction on a complete metric space, and if additionally F is continuous, then F is a weakly Picard operator. So we have the two conditions that I mentioned in the previous definition. So we have at least one fixed point, and the Picard the sequence of Picard iterates always converge to a fixed point. Fiber contraction principle is the following theorem. Here is given in a generalized form. In fact, in its, let's say, classical form, it was used for proving the differentiability with respect to parameters for the solution of some operator equations. In this generalized form, we have the following theorem. Xi di from 1 to m are metric spaces, and we consider the following subsets: u1 of x1 times x2, and so long um minus 1 subset of um minus 2 times xm, non-empty. And we attach to these sets the following sets. u1x means the elements x2 from capital X2, such that x and x2, the pair x2 is in u1 for every x in x1. And so long um minus 1 of x, the elements xm from capital Xm, such that the element x xm is in um-1 for x in um-2. We suppose that these sets are non-empty, and we consider the operators T1 from x1 to x1, T2 from U1, which is a subset of x1 times x2 to x2, and so on, Tm from un-1 to xm. These operators, this T1, T2, Tm, generate the following a kind of triangular operator, capital T, from un-1 to x1 times xm, given by the formula T on this point, x1, xm, is T1 of x1, T2 of x1, x2, and Tm of x1, xm. Now the hypothesis of this theorem, m is a natural number greater than 2. We suppose that xi, di are complete metric spaces from 2 to m. We suppose that the sets ui are closed for every I from 1 to m-1. We suppose that ui is an invariant set with respect to this operator for I to 1 to m-1. And now we suppose the following main condition. T1 is a weakly Picard operator. In particular, it could be a graphical contraction. And the following Lipschitz type condition holds with respect to the operators Ti plus 1, where I is from 1 to n-1. So here Li is strictly positive, but small li should be less than 1. And this condition holds for elements from ui. Di is a metric induced by the matrix d1 di on x1 times xy by the maximum of the values of d1 di. These are the hypotheses, and now the conclusion is that the operator T that was generated before by T1 Tm is a weakly Picard operator, and moreover, if this T1 is Picard, then T is a Picard operator too. For example, in the case m equal to 2, we get the classical, let's say, the classical fiber contraction principle. And in this case, you can see that T has this form, and the conditions that I mentioned before takes a simplified form. And this theorem was, as I mentioned, used for some property of the solution with respect to parameters. Now, the definition of an abstract Volterra operator in a general form is the following one. X will be an abstract set lambda from lambda, and R lambda be a family of equivalence relation on X. Then we say that V from X to X is an abstract Volterra operator with respect to the family R lambda. If the following implication hold, if Xi are in R lambda, then Vx, Vi should be there also. Some examples. Let us consider AB from Rp such that AI and is strictly less than Bi for every I. And we denote by this symbol, by this interval, the Cartesian product of the intervals AI, Bi. Let's consider I a non-empty set, X be the sets of all mappings from AB, from the interval AB to Y. So with respect to the above definition, capital lambda is AB, R lambda is the family of the pairs UV such that U and V coincide on A lambda for every lambda from AB. By definition, then, an abstract Volterra operator with respect to the above family, satisfying the above property, is called a forward abstract Volterra operator. So in this case, we have an example of abstract Volterra operator, which will be called in the following part of my talk as a forward abstract Volterra operator. In the special case P equal to 2 and Y it's R, the operator V defined by, we consider the operator V defined by this formula. So the integral are from A1 to X1, A2 from X2. K is a continuous function. This is an example of a forward Volterra operator, so satisfying the above properties. A second example, if we consider a different equivalence relations, give R tilde lambda given by this formula, in this case, the restriction of U and V on lambda B coincide for every lambda. And in this case, capital V from X to X will be called a backward abstract Volterra operator if it is an abstract Volterra operator with respect to the above family of equivalence relations. And for example, this operator, the integral here are from B1 to X1, B2 from X2, is a backward Volterra operator, but it isn't a forward Volterra operator. Another example which leads us to the definition of roots of the abstract Volterra operator with respect to a subinterval is the case when the equivalence relation is RC given by this formula with respect to a certain C between A and B. Okay. Now, let's say the main result of this talk, the step-by-step contraction principle. We have AB as before in the case of forward abstract Volterra operators. We have these points. T0 is the point A, Tk is constructed at T0 plus K over MB minus A, K from 1 to M, and V, it's considered to be a forward abstract Volterra operator. Then the operator V induces the following operators denoted here by V1, Vm minus 1, V1 from the space of continuous function on AT1 with values in the Banach space B2 itself. V1 of U on X is given by V on U tilde on X, where U tilde is a continuous function having the restriction on AT1 equal with U. And so long for Vm minus 1, Vm minus 1 of U on X is V of U tilde on X, where U tilde is a continuous function which coincides with U on the interval ATM minus 1. We also need two notation. Capital G in index K is the set of all pairs UV such that UV are continuous and they coincide on ATK. And for UK from the space of continuous function defined on ATK, X index UK is the set of continuous function U such that U coincide with UK on ATK. Now we have the following result, the so-called forward step-by-step contraction principle, and we suppose that V is a forward Volterra operator. We suppose that V1 generated by V is a contraction. We suppose that the rest of the operators Vk from K to 2 to M are Gk minus 1 contraction in the sense that I mentioned before. Then we have the following conclusion. The operator V has a unique fixed point. Moreover, this fixed point can be obtained as the limit of some Picard iterates. On AT1 X star is the limit of Picard iterates generated by V1. On A2 T2 X star is the limit of V2 of the Picard iterates generated by V2 from every X from the set X index X star on AT1, and so long X star is can be obtained as the limit of Picard iterates for Vm minus 1 starting from any X from this set. And X star is also the limit of picoret rates of capital V for any X, starting with any X from the set X index X star on ATM-1. The idea of the proof is to obtain step by step the conclusions. For example, since V1 is a contraction, V1 is a Picard operator, and we know from Banach contraction principle in the main result that it has a unique fixed point, X star 1. And then we move to the second operator, V2, which is a G1 contraction on this space, X index X1 star, and is a G1 contraction, sorry, and for this reason, V2 is a contraction on the set X index X1 star, and it has also in this set a unique fixed point. And moreover, it is a Picard operator because it's a contraction. And by this approach, step by step, we can get the conclusion. A similar result can be given by for the case of backward Volterra operator, and here is the construction that we need for this purpose. I will skip this part because I would like to move to the last part with an application. So a backward step-by-step contraction principle is quite similar, but in this case, the main assumption is that V is a backward Volterra operator, and we obtain the conclusions from the above theorem, of course, related to the special case of backward Volterra operator. As I mentioned, I would like to also to present an application of the above theory. If we consider the Darboux-Ionescu problem, given here, the second derivative of U with respect to x1, x2 is equal with f of x1, x2, AU on x1, x2, with the Darboux-Ionescu conditions, where the values B1, B2 are strictly positive, B is a Banach space, F is a continuous mapping, and A, which appears here, is a forward Volterra operator. We are searching for a classical solution of this problem. So the idea is to obtain existence results or existence and uniqueness results for this problem. First, we can notice that this problem is equivalent with an integral equation of this form. So you can see here in the right-hand side, we have the integral from 0x1 to 0x2. And if we denote the right-hand side of this integral equation by capital V of U computed on x1, x2, then it is easy to observe that capital V is a forward Volterra operator. Of course, under the hypothesis that I mentioned here, that capital A is a forward Volterra operator. So in this case, this problem looks like an equation induced by a forward Volterra operator, and we can apply the step-by-step contraction principle for forward Volterra operator, and we can obtain the following result. So we impose the following assumptions. We have a Lipschitz condition with respect to the third argument related to the operator F. We have a kind of Lipschitz assumption with respect to A. As you see here, LA should be strictly positive such that the Lipschitz conditions mentioned here is satisfied. So under the above two conditions, if additionally this number is strictly less than 1, then the following conclusions take place. So we have existence and uniqueness for the problem 1, in the sense that the equation with abstract Volterra operators have a unique solution. So the unique solution of the Darboux-Ionescu problem is the fixed point of V. And this is denoted by U star. And this U star can be obtained on different intervals as the limit of Picard iteration starting from convenient values from the space of continuous function defined of 0 T1 or on different intervals that we mentioned here. So the idea of the proof is that the operator V that is generated by the integral equation and the operator V1, V2, Vn minus 1 satisfy the forward step-by-step contraction principle. A similar result can be given related for a different Darboux problem applying the backward step-by-step contraction principle. An open question that I would like to point out, if V is an abstract Volterra operator, as in the step-by-step contraction principle, under which additional assumption can we have the conclusion that V is a Picard operator, in the sense that the fixed point of V is the limit of the Picard iterates of V starting from any point of the space. As a partial answer to this problem, the operator V from the above theorem, so from the case of Darboux-Ionescu problem, is a Picard operator. So in this case, the conclusion follows by applying the generalized fiber contraction principle that I mentioned in the preliminary section. The main references are related to the main references with respect to this talk is the main one is this paper written with Professor Roos and submitted for publications. But also important papers are this survey paper of Cordugnano, Abstract Volterra Equations from 2000. For the fiber contraction principle, we have a paper recently published in fixed point theory, some variants of fiber contraction principles and applications. Also, with respect to the case of Volterra operations with operators with respect to a sub-interval, this paper of Roos, and the paper of Zhukovsky and Alves, where I mentioned the notion of abstract Volterra operator under this name was introduced for the first time. I think that's all. Thank you very much for your attention.
Thank you very much for your very thought-provoking and illuminating talk concerning Volterra operator, then fiber contraction and Volterra integral equation, application to Volterra integral equations. So few questions, maybe if there are, please, from the audience side. It seems there is no question from other participants. So I want to know one thing, sir, one question, just this fiber contraction, and what is the basic difference between fiber contraction and the Banach contraction?
So the main difference is that in the case of fiber contraction, we have we get existence and uniqueness for a fixed point for an operator defined on a Cartesian product of spaces. This is the main operator, and this operator is composed by two operators, which is I can show you the case n equal to 2. You see? So in this case, the result is given for this capital T which works from a subset U of x1 times x2 to x1 times x2, and it is the fixed point of a kind of triangular operator. and is a very useful tool for some properties, especially differentiability with respect to parameters in different differential equations.
Okay, thank you, Professor Petruzel, for a very nice talk. And now I request you to chair the next talk to be delivered by Professor Radu Jan Bott from Austria.
Okay, I will stop sharing. Yes. Okay.
So, hello. Then I should try to share my screen, I guess. I mean, it's okay. Oh, it's the first time I'm using Meet Google. So let's see.
There is a sign there. Okay. It's very similar to Teams if you use Teams more.
Yeah. Okay, so let's, yeah. Okay, let's see. Give me 1 second, please. Okay.
Just click on the arrow on the bottom.
Yes, but my iMac has a lot of
Oh, I think that Professor Bott left the meeting. Maybe it's a kind of
no. He will join certainly. Probably
internet problem. Let's wait for him. Okay, he's back.
Sorry for that. So it is just my computer with a lot of protection, and it's not very, yeah. So it is not very much compatible with Google.com, and yeah, there is always conflict between Google and Apple and so on in terms of access rights. So let me try to do it again. I don't know. Okay. So what about now?
Yeah, it's
coming.
It's
fine.
Okay,
Can you
so it is my real pleasure to introduce the next speaker. In fact, we have a keynote talk now, and the speaker is Professor Radu Jan Bott. So Radu Bott is full professor of applied mathematics at the University of Vienna, Austria. And Professor Bott is a well-known expert in the field of optimization theory and applications, including here computational optimization, non-smooth and vector optimization, convex analysis, and so on. Professor Bott published 2 excellent books focused on duality in convex and vector optimization, and it has more than 170 papers in very good international journals. Since 2020, he is serving as Dean of the Faculty of Mathematics and Head of the Institute of Mathematics at the University of Vienna. He is also a member of the editorial board of many important journals, including Journal of Optimization Theory and Application, SIAM Journal on Optimization, Applied Mathematics and Computation, Applied Mathematics and Optimization, and many others. He's also working on different cooperation projects with industrial partners from different countries, Austria, Germany, Switzerland. So we have here an expert in the field of optimization, and I am very pleased to offer the floor. Professor Bott, please.
Thank you very much. I'd like to thank first my friend Adrian for the very nice introduction. And I'd like to also to thank Professor Som for inviting me to give a lecture in the framework of this conference. It's a pity that you are not now in India, just to enjoy your beautiful country. Yes, probably this will be possible. Hopefully this will be possible in the future. Yes, so today I will talk about the interplay between continuous and discrete time methods for convex optimization. And the talk today is based on joint works with some of my collaborators, Robert Chennai, Sira Laszlo, and Koan Nguyen. So I want to ask you two questions. The first question is, do you see my mouse?
Yes.
Okay, very good. And now I will move to the next page. Do you see the second page?
Yes.
Yes, very good. So let's start. So I will start with a short introduction, and I will just present some classical approaches, classical models for addressing optimization problems. So we start with the minimization of a function h, which is assumed to be convex and differentiable. Gradient depth is continuous, and one can approach this problem through a first-order dynamical system of this type, where we have a first-order differential equation, and x0 is the value the trajectory takes at time 0. And what is known, namely the following fact: if there is a minimizer for the given problem, if you know that the set is non-empty, then the trajectory of this system, which we know that to exist, is bounded. And it converges weakly to a minimizer of the function h. So if the set of minimizers is non-empty, and the derivative is converging to 0. Now it is well known that after time discretization, one obtains the very classical gradient method with step size decay. Now, okay, then let us move to another unconstrained problem, but by assuming that the objective function is now non-smooth. So the function is proper convex draw semi-continuous. This is a classical setting. And one would like just to extend the above approach to this problem. And how? In a very natural way, namely by replacing the gradient by the subdifferential of the function f, which you know that it is set valued. So we just replace the equation we had in the previous approach by an inclusion. For this hierarchical system, the existence of trajectories, it's a little bit more difficult to show. But what is known is that providing there is a trajectory, then this also converges to a minimizer of the function f. So we have the same behavior for the two systems approaching two problems, but for which the objective functions have different properties. So in particular, for the second model, there is no differentiability assumed. Now, what about discretization of this inclusion? Here we have two options. So we can either discretize the system in an explicit way, and this means just replacing or just taking it as an argument of the subdifferential xk, and one easily can see that this gives rise to the so-called subgradient method. Or we have the option to use xk plus 1 in the argument of subdifferential, and through the equivalent through a reformulation of this inclusion, one just obtains that xk plus 1 is the inverse of the sum of the identity operator with the differential operator, and this operator is nothing as the proximal operator of the function f. So one obtains, by discretization of this system, one can obtain two classical numerical algorithms, the subgradient method and the proximal method. Okay, and this is what we know for the minimization of a single function. Let us make now the problems a little bit more involved and consider the first model, but now by minimizing the function h over a set C, which is assumed to be convex and closed. And Antipin, long time ago, and Bolt, 10 years later, he proposed a system for this, let's say, structured problem, for which one could also just extend the model from the slide above by considering on the right-hand side the sum of the differential of H and the normal cone of C, so just to have an inclusion. But this would be one easy, natural way to approach this problem to an analytical system. But there is another construction proposed by Antipin and then constructed by Bolt, where one has an implicit type analytical system or first order equation, where one has on the right hand side a gradient step for H and composed with a projection on C. Okay, so is this formulation kind of better than just using inclusions? From the point of view of proving existence of trajectories, it is better, since for such a model, the existence uniqueness result follows by standard Cauchy-Lipschitz theorems, and one can prove for this construction more or less the same behavior of trajectories as for the previous ones, so weak convergence and so on. Okay, then it was just natural to extend this model to the minimization of the sum of two functions, non-smooth plus smooth. This was done by Abbas-Satoush, 2015, where in a natural way the projection operator was replaced by the proximal operator of the function f. And one can prove for the trajectories of this system that they weakly converge to a minimizer of this problem, where we have more structure than before, since we consider the sum of two functions. And here is interesting to see the discretization of the Abbas-Satoush system just leads to the so-called proximal gradient algorithm with relaxation parameters and with variable step size. And it was noticed in the last years that using relaxation parameters is not only let's say a complication of the scheme, but can be of some help, in particular if one looks at the interplay between relaxation parameters, step sizes, and sometimes inertia parameters. So this is what we know, what we have for the minimization of the sum of two functions. Now the question is, what happens if we consider even more structure into objective function, and more structure comes with an objective function which is more involved. And before coming to this part, I'd just like to say that the continuous dynamics provide the unifying schemes when assigned to optimization problems. Then different time discretizations lead to different numerical algorithms, and there is a very nice interplay between continuous and discrete times, and one can just make use of ideas, let's say, developed for continuous time schemes like Lyapunov functional asymptotic analysis, and export these ideas to discrete schemes. So there is an interesting parallelism. One can just enrich one topic by using ideas from the other topic and vice versa. So as I said before, let us make the problem we consider more involved. I mean, why is this just a useless generalization? For sure not. So addressing problems which appear in many application fields means considering this type of more involved optimization problems, where, for instance, composition of linear operators appear. Namely, so we have here the sum of a non-smooth convex function f, of a smooth convex function h, and of the composition of a non-smooth function with a linear operator. It doesn't make sense to compose a smooth function with a, since we finally get a smooth function, but it makes sense to compose the non-smooth function with linear operator a, and the question is how to address such problems. And for such problems, independently of the setting we are considering, discrete time, continuous time, one will have to make use of some primal dual concepts, of primal dual techniques. And this is what we also have in mind. So we would like to use to develop a primal dual scheme. And to this end, we will first attach to the problem we have the following reformulation, where we introduce z as a select variable, and we obtain an equivalent formulation where we have a linear constraint. And to this problem we attach is the Lagrangian, construct the Lagrangian, where y is the Lagrange multiplier, and we are looking for center points of the Lagrangian. So center points, this everybody knows what the center point is, and the question is how do they relate with the primal solutions, and also with dual solutions. This is something I will explain on the next slide. So finding a center point, either through a dynamical system or by means of the discrete scheme, means solving the primal problem. So X star will be a solution of the primal problem, means solving the differential dual problem. F star, H star, G star denote the differential conjugates of the functions f, h, g. A star is the adjoint operator. And there is a link between X star and Z star through A. And this is the way to proceed when considering problems where a composition linear operator occur in the objective function. Okay, so this is what we want to do. We want to detect center points either through continuous time approaches or through discrete time approaches. Now, there is another characterization of a center point, namely by means of the so-called system of multi conditions. So finding a center point means you're just solving the system where we have the differential of f and g star, where we have a gradient of h, where we have the adjoint of a star. So this is equivalent formulation of X star, Z star, Y star being a center point. This is something we have in mind, and we want to do in the framework of this talk and of this investigation. Now the question is: do we have center points? Are we able to guarantee the existence of center points? Yes, we are. To this end, one needs to assume that the primal problem has an optimal solution. Okay, there are many ways to do this. One usually uses coercivity or sometimes compactness of the feasible set if this is given. Or, and the existence of primal solution it must be combined with the so-called qualification condition. Here I formulated one of the one weak condition, probably not the weakest, but the to this one is a weak condition of this type, which then guarantees existence of a primal dual solution, and then existence of such a triple, which is a center point of the Lagrange. So we know how to guarantee that center points exist now, and we know that when addressing such problems, we have to construct an algorithm or a dynamical approach which detects, or both, which detect a center point. Now, how to do this? Okay, let me propose to this end the following dynamical system, which looks kind of complicated, but I will just explain you what we are doing here. And this is based on a paper we published last year with Robert Chen and last in Journal of Differential Equations. So we have 3 blocks, and we have a set of initial time conditions. And the 3 blocks, they correspond to the 3 variables. So an X block, a Z block, and a Y block. And all 3 blocks are differential equations. The first one is a differential inclusion. We have here the inverse of an operator, which is for sure maximally monotone, but nothing more. We don't know that if this inverse is single valued, since we cannot apply Minty theorem in the general setting. We have a second inverse of a second operator, where to the Minty theorem we know that it is single valued, and we have an update of an equation in Y, which as I said, corresponds to the dual variable. And here it's important to know that M1 and 2, these are operators with values in the family of continuous linear self-adjoint operators, positive semi-definite, and we are free to choose M1 and 2. So we will see, we will take M1 and 2 equal to 0. So M1 and 2 gives us a certain flexibility, and we will make use of it. And we have C, which is a variable that is very much related to the Lagrangian. We'll see later to the augmented Lagrangian. And we have gamma, yeah, which is an operator, which is a number that will give us the level of implicitness of our scheme. And I will say more about gamma later. And I'll try to emphasize, to highlight the role played by gamma. Okay, so what about this dynamical system? It looks complicated, but we will see that time discretization of the system different discretizations lead to different primal dual algorithms from the literature. So we can show the trajectories exist and they are unique. We can prove that trajectories weakly converge to a primal dual solution or to a center point of the Lagrangian, and we can prove a convergence rate of 1/t for a primal dual gap and for the feasibility condition. But this is in an ergodic sense. Yeah? So this I will do in the first part of my talk, and then I will come to a second order system. Okay, and then for this system I will present very fresh results, and in particular related to the convergence rate of this second order system. But let's stay now with the first order system. And just in order to link it to algorithms, I like to mention that the first inclusion or the first block can be written as an inclusion of this type. And now discretization of this dynamical system leads to a numerical scheme, wherein for every k I just generate an element xk plus 1 with this property, which I can write equivalently as xk plus 1 is an arc mean of this function. And the M1 matrix, or the M1 operator gives a matrix M1k, which is assumed to be positive, semi-definite. And I do the same with the second equation, time discretization, and this gives another iterative step. Now this equivalent to zk plus 1 is the arc mean of the function we can see here. Okay, and now putting this together, and with the discretization of the third block, which corresponds to the dual variable, I obtain the following algorithm, which is a classical algorithm in the literature. And this just shows that the dynamical system proposed can be seen as a continuous counterpart of a so-called proximal ADMM method. Okay, why proximal? Since for M1 and 2 taken equal to 0, one obtains the ADMM method, but if the two matrices or the two singles matrices are not 0, one obtains here two proximal terms introduced by means of these variable metrics, if you want. Okay, but then we are very close to the ADMM algorithm. And then for gamma 1, proximal ADMM, see for gamma 1, we use in the second block xk plus 1. And this is what ADMM is doing. For gamma 0, we use in the second block xk. And for gamma 0, it means that the first two blocks can be generated by parallel schemes. So I'm not using this alternating scheme or step. And as I said before, for M1 and 2 0 and gamma 1, what we get here is ADMM. So dynamical systems provide a unifying scheme for algorithms. This is what I said before, and this is what we can see here again. For the dynamical system we considered, we can let's say rediscover many important algorithms in the literature. But is this all? We will see. No, we get even more. And even more means the following. Okay, probably let me say one word about ADMM. So what we don't like when it comes to ADMM, we don't like the fact that not the second block. The second block can be written as a proximal operator. When M1 and 2 are 0. But the first block cannot be written as a proximal operator because of AX here. This means that in order to solve the first argument problem, even if the function f is prox friendly, one has to use an inner loop. And this is something one like to omit, and this can be done by choosing M1 and M2 in a clever way, just to annihilate, let's say, the bad influence that the matrix A, operator A has. Let's do this in the diagonal setting first. How? By choosing M1T, M2T in this form. So M1T is this matrix, M2T is 0. I have to guarantee that M1 is positive semi-definite. So to this end, I just have to make an assumption on the step size tau, to choose it like here, and this is easily guaranteed. And then for this choice, my OD, the OD becomes this diagonal system where we don't have inclusions, we have only equations, and the first two steps are proximal operators. And as I said, if F and G are prox friendly, one can, for many applications, calculate these prox operators in an exact way, and one obtains very easy schemes which then can be solved by discretization, namely, and this is something I like to present now, for H equals 0 and gamma 1, this means I assume that there is no smooth function, and that gamma is equal to 1, then the scheme has this formulation, and now by discretization, I obtain an algorithm, which you can see here, which is nothing else than the classical Chambol-Poc primal dual algorithm. And Chambol-Poc is probably one of the most influential numerical methods of the last decade, 10, 15 years. And it was widely used by engineers, by computer scientists, by mathematicians, by many practitioners, because of the fact that such an algorithm is a full splitting method. One has forward regulations for A and A star, one has proc steps for the non-smooth functions, and this is a great scheme. And the Chambol-Poc algorithm is another particular scheme we obtain by discretizing and our general diagonal system. Okay, let me now continue with the analysis of the diagonal system, and I will address three main questions. The first question is related to the existence and weakness of trajectories. And we have here a result which I like to mention. Namely, we assume that M1 is chosen such that CA star A plus M1 is positively definite. This is more than what we had before. And we assume that M1 and M2 are L1 locally integrable operators. And then for every starting point, the system has a unique strong global solution. So this means that it has a solution which fulfills the system almost everywhere. These are absolutely continuous solutions. Okay, how to prove this result? I mean, here we are using a theorem of Cauchy-Lipschitz type, just to link now the topic with the previous topic. But this is a result by Haro. So with the previous talk by Adrian Petrushel, is a result by Haro. And to this end, you write the diagonal system in this form, by using an operator gamma, which is an operator that depends on t, x, y. And this operator is defined in the following way. So the operator in t, x, z, and y takes as value what you see here, u, v, w, and these are just the minimizers, the first two, of some functions. But what is important to notice here is the following, that the operator we consider here when fixing x, z, and y is Lipschitz continuous, and the Lipschitz constant is L1 local integrable. And this is something which we need in order to get the existence result. Okay, just one question I'd like to address here. Where does Lipschitz continuity come from? So we have here arc mean, so this is not a surprise, since what we have there is these are prox-like constructions. And we know that proximal operators are Lipschitz continuous. And this is something we can expect also from these arc mean constructions we consider here. It's very much to the intuition, and it's very much connected. And the intuition comes from the Lipschitz continuity of proximal operators. Okay? And this explains why these arc mean constructions are Lipschitz continuous. Okay, this is a way to go here and to prove that the first property is fulfilled. For the second property, we fix x, z, and y and prove that what you obtain in T is locally integrable, and then putting this together, these two properties give us the setting in which one can guarantee existence of strong global solutions for our dynamical system. Very good. So the next question I'd like to address is the convergence of trajectories. And to this end, I just want to define the derivative of M, which is defined, if you want, in a Gator sense. We are considering the norm topology, which is, okay, this is the limit of this object at T0. We consider the limit with respect to norm topology of the space of linear continuous operators. And defining this derivative allows us to consider the following properties. So first of all, if M is locally absolutely continuous, then derivative exists almost everywhere. Okay, this is great. And we say, and then we can relate this notion with the notion of M being monotonically decreasing, which is defined here, and which is very natural. And this is in the sense of the half order, defined through the property of being positively semi-definite. So what I'm writing here means that MT1 minus MT2 is positively semi-definite. And if M is monotonically decreasing in this sense, then the derivative exists, and if it is also locally absolutely continuous, and we have this property for the derivative. You can see here this inequality. And this is something we will assume here, but this is something which is, of course, very much in the spirit of what we have for discrete schemes, where one is usually considering a sequence of such matrices, which then are assumed to be monotone in a similar sense. Okay, so, and now I would like to formulate the theorem which proves the convergence of trajectories. What we assume is that the center points exist. Then we assume something which is very reasonable and which is fulfilled in many cases. Then the two operators in time are locally absolutely continuous, monotonically decreasing, and that the norms of the derivatives are bounded. And then we have two settings. One setting, the second one, let me start with the second one, where gamma, this parameter just describing the level of implicitness, is between 0 and 1. By gamma 1 is not allowed here. And we just have to assume that A star A is positively definite. But this is something which usually assume when considering ADMM. Or in the second setting, where we allow gamma to be equal 1, gamma is between 0 and 1, the closed interval, and we have this condition on the matrix. And let me recall that we are free to choose M1, and then if one of the two conditions is fulfilled, then the trajectory converges weakly to a center point of the Lagrangian. Now, I will not present the proof, but just mention the pillars of the proof. One pillar is the continuous OPR lemma, which is very similar to the OPR lemma we know in the discrete case for a given norm. Now we have a continuous version. We have some norms here which are, or sometimes semi-norms, since MT was assumed to be only positive semi-definite, induced by MT. And if this limit exists for every Z in the set C, if every weak sequential cluster point of trajectory belongs to the set C, then the trajectory converges weakly to the set C. This is one pillar of the proof. And I just want to show you at which point are we using this lemma. So first of all, what we need a Lapoon of an energy function. And the function you see here in parentheses, with the parentheses, is the energy function. And then we can show that the time derivative of this function plus some other terms which are great, because of the fact that they are all non-negative, is also equal than 0. Here the last term can be omitted if there is no, let's say, no smooth function objective. So everything works well. And then from this inequality, you conclude that this limit exists, and this is exactly what we need in the OPR lemma. But now to put everything in the setting of the OPR lemma, we will just need an MT, which is decreasing, and which is this operator. And with this, we obtain that the first element of the OPR lemma is fulfilled. And then we can also derive from the previous inequality that the first derivatives of the trajectories, first order derivatives are L2, and we can conclude from here the second order derivatives are L2. And by combining these two properties through let's say a classical result, we obtained that the first order derivative converges to 0, which is something that we had also for the schemes I presented during the beginning of my talk. X prime, Z prime, Y prime converge to 0, and then these are fundamental statements. Since now, in order to prove the second hypothesis in the OPR lemma, which says that every weak sequential cluster point is a saddle point, we are using a so-called asymptotic principle, which in some books is called demi-closeness principle, which is very much related to the fact that the graph of an operator that is maximally monotone is weak times strong closed, or strong times weak closed. So these properties are used in order to formulate this asymptotic principle, which we can prove that is fulfilled for our problem and for our dynamical system. And then putting these two things together, like statement A is of limit plus statement B in the OPR lemma just gives us convergence of trajectories. So the proof is technical, but it is very much in the spirit of what we are actually using when analyzing the convergence of trajectories or of sequences generated by algorithms. So let us consider some particular cases before just moving to the third main result of this first part. And now we are free to choose M1, M2, and then we obtain a corresponding dynamical system for which you know that it converges weakly to a saddle point. We have two possible choices for gamma 0, 1, or not equal 1, or gamma 0, 1 closed interval, but then we need a condition on A. Then we have a further choice for M1, M2, which just is related to the Chambol-Pox scheme. We get a new dynamical system, we get a new setting, which is very general because of M1, M2. Here they are fixed, and then we get trajectories which converge weakly to a saddle point. And just before moving to the convergence rate result, I would like to discuss a very simple example, just in order to emphasize the role of gamma, which I call to be the level of implicitness. So we have here a primal problem, we have a dual problem, we are just plotting some trajectories here for different values of gamma, and for different values for tau times c. This is a parameter which appears, or these are parameters which appear in the scheme. And what we can see here, so we start with gamma close to 1, then we take gamma 0,5 and gamma close to 0. And we do this for the primal and for the dual trajectories. And what one can see is that when gamma is close to 1, then convergence takes sooner place than later when gamma is close to 0. And this we can see for tau times c, which must be less than 1/2, for tau times c close to 1/2, but also for tau times c equals 0.25, and for tau times c close to 0. So same behavior, larger values for gamma just induce faster convergence or earlier convergence. It's beneficial for convergence. So this is just a toy example, just in order to understand what the role of gamma, and what's written here is just what I explained before. It's good to take gamma close to 1, but then only if tau times c are let's say closer to the upper bound. For here, when tau times c is close to 0, there is not much difference between the choices of gamma. Just a toy example before proving here something which is very standard for primal dual algorithms, namely ergodic convergence rate result, where we are looking at these trajectories x tilde z tilde, which we generate, which we define this way, and one can prove that the feasibility gap or the feasibility condition for these two trajectories converges to 0 at the rate big O 1/t, and the difference of trajectories, the difference of function values converges to 0 again with gap big O 1 over T. But again, we are talking about the convergence along ergodic trajectories. So, and the question is this the best we can get for primal dual schemes? And the question is, can we just modify the schemes? And can we relate the modified schemes to numerical algorithms such that we can improve this rate, the rate of 1 over T? So I mean, here, of course, we have in mind the Nesterov model for minimization of a smooth function, where the rate is 1 over T squared. And it is a natural question if we can translate this rate, which we have for unconstrained problems and for smooth problems, where we minimize one simple function, convex differentiable, if you can translate this rate to problems with more structure. And I like to try to answer this question in the second part of my talk. Okay. And to this end, I will consider the following problem, where we have structure, but of course, less structure than you would like to have. It would be fantastic if one could consider the problem from the first part and just carry out the analysis I'm proposing here in the second part. But we are not yet there. Still, this is the first step, namely what I'd like to present you next. So the problem we address is the following: minimize a smooth function with respect to or subject to a linear equation. One could write this problem as an unconstrained problem by using an indicator function of the set B and by composing the indicator function with the linear operator A. But as I said, we induce some structure and minimize the smooth function H, which is assumed to be C1 with respect to a linear equation, subject to a linear equation, and define the Lagrangian as before, and define the so-called augmented Lagrangian. And the coefficients or the positive number C, which appeared in the first part, comes actually from the augmented Lagrangian. This is the coefficient of ax minus b squared. Okay, so very good. So let's look at now this problem and what we propose here. And this happened in the paper we published this year with my former PhD and my current postdoc, Kaohsiung. So we propose here a primal dual dynamical system. And looking at the system, you will recognize something which you know from the Poisson system. This is the continuous counterpart of Nesterov. We have this vanishing damping damping term. So we have a vanishing coefficient of the derivative, but not only for the primal trajectory, but also for the dual trajectory. And here we are considering the derivative, the gradient of the augmented Lagrangian. Okay, and this is a system we are proposing, and this is a system we would like to analyze. And this is an equivalent formulation. And what we see here is that we have three parameters: theta, c, and alpha. Alpha is equal than 3. This is not something which you know from the Poisson schemes from the two systems, addressing the unconstrained problem. Okay, and then I will relate everything to the unconstrained problem. Okay, what we can prove here is the following. So we have a following setting for alpha must be equal than 3, for c and for theta, which we can choose between 1/2 and 1/2 minus 1. And for this choice, we can construct the following energy function, where we have the following objects: the primal dual gap multiplied by t squared. We have the primal trajectory, the primal dual trajectory, derivatives, and we have again the primal dual trajectory. And for this function, we can prove the following inequality, and this just shows that the energy function is dissipative. And based on this inequality, we can conclude from here, and this is not, let's say, a straightforward step, but this is what we can get, that for the center point of the Lagrangian, one obtains for the primal dual gap and for the fifth measure a rate of 1/t squared, and the same for the objective function value, 1/t squared. So we are talking about rates for the last. Okay, not for the trajectory, for the trajectory, if you want, for the last iterate, if you discretize. not for the ergodic trajectory. And this is the first result of this type, where one obtains rates of 1 over t squared for all these three important objects: primal dual gap, feasibility measure, and primal objective function. And even more, in addition, if you just restrict alpha to be greater than 3, so alpha equal to 3 is not allowed, and then we can choose theta in this interval. For alpha 3, this wouldn't be possible. Then one can prove that the system has a unique global twice continuous solution, a C2 solution. And one can prove even more that the trajectory, the primal dual trajectory, converges to a set of the Lagrangian. And we also have some rates here, which are which are related to the gradient of h, not to h. For h, you know that we have rate of 1 over t squared. We talk about gradient, and for a star yt. But here the most important statement is the last statement. The trajectory, the primal dual converges to a set of the Lagrangian. And let me relate these results to what is known from the literature. Let me consider the unconstrained problem. And again, x star y star is a setter point. Then this is, okay, how to obtain this problem? By taking a0, b0. So there is no constraint anymore. Then it makes no sense to talk about dual solutions. So we talk only about primal solution x star. Our system becomes Nesterov's fast gradient system proposed by Suboy-Candes. So we have only one equation in the primal variable. And what we recover as particular case or particular cases of our statement is the following: that the function value converges to minimize with a rate of 1 over t squared, and for alpha greater than 3, the trajectory converges weakly to a minimizer of h. So these classical results obtained in the last 4 or 5 years are just particular cases of our general primal dual result. And now the question is, so we have an hierarchical system for this constraint problem. Okay, do we have an algorithm which is kind of which has the same properties and the same fast convergence properties? And the answer is yes, we have an algorithm, and this is something which we put on archive 2 weeks ago. So the algorithm looks in this way, and of course it is a augmented Lagrangian method. So I want to emphasize here 2 facts. So namely the fact that we have inertial terms and we have here a construction which is very much in the spirit of the Nesterov method. But now the coefficients which give the inertia parameters are defined by tk plus 1, and we assumed for tk this inequality. And then I will show you that this inequality covers the classical choices from the literature. This is Nesterov, this is Chabot-Dosal, then and Atouche-Cabot. The choices we have for fast methods in the literature. So this is a general setting. And in this general setting, we define primal and dual sequences in this inertial way by using inertia parameters. And what we have here, we have for the step size an inequality which is related to the primal dual setting. So you see we have a gamma c norm a squared. These is an upper bound for the step size. This is something which comes from the primal dual thinking. So what we are doing here, we are putting together two very well developed directions optimization, the fast algorithms for primal problems and the primal dual thinking, the primal dual constants, the primal dual constructions. Put them together, we obtain this algorithm. And the question is, okay, what can be said about this algorithm? Following can be said. Now, we have fast convergence, namely, if the sequence tk satisfies one of the following rules, the Nesterov rule, and the Nesterov rule corresponds to the choice m equal gamma equal 1. This choice just gives here an equation. For m1, gamma 1, we obtain the Nesterov rule fulfilled as an equation. This is something we know. Nesterov published in '83. then we can cover with our choice the Chambol-Dossard rule. This is this rule. And this fulfills the previous inequality, the general inequality for m equal 2 over alpha minus 1. And gamma can be chosen between these two values. And we also have the Atush-Cabot rule, which is fulfilled by our general setting. And for each of these rules, we obtain for the primal dual gap a rate of 1 over k squared. We obtain for the feasibility measure a rate of 1 over k squared. And we obtain for the function value a rate of 1 over k squared. And so this is the archive paper which the paper mentioned here. Yeah? And then even more. Yeah? If we assume that alpha is still greater than 3, yeah? And then if gamma is chosen between m and 1, yeah, with strict inequalities, and the same for the step size, then we can prove that the trajectory, the primal dual convert. Here we are talking about the sequence of iterates, that the discrete trajectory or the sequence converges weakly to a certain point of the Lagrangian. Yeah? So we have on the one hand fast rates, on the other hand we have weak convergence of the primal dual trajectories. And of course, in the case A equal B equals 0, here what we obtain here is just an ester of fast graded algorithm as a particular case, and we obtain the corresponding convergence results for the fast algorithm. Yeah? And as I mentioned before, these are results published some weeks ago, and you can find these results in this paper. Very good. And before closing, so this is my last slide. Of course, I just would like to reiterate what I said before. This is just one step where we are looking at the minimization of a smooth function with respect to linear constraints. This is, let's say, not the most general problem one can consider. So the question is, what would be the next step? How to extend these results to problems where more structure is available, or where the objective function is even more structured. And as I said, this is my last slide, and I'd like to thank you for your attention.
Thank you very much. If someone has some comments or remarks or questions, we have, let's say, 5 minutes for discussion. There is a raised hand. Professor Singh.
Good evening, sir. Myself, Hardeep Singh from Aligarh Muslim University, India. I have a question, sir.
Sorry?
Sir, is there any applications of these primal and dual dynamical systems? Are there any applications of these systems?
I mean, for the algorithms, of course, they are related to the algorithms. So the system I used in order to derive algorithms, to derive new algorithms, and for the algorithms, there are plenty of many applications. I mean, this is well known. I mean, let me mention imaging. Let me mention machine learning. So many problems here in concept optimization have this structure where we have a smooth object, we have a composition of a non-smooth object with a linear operator, we have another non-smooth object, and then we would like to formulate algorithms such that all these components of the objective function are evaluated in an efficient individual way. And I mean, this was also one of the main motivations for introducing primal dual methods, namely the large number of applications, in particular coming from imaging, but not only. There is clustering, there is data science, machine learning, regression, compressed sensing, and so on.
Okay, sir. Thank you.
Thank you.
You're welcome.
Hello. Hello.
Yes, please.
Professor Boat, sir, really nice and a fantastic presentation on the dynamical system. And I observed that there is nice generalization of the Opel condition. So one thing is in my mind, that how can we practically consider the continuous open lemma, because it is changing according to the NAR and depending on MT.
Yes.
And that.
No, but this is. Yes. So this is something which is known, which is already known for algorithms, yeah, for discrete time. That there is an extension of the OPR lemma, yeah, where the limit of the norm with respect to a variable metric, or let's say introduced by a matrix, can be considered.
Oh, okay.
Like the norm must be not fixed, yeah? And the norm can depend. Okay,
yes,
okay,
yes.
Let's say can depend, yeah, on the index of iteration.
Yeah.
And this is already known for algorithms, and then it was just natural to extend this OPR lemma result to the continuous time setting, and you can find the proof in our paper.
Okay, okay, okay. But it is the one kind of the big assumption, because it is depending on the metric.
Yes.
Yes. Okay, okay.
But this is very helpful, in particular when considering.
Of course. This is essential tools for the handling the situation.
Yes, I agree.
Okay, thank you again. If there are other questions, comments, remarks, it seems there are not. So in this case, let's thank again the speaker, Professor Botz, for this very interesting talk on the primal dual methods in dynamical systems. And for the next talk, it's my pleasure to pass the floor to the next chairperson, Professor Sorin-Mihai from Vienna or from Paris, I don't know.
Yes, Professor Glad.
From Paris now, I guess. We moved to Paris.
Okay, thank you, Adrian, for passing me the microphone. Shall we start now or wait 5 minutes until official
If the speaker is ready, then I think there is no point waiting.
Okay, then we can start.
The speaker is ready.
The speaker is ready. Okay, then, so it is my pleasure to introduce Professor Pierre Maréchal from Paul Sabatier University in Toulouse, who is a well-known researcher in optimization inverse problems. Before allowing him to present his work, some facts from his biography. So he took his PhD in 1997 at the same university, after which he worked at Simon Fraser University in Vancouver, University of Montpellier, and until this year at École Polytechnique Fédérale de Lausanne. And now, as I said, he's working in Toulouse at Paul Sabatier University. So please prepare the slides, and after that we can start. We have like 30 minutes plus, 1 to 3 minutes from from this break, so to say.
Thank you for the kind introduction. I will try to share my okay, trying to find how to to share my slides. Is this okay?
Yes, we are seeing a list of your files. So maybe you should open the.
Do you see now the presentation?
No, just the list of files. I think it's your folder for this conference, so to say.
Maybe I should do this again. Okay, so I should choose a window. Now maybe this one. What? How about now?
Still nothing. I see just the faces of some participants. Still nothing. Just some faces.
I don't really know how to do that. Can you give me some advice?
Sir,
Okay, so please.
on your screen, are you seeing this arrow at the right side of the on your screen?
Below there are some
below the screen. Below there are some symbols. At the there is a symbol of the hand
and after that,
and that arrow.
Just below the pictures, below the faces of the participants. I think something is coming. It's again the list of files from your.
Again, sir, if you click on the link, if you click on that link or that list, then maybe we'll get to see the PDF because your screen is visible now.
So I click on present now, right?
Yes, sir. Present now, and either present the whole screen or a window, but to present your window only, just first open your PDF in any document.
I think I will try with the whole screen, and then I'll see what I get.
Yes, sir. Yes, sir. If you
How about now? Is it okay?
No, it's
not yet shared.
It's not shared. It's not.
I have no idea what to do. I'm sorry.
So, can I show you by sharing my screen?
Yes.
So, whether my screen is visible?
It is the same thing.
So
actually, sir has shared.
And, maybe if you open the so you can see on your screen your presentation.
And open your presentation, sir. Open your presentation.
Yes. It's actually on my main screen now.
Strange. Because you still see only the content of your folder.
Yes, sir.
Strange.
Close the sharing and again share through my window. Megha, you share the slides. Our team will share the slides, sir. Please wait.
So if it is okay for you, then I can share a screen for you, sir. So
yes, I sent my slides to Professor Moy just before, so maybe it's better.
Yeah. Okay, sure, sir. Sure. So is it visible?
Yeah.
I can see the slides.
Okay, so now I'm doing it on full screen.
Okay, thank you very much for doing it for me. I don't know why it was not I was not allowed to authorize sharing the screen for some reason which I don't understand. Okay, so first of all, I should say that I'm very pleased to participate in this conference. And I want in particular to thank Tan Moy Som for his very kind invitation. I'm going to present a work that was done in collaboration with my colleague from Grenoble, Fauzi Triki, and also my student, Walter Cédric Simo-Taole, former student, because now he has obtained his PhD last year. So the subject is about the regularization of a Cauchy problem for the inhomogeneous Helmholtz equation. Can you go on, please? So I will briefly introduce the problem first, So we consider the following PDE system. Next, please. And you can go down because every symbol will be explained. So you consider V to be a domain, a bounded domain with a C31 boundary. Nu denotes the outward unit normal vector to the boundary of V. Gamma is a non-empty subset of the boundary of V. And the unknown of the problem is U. It's the amplitude of the incident field. And here, eta denotes the refraction index, which in this study is not assumed to be constant. Okay, K is a positive wave number. And so the data of the problem is the source that is given. And assumed to be a member of L2 space, as well as the boundary conditions F and G. Next, please. So now the Helmholtz equation arises in a large range of applications related to the propagation of acoustic and electromagnetic waves. And here we consider the inverse problem of reconstructing the fields from partial data given on an open part of the boundary of the domain. So this problem is called the Cauchy problem for the Helmholtz equation, and it turns out to be ill-posed in the case where gamma, the locus where we get the boundary conditions, does not occupy the whole boundary of the domain V. Next, please. This problem was considered in the particular case where the refraction index, eta, is constant by colleagues from Ho Chi Minh. And unfortunately, the techniques they used, which also referred to modification, could not be extended to the case where eta is not constant. In fact, the sense they give to modification is the sense that goes back to works around Murillo, in which modification was applied to the data prior to inversion. We will focus here essentially on the variational acception of the word modification, which is much more flexible and which allows to use the same concept of regularization by modification in contexts that are more difficult and more intricate. Next, please. So our functional setting is the following. The Laplacian is a bounded operator from H2 to L2. Therefore, we have a first component in the data, which is encoded by operator T1, which is just the sum of the Laplacian and the multiplication operator by K2 eta, which is therefore a bounded operator from H2 of V to L2 of V. Now, if we consider the second component, the one that is related to the normal derivative of U, we also have an operator that is compact from H2 of V to L2 of gamma. Gamma is let me remind you that gamma is the subset of the boundary of V where we acquire data. And the third component of our forward operator, let's say, is T3, which just takes the restriction of U to this subset gamma. And again, we have a compact operator from H2 to L2. Next, please. Next, please. Yes. So we will work in the functional space H2 of V, and in fact, our system takes the operator form Tu equals V, in which T is just the concatenation of the three components, T1, T2, and T3 that we just visited in the previous slide. And the data now is the triplet SFG, which is a member of what we will denote in the sequel by capital G, which is merely the Cartesian product of L2 of V by L2 of gamma, and again by L2 of gamma. And it is a standard result that the linear map T is also an injective operator. Next, please. So now we'll review a few things about inverse problems, ill-posed inverse problems. After that, we will see what is the principle of modification in the variational form of the term. So we consider now a general ill-posed linear equation, the same type of what we just visited for Helmholtz. Tu equals V, with T being a bounded linear operator from F to G, F and G being separable infinite dimensional Hilbert spaces, and with the particular property that the infimum of Tu for U running through the unit sphere in F is equal to 0. In this case, it is a standard result from the basic theory of ill-posed problem that the pseudo-inverse, which we denote here by T dagger, is only densely defined operator and unfortunately unbounded. Next, please. An iconic example is provided by deconvolution. If you consider a convolution kernel, let's say, for example, in L1 of R, so let's consider the one-dimensional problem, then you may consider the convolution operator T sub gamma, which maps U to gamma convolution U. And if we denote by F the Fourier operator, and make the standard assumption that the Lebesgue measure of the set of points where the Fourier transform of the convolution kernel is equal to 0 is itself equal to 0, then we have an injective operator, convolution operator T gamma. And in fact, it is easy to show using Parseval identity and a few properties of the Fourier transform of L1 functions, in particular the Riemann-Lebesgue lemma, that the previously mentioned infimum is equal to 0 in this case. So we typically have ill-posedness, and we need to apply some regularization. There is a long history now about regularization, and one of the principles I have studied in the last years is what I call the variational form of modification, which I will say a few words about in the next slides. Next, please. So we'll first talk about modifiers. So this is a concept that was introduced in the field of PDEs by Kurt Friedrichs in the 40s. So if you are given a function, a L1 function with integral 1, then you may define what is called an approximate unity in some cases by considering phi alpha of x to be 1 over alpha n phi of x divided by alpha. The integral of phi alpha is the same as that of phi, that is to say 1. And if you let alpha go to 0, this will concentrate the function near the origin. And so this is a way to emulate the Dirac delta function, which is not a function, of course. So a standard theorem from approximation theory, previous please, says that any LP function for p between 1 and infinity can be approximated by its smoothed version, smoothing being understood as by means of the convolution by phi alpha. So we let alpha go to 0, and then we asymptotically converge towards f in any LP norm. So of course we use this for L2, and here the difficulty in inverse problems is that we do not know f. We only know f through an operator, an ill-posed operator equation. Okay, so we would like to do the same as in approximation theory, but in a context where what we learn about f is not f itself, but its image by an operator whose pseudo-inverse isn't bounded. So in this context, the notion of modifier was used by the in a seminal paper by Alfred Lewis and Peter Maas. And this gave rise to a methodology called the approximate inverses, in which they use Hilbert duality to encode this principle. Next, please. In another paper that just before, please, in the previous can you just go backwards just one slide, please? Previous one, yes, stop. Thank you. And at about the same time, slightly before, there was a first occurrence of what I call the variational acception of modification in a paper that was published by André Lannes in the context of signal processing, where in fact the modification was encoded not using Hilbert duality, but using optimization problems in a Hilbert space setting, projection operators. Next, please. So we'll see how to explain this, the heuristics of this methodology. So you consider that your original object that you would like to recover, which we denote here by U naught, is tautologically written as its smooth component C alpha U naught, where C alpha is a convolution operator by the function phi alpha, plus the obvious complement. And we decide that we do not want to deal with high frequencies of the object. So we have somehow an undesired component, which is the identity minus C alpha times U naught. And this suggests to use as a penalty the square norm of I minus C alpha times U. And now, if we assume that we can generate the data corresponding to the desired components, namely C alpha U naught, we may also consider a fit term of the form square norm of V alpha minus TU. Okay, it's not always possible to generate such a V alpha, but in some cases it is possible. So now we can, after having written this, we can look at an overview of the principle of regularization that I am talking about. Next, please. So the regularization scheme goes as follows. We define our target object to be the smooth version of U naught, smoothing by means of the convolution operator by phi alpha. Then we try to generate from the data that we acquired, which is an approximation of T U naught, an approximation V alpha of T C alpha U naught, because it's the new desired component that we are looking for. And then we define the reconstructed object U alpha to be the solution to a compound minimization problem with one fit term, the one that is in purple, and one regularization term, the one that is in blue. And it's very easy to see that the solution to this problem is given by the formula that is right below. And of course, in the theory of inverse problems, we have some requirements. And in particular, we want to study how the solution would behave as the regularization parameter, alpha would go to 0. So I stress here that our regularization parameter has nothing to do with a weight, as it is the case in Tikhonov regularization, the celebrated Tikhonov regularization, just because alpha appears not as a weight. Okay? It's really has something to do with the way we approximate delta, the Dirac distribution. Next, please. Just a remark that, as I said, in some cases it is not possible to generate the regularized, what I call the regularized data, V alpha. But in some cases, we dispose of an explicit operator, which is denoted here by phi alpha, that realizes the intertwining relationship phi alpha t equals t c alpha. In this case, to generate the regularized data is just applying this operator to the raw data V, for the reason that appears in the centered equation. And if it is not the case, if we not dispose of such an operator, I would say the simplest thing to do is to just ignore this step and just use the usual fit term in the regularized functional. So we just do not consider V alpha. We just take V as attached term. Thank you. Next, please. So now we get back to the Helmholtz equation. If we want to follow the idea from the theory of modification in the variational sense which I just outlined, we wish to reconstruct a smooth version of U, namely the convolution of U by some phi alpha. Here we will consider functions phi alpha, which are approximation of unities generated by a given function phi, which we take to satisfy two properties. We can take more properties. We can use smooth functions phi. Here we only require phi to have a support, to be supported in a ball of radius r. And as usual, we want the integral of phi to be equal to 1. Next, please. Thank you. So in the problem of PDEs in general, and in particular in the Helmholtz equation, we have one difficulty, which is that if we convolve U by phi alpha, then we also change the support of the function. I mean, we have to extrapolate U from V to V plus alpha times the ball of radius r. And this difficulty has, in fact, a cure, which consists in introducing an extension operator that will preserve the properties of the solution on V. So we define V alpha to be V union its boundary union what is denoted here by V epsilon plus, which is generated from V by the boundary of V by following the outward normal vector nu over a distance that is epsilon. Okay, so we have somehow V epsilon, which is a thickening of V. Next, please. And now the nice thing is that we can construct an extension operator. We can explicitly construct an extension operator such that with properties that will make our analysis easy. Not easy, but possible, let's say. So if you fix S to be between 0 and 1, any S in between 0 and 1, in particular S equals 0, then you can find an invertible bounded operator E from H2 plus S to H2 plus S naught, where the naught indicates that we consider compactly supported functions in H2 plus S. with the blue sequence of inequalities, in which the constancy depends only on S, on the shape of V, and on the thickening parameter epsilon. And in addition, the support of the extended function is contained in V epsilon, in our thickening. Next, please. So now this definition opens the way to the following variational formulation of modification in the case of our PD system, which consists in minimizing V minus TU, norm square, in G, plus not exactly as we did before, I minus C alpha applied to U, but applied to the extension of U by means of our extension operator. So this variational way of stabilizing the inverse problem has nice properties. First of all, it is a regularization of the ill-posedness feature of the problem, in the sense that the solution to this problem exists and it depends, is unique and depends continuously on the data V. This is the easy part. The more difficult part is to obtain the consistency of this regularization principle, and that is to prove that the solution, the regularized solution U alpha, converges to T dagger V as alpha goes to 0 in some sense. I recall that T dagger is the pseudo inverse of T. Next, please. And in fact, doing some analysis, we were able to prove the following results. So we assume that our modifier, capital phi, has a particular behavior near the origin in the Fourier domain. That is to say that 1 minus phi hat behaves essentially like a power of the argument, of the norm of the argument, the power being S, near the origin in the Fourier domain. And in this case, assuming also that the only place where phi hat is equal to 1 is 0, it never goes back to this value, which is a very mild assumption indeed, then the solution U alpha to the problem P converges strongly to T dagger V in the Sobolev space H2 of V as alpha goes to 0. Just in the next slide, we'll see just a sketch of the proof. So we have essentially 3 steps. The first step consists in showing that U alpha is bounded in H2 of V and therefore weakly compact. In the second step, we show that if we take any sequence alpha n going to 0, we can find a subsequence of U alpha n, let's say U alpha nk, that converges U weakly to U dagger in H2. And in step 3, we use the Frechet-Kolmogorov compactness theorem to show that the convergence is in fact strong. So I just want to notice, to make the remark that the proof is a non-trivial adaptation of a result in a paper going back to 2009, where we studied the variational approach to the inversion of the Fourier truncated Fourier operator. That is to say, the Fourier operator followed by truncation to a bounded domain. Next, please. So just want to finish with a few simulation. We played a little bit with, in particular, with the help of my student Walter Cédric Simon-Taolé. So we did a simulation in a 2-dimensional version of the problem in a rectangular domain. So for numerics, we gave up the regularity, the full regularity of the boundary of V. But applied the same spirit in the regularization. So we face the problem of recovering the solution U for the second variable y being in 0, 1 from data on the boundary corresponding to y equals 0. Next, please. Next, please. Thank you. So just for technicalities, we use a finite difference method of order 2 for the differential operators. We add noise on the data with a normal distribution with 0 mean. And we considered several noise levels. We call that a relative error on the data, RED. The modifier we used is Gaussian. And we, of course, transform the problem into a huge linear system and use the GMRS method on MATLAB to solve the corresponding linear systems. And we use also a selection, a parameter selection rule that is called the discrete quasi-optimality rule, introduced by Bauer and co-authors. Next, please. Next, please. Yes. So in our example, we took the following K and eta, the refraction index, and consider the solution to be given in the last centered equation. And we, after generating the corresponding data and adding the noise, we reconstructing using our modification approach and obtained what is in the next slide, please. Next, please. Yes. So on the no, one before, please. One before, please. Just one before. Yes.
No, next.
Next. Thank you. So on the left, it's the original object, and we see several reconstructions using various levels of noise. Next, please. And in the next table, we see that we compare the values of the relative error on the reconstruction for various layers being indexed by the value in y. And we see that we may multiply the noise by 100, and even in the last row, we have quite reasonable amplification of the noise. So it seems to be numerically a stable approach, and it works nicely in practice, at least for a two-dimensional problem. It would be interesting to move to three-dimensional problems, but we haven't done that yet. So thank you very much for your attention.
So thank you. We thank Professor Maréchal for his interesting talk. And now, because of the time, maybe you have time for one or maybe two short questions. You can raise your hand or just unmute yourself and just ask.
Yeah, one question, please, Professor Rachel.
Yes.
The penalty term you have
Yes.
introduced there. So, what is the maximum limit of penalty term? Suppose it is applicable to some example or some. Okay.
What is the maximal limit?
Yeah, penalty. How much penalty can be given? Can be allowed?
The penalty term is, in fact, the weight is always 1, so we don't change it. We can only change the penalty term by changing alpha. If we take alpha going to 0, then the operator that is in front of EU vanishes, because C alpha gets pointwise very close to the identity. So the way to make the penalty small is to let alpha go to 0. On the opposite side, if you let alpha grow, then the operator C alpha gets away from the identity, and the regularization part takes more importance. And so, of course, we have, as usual, the trade-off to find between the requirement of stability and the requirement of fidelity to the data. So on the one hand, we want to make this this term small, but sometimes we have to make it not so small because of an instability.
Okay.
Okay, thank you. And another short question or another short comment. If anybody can unmute herself or himself and place the question. If I don't see any hands with no. And thank you again, Professor Marechal, for this interesting talk and for the questions.
Sir?
Yes.
Yeah, am I audible, sir?
Yes.
I can hear something.
Sir, actually, I want to ask that what is the meaning of densely defined?
Densely defined means that the pseudo-inverse T dagger is not defined on the whole of the image space, capital G, but only on a dense subspace.
G. I mean, it is a subset of G.
Yes, it is a subspace of G.
Subspace of G, dense.
Yes, it is a dense subspace of G. Yes, the domain of definition of T dagger of the pseudo inverse. Yes.
Okay. Thank you, sir.
You're welcome.
Okay. Thank you. So thank you again, Professor Marechal, for his talk. Also to the colleagues who asked questions. And now I will pass the floor and the microphone to the next chair, to Sahu. And okay, we will introduce my talk. So.
Okay, so I'm stopping this presentation. Thank you, sir. Thank you, everyone.
Okay, and I will try to.
Professor Sahu will chair this session. Next talk, please.
Okay, thank you, Professor Som. It is my pleasure to introduce Professor Sorin-Mihai. He is Professor of Optimization. He was PI at University of Vienna during 2018-2020. He is member of various prestigious societies. He is editorial member of various journals. Particularly, he is associate editor of Optimization, Fixed Point Theory. He has published 2 important books in era of optimization. First one is Duality in Vector Optimization. It was published in 2009. And second one is Vector Optimization in Monotone Operators via Convex Duality. It was published in 2015. So welcome, Professor Sorin, for your talk related to the incremental mirror descent algorithms.
So, thank you very much for introduction. I hope that you can see my slides.
Okay.
Yes.
You can see that I put on full screen, so I don't see myself. I don't see any face. I don't even see the time, so please interrupt me if I'm talking too much.
Okay.
Okay. So first of all, thank you for the introduction, and I also would like to thank the organizers, in particular Professor Som, for the invitation, for insisting that I give a talk at this conference. I also would like to say hello to the colleagues and friends see in the room here. Yes, so I will talk about a joint work with Sandy Bitterly, a PhD student from Chemnitz, who is about to finish her PhD studies. It's about a stochastic incremental mirror descent method for minimizing sums of proper convex LSE functions, where the Nesterov smoothing plays a role. And just to address the comment of Adrian Petrushel before the previous talk, so I'm now at ENSTA Paris. I left Vienna at the end of September. So from the first slide, you can see the motivation, why mirror descent. It's a method introduced by Nemirovsky for minimizing one convex function. And then it was extended for minimizing sums of convex functions. It was extended also to variation inequalities, even to some classes of constant optimization problems. Basically, most of the work with this method has been done for convex differentiable or convex Lipschitz continuous functions. And there are some applications, machine learning, finance, and so on. And on the next slide, you can see our contributions. So we introduced such a stochastic incremental mirror descent method for minimizing a sum of finitely many proper convex LST functions over an unempty closed convex set. Then we extended to compositions with linear operators, and also towards adding to this sum of another function, which is a so-called prox friendly. Let's say one of the changes towards the previous works in the literature is that we don't ask the involved functions to be Lipschitz, continuous, or differentiable. Now you can see some technical details, preliminaries. You don't need now to take notes or to put everything in your memory, because I mean, these are quite technical things. What's important is that you see here the relation 1, which is the Nesterov smoothing. Basically, given a function defined on Rn with extended real values, the function which has this a function which has this particular form, then this one f gamma is the so-called Nesterov smoothing or Nesterov smooth approximation of this function. And when f has this particular form 1, then we have this relation, this chain or double inequality. So the Nesterov approximation, Nesterov smooth approximation, is less than the function itself, but the function is again upper bounded by the smooth approximation plus some constant term. Of course, smooth functions are easier to work with, are handy functions, and the idea would be to replace in some algorithm, in the mirror descent algorithm, the function itself by means of its Nesterov smoothing, so that we still stay convergent in some sense and don't go very far away from the value of the function f. F gamma is the Nesterov smoothing, so of course it's well defined, has nice properties, it's convex, continuously differentiable, and its gradient is fulfilling what you see here on the last line. So it's a nice function to work with, but of course it's we should not forget that the target is to minimize the sum of functions of f's, so to say. On the next slide, you see also some example. One can, of course, ask, we have the formula 1, but which functions are fulfilling it? It looks like a conjugate. So the first, or the classical example goes towards the direction. For a proper convex LST function, we have this formula. And if the domain of f star is bounded, then we have the maximum here attained. So for instance, such functions verify the given formula. And also one can ask, yeah, these technicalities from here, how can one actually feel them in some sense? For this constellation, the Nesterov smoothing is nothing but the Moreau envelope of the composition of G and A, where G is defined like this, so it plays a role in the construction of F. So you can see that this is, let's say, a generalization of the Moreau envelope in a certain sense. On the next slide, again, some technicalities. We will need a bit later the Bregman proximal operator of a function, which is defined here below, is again an extension of the classical prox operator, proximity mapping or proximity operator. But of course, by means of the function h, which is defined again here, proper convex, and by using it, one defines the Bregman distance-like function and also the Bregman distances. But again, there are, let's say, technicalities which allow us to be more flexible and to work in a more general framework. On the next slide, we can already see the first
Excuse me, sir, your slides are not visible.
Not visible.
Sir, your slides are not visible.
Okay, so they were from the beginning or just now?
Just now, just now.
Just now.
Just now. Maybe I'll start sharing again. I did it again.
Yeah, it's visible now. Yeah. Thank you.
It's okay.
Okay, thank you for telling me, because I see just the full screen with my slides and I have no idea what happened. So I presented a slide with the Bregman proximal operator. It's defined here. It's a generalization of the classical proximity or prox operator. And now on the 7th slide, you can see the first problem we are dealing with. Minimize a sum of functions, finitely many M pieces, over a given non-empty convex closed set. And all these functions fulfill the property 1 presented before. Because of this condition, all these functions are proper convex LSC. And of course, the domain feasibility property has to be fulfilled. Otherwise, it has no object, the whole thing. For this problem, we introduce again the technical stuff. As I said, we need here and there some technicalities. In this case, we need a so-called mirror map, which is defined by means of a proper convex, strongly convex function H, capital H. And the mirror map is this gradient of the adjoint operator of the conjugate of H. For instance, when H is the half square norm over C and plus infinity otherwise, the mirror map is exactly the projection onto C. But again, you can see that this mirror map is a generalization of the classical projection. Now the first algorithm is given here as a scheme. Of course, we need some sequences in order to have some flexibility and to move on and so on. What's here very interesting are, let's say, two things. I begin the second one, which is this step here. So after doing something with variables, we use this mirror map in order to come back on the set C, so to be feasible, because again, the problem is minimize a sum of functions over C. And using the mirror map, we are coming back on C to be feasible, because we want to stay there. And as I said, for instance, for this choice of capital H, the mirror map is a projection on C, onto C. So basically this one comes back to C. And I'll come now to the first interesting, at least in my opinion, thing here. There is this line where we advance, we update the variables, the y's, which will be then mirrored on the set C, and the x will be basically this one. With the first variable m. Anyway, so back here you see two particular things. The first of them is the presence of this epsilon, which is a random variable independent of C, which is 0 or 1. It looks like maybe a bit strange, but it's a trick which can be used, let's say, for large scale optimization. If you have like 1 million variables, of course, updating all of them in each iteration would cost a lot of time and lots of resources. And that's why you also saw maybe the word stochastic in the title of my talk. So this is a stochastic step. Basically, we don't update all the variables. we update just some of them, which can be controlled by means of these probabilities given here, the PIs. So let's say if we have 1 million variables, we don't update all of them, we update like 100 or 1000, and the others stay the same. But even so, we still stay convergent in expectation, as we shall see on the next slides. And as I said, we use the Nesterov smoothed approximation of the functions involved, approximations in the plural of the functions involved, because we have here this gradient forward step involving the Nesterov smoothed approximation of fi for each I from 1 to n. So this is the algorithm, the first one. The convergence, as I said, it happens in a sense specific to mirror descent, and also it happens in expectation because of the stochastic steps. So first expectation, and then this is a type of convergence specific to mirror descent, where there are only a few papers when one gets convergence for xk. Usually in this setting or in this type of algorithms, the convergence happens in a sort of ergodic sense by by involving the objective values. So not like, for instance, in the case of Fista, which is okay, not related, but still, in such cases, we don't have convergence of xk's, we have convergence of, in a sense, as you can see here, of the sum of fi's at points xk. On the right-hand side is more or less fixed. Of course, it depends on the involved sequences, but one can use these some standard sequences, or one can fix them. And in that case, one will get a constant right-hand side. Using a result due to a Beck-and-Teboul, one can even get that optimal step size for this algorithm, which you can see here, the choice of the TKs. As I mentioned, the TKs play a role here, here, and here. So for this choice of the TKs, using basically only constant things which were defined or used before, one gets this result, this convergence result, again, in expectation and involving the objective values. So this is the first, let's say, main result. We were motivated, inspired for this work also by a work by Botts and Böhm, and they used for the algorithm not the smoothing, but the subgradients of the involved functions, and they needed Lipschitz continuity. We were able to avoid using Lipschitz continuity in modifying their work, but in that case, we needed this construction of the Nesterov smoothing, so to say. On the next slide, you can see, as announced, an extension towards compositions with linear operators. All these involved functions are now composed with such mappings AIs. And in this case, these operators have to be the ones which allow FIs to fulfill the relation 1 from the beginning. And in order to not overcomplicate the things, we use as a smooth approximation for this composition and the Moreau envelope. Of course, one can use even the general one, the Nesterov one. And the algorithms, the algorithm looks like this. Again, we have the mirroring on the set C, because again, we need to stay feasible. And because of the choice of the smoothing, again, we smooth the functions, the compositions by means of the Moreau envelope. We use this directly, so basically we don't have a gradient, we have directly the result which follows. The gradient of the composition of the smooth approximation of the composition is then this one. Involves the prox operator of the functions fi's at these points, and the adjoint of the linear operator, and again the switch is 1, 0, so on off of these random variables in order to be able to control how many, if you want, how many of the variables or a percentage of the variables which will be updated at each iteration. For this algorithm, there is again a similar convergence result, but we don't have the time now, and of course it will be like a whole slide full of formulas. So we go on to the next problem we considered, which is the previous sum, to which we add a prox-friendly function. Again, the Fi's fulfill the formula 1, but the G function has to be proper convex LSC and prox-friendly, so its prox can be computed. Again, we need some technical assumptions here, and I'll get to the algorithm. As you can see, because of difference of the properties between G and the F's, we get them separately. First of all, we have the same construction for processing the F's by means of their Nesterov smooth approximations. Again, we have the steps 0, 1, the random variables in order to switch on and off. And after that, we have the mirroring on the set C. So in this step here, we basically compress the two steps from the previous algorithms for space reasons. And after finishing with F's, Fi's and the mirroring, we compute the prox of G at this point, and xk goes on. So this is the difference, again, between the algorithm from this problem and the algorithms from the previous problem, from the simpler one without G. So G plays a role, and then it's not processed by means of its Nesterov approximation, Nesterov smooth approximation directly by means of its prox, because again, it's a prox-friendly function. The convergence result, again, it's an expectation because of the random variables, and it's similar to the previous one. So it involves only the sum of the objective value at the point, so the sum of Fi's plus G at the latest point, so to say, at the xk plus 1. And again, also here one can get an optimal step size result. And now we have some applications where we tested the theoretical advances. The first one is a continuous location optimization problem. It was, let's say, borrowed from the paper of Nesterov. We have the classical continuous location of, okay, Nesterov also used it in this context, but of course it's a classical problem. Minimize the weighted sum of some distances where to some certain given point Ci's from X, which X has to stay within a given set, which is a ball in this case of radius R. For such functions using Nesterov's results, we have here those Nesterov smooth approximations, their gradients, and we take H to be the classical 1/2 square norm over S. Here you can see also the picture. So we are looking for a place, for a point X, which best approximates or whose sum of weighted distances to the given points is minimal. The X has to stay within this ball S. And as I said, large scale before, so we used, we tested this for 1 million points. So of course, in reality, maybe you cannot say, yeah, we have, we look for a storage capacity or a storage place such that 1 million of our shops will be optimally delivered from this point, because of course, who has 1 million shops around a certain deposit? But still, this is the, let's say, the easiest interpretation, canonical interpretation of this problem. So we solved this problem in MATLAB, and we got this red curve which represents the objective function values. And we compared with the algorithm of Botsam-Böhm I mentioned before. And you can see that our stochastic incremental smooth version algorithm decreases faster than their algorithm. Not much faster, but still faster. And as I said, the main difference is that we don't require the functions to be Lipschitz. They needed the function to be Lipschitz. So we had, from some point, different constructions. And in case of Lipschitz, the Formula 1 is fulfilled. So that's the extension, if you want, in a certain sense. So we got, for the location problem, such a graph. The objective functional values, in our case, are less than the ones of our colleagues. Did I hear some question or just... Okay, I'll move on. The second, I have 3 applications, so this is the time. So the second application is in tomography, positron emission tomography, a problem which was, for instance, mentioned in a paper by Bental, Margalit, and Nemirovsky, and it can be represented or modeled like this: minimize over the unit simplex such an entropy type function. Again, you can see here the meanings of these yi's, number of photons, and so on. The mirror map is taken no longer the half of the square norm, but this entropy function, because of course we have entropy here, and it's the most natural, or it's more natural to work with this mirror map. And the procs of the involved functions, the proxies, fulfill such a formula. So technical things. On the next slide, you can see the results in dimension 1000 for 6000 beams. Again, we compared our result with the one, or our objective values with the one from the paper of Botsam-Böhm. You can see that we are a bit faster in order to, so after a certain time, like 8 seconds or 10 seconds, our objective value is below theirs. So again, it's a minimization problem. We want to minimize, so it's better to be as low as possible, because of course we need to minimize such a function. And we also compared here by changing dimensions. So here above you can see dimension 1000 and 6000 beams. For 15,000 beams and dimension 5000, the tendency stays, but the curves are more regular, more round if you want. So in the, again, 1000 dimension, we have these curves which are not very, very nice if you want, but if you increase dimensions on the numbers of functions, then you get nicer curves. And last but not least, we have also an application in machine learning. So it's a support vector machine image classification. I'll show you here the intuitive first, the intuitive phenomenon. One has handwritten digits, twos and fives, and of course, me or you or anybody from the room, from this conference could say, okay, this is a 2, this is a 5, this is a 5, a 5, and so on. But the computer doesn't have our experience, so it has to be taught in order to differentiate between 2s and 5s. And we have training images and test images of the size and so on. So again, technical things. The problem can be modeled like this: minimize this construction. And in this case, we use the last algorithm because this function is the G, and these are the Fi's from our previous scheme. Again, the mirror map is the half of the squared norm. And again, you have the technical results here, the proxies of the functions involved and so on, which are known from a paper by Rosweiss. And here you can see the curves. In this case, the curves are more or less similar. So our algorithm performs, you cannot hear it, slightly better than the one of our colleagues. And in order to find another criterion, we looked at the percentage of misclassified objects. And you can see here that our algorithm misclassified less objects, so less digits, slightly less, of course. The decrease in misclassification is not that dramatic, but still we have, so we were, let's say, more accurate, a bit more accurate for different types of the parameters than the previous algorithm. And one last idea, what we are planning to do next is work on, where is this? On this algorithm, in order to add to it not one, but two or more proxy functions, and also to add here some composition with a linear operator. And that's it from my side. I thank you very much for your attention. And of course, the floor is now. So the mic goes to the chairman.
Thank you. Thank you very much, Professor Great, for the nice talk regarding the optimization problem. I think it is the big data optimization, and it is particularly related to machine learning. And you have given the nice applications of the descent algorithms, I mean the incremental descent algorithms in machine learning. You have already covered the convergence rate analysis.
Sorry, I don't understand the question. I hear some radio or something in some background. So,
there is some parallel session, I think.
Sorry, can you please repeat the?
Anyway, I will ask.
Yes. So, can you please repeat the question, because I couldn't understand.
Any comments and questions from the audience?
Okay. I thought that you have a question. Sorry.
It was really a wonderful talk. Certainly, some are actually they are not putting question. It is very unfortunate. I thought somebody will ask.
At the last, I would like to ask the one point that what is the role of the mirror mapping? What will be the connection? Just a moment. What will be the connection between the minimizer of the minimization problem and some properties of the mirror map?
So the role of the mirror map, I hope you can see it, is to come back on the feasible set. So maybe it's better here. So we do something and we have to be again in the set C. So the mirror map comes back to the set C. So the mirror map is in such a situation is the projection. And then it's a generalization of the projection. So the idea is that it comes back on the set C in order to stay feasible.
Okay.
And the function h, which defines this mirror map, has to fulfill something which is connected to the problem here. So it's the set C is the closure of its domain, and it's the image of its the gradient of the conjugate has to be included in the intersection of the domains of the FIs. But basically, this is these conditions are the only ones imposed on H. Otherwise, H can be whatever.
One can take the H the gradient of H identity.
The gradient of H is the H star is the projection in this particular case. Identity, I don't know. Actually, no, I don't know. It's a good question.
Okay.
It's a good question. So
I am thinking that there will be the connection of the solution of the optimization problem with some kind of the variational inequality problem also.
Maybe.
Yes. Okay. Anyway, really nice talk on the applications of the optimization problem in the machine learning. Thank you. Thank you, Professor Sorin, for the talk.
Thank again the audience, and also thank you for the questions. And okay, you have the floor, so thank you again.
Okay. Okay. Thank you, Professor Som, for giving me opportunity for sharing.
Thank you, Professor Sahu and Professor Sorin, for a very nice and illuminating talk, and Professor Sahu for chairing the session. Now I hand over. So these are the talks. This evening session talk is not yet over. We have another session little late evening by Professor B.S. Chaudhary. Before that, we have paper reading. So there are two parallel sessions of paper reading. One is already going on. So this is paper reading on fixed point theory to be chaired by Dr. M. Saha.
Good evening, sir.
Yeah, please. Dr.
Good evening, sir.
Good evening. Good evening.
Thank you. So how are you, sir?
It's fine.
Okay. So can I start? Am I audible
Yes,
to you?
you can start. There are about how many? You have the list, I think.
Yes, I have got the list, and I think that there are 10 numbers of participants, right?
Yeah. Maybe one more. I have probably one. Last one is who?
The last one is Obhik Digar.
Okay. After that, one more will be there.
Okay.
We will send you. Okay, we'll send you.
Okay.
Dr. Vandana Tiwari, you just add that one. Yeah.
Sir, she's already added in the list.
Okay, it is all right. Please continue.
Okay. So thank you, Professor Som, and thank you for the for inviting me, for giving me an opportunity to chair this session. Thank you, Professor Som, and on behalf myself, first of all, I would like to thank each and every one of the organizers. Okay, thank you. So it is my duty to chair the session. So there are 10 numbers of participants, and I think that all are present. The first speaker, Yao-T Wong. The first speaker, Yao-T Wong.
Okay, I'm here.
Okay. So your time now starts. So we'll get 15 minutes. So within the 15 minutes, you have to finish, and that is 13 minutes and 2 minutes for introduction. Okay.
Okay. I can give my speech.
Yes, you can start.
Okay. Let me share my screen. Could everyone see my screen?
Yes.
Thank you, everyone.
Yes, everything is visible.
Okay, I will give my speech.
Yes, you start.
Right, I will give a speech about the linear angle preserver of Hilbert bundles. This is Yalta form. And first we define the angle of xy belong to the interval from 0 to pi/2. The vector xy in real or complex Hilbert space H is defined by the following condition. The inner product, absolute value of inner product is equal to ln of x times ln of y times the cosine of angle xy. If x and y is 0, then the angle is understood to be any value in the interval from 0 to pi/2. Let T is a minor mag and from H to K, and we can use the polar identity for the complex case or for the real case. And we can see that when T preserve inner products, then T will be isometry. In particular, a scale apparently auto-catched isometry preserve angles. And we have questions about, do angle preserver arise from isometry? We have a theorem 1.
for any two fixed angles, theta and phi belong to the interval from 0 to pi over 2, but not include 0. No real linear map T is a positive scale multiple of an asymmetry if and only if the angle of xy equals theta implies the angle of tx ty equals to phi. In this case, we must have theta equals phi. We have proved for a special case when theta equals phi equals pi over 2. The x and y belong to H, and the sum known equals 1. Let lambda be the unimodular scale such that lambda times inner product of xy equals at the value of inner product of xy. Then we have the inner product of s lambda s plus y and lambda s minus y equals 0. And by the condition of the theory, we have it then follows lambda tx plus ty and lambda tx minus ty equals 0. And consequently, we have the questions. And equating the real part, we see that the ln of tx and equals to ln of ty. And consequently, we have 1 over alpha times t is an asymmetry. And the real case is even easier. Next, we will show the balance bundles, a real or complex balance bundle over a local compact host of X. The balance bundle is a pair Bx pi x in which Bx is a topological space and pi x is a continuous open subjective map from Bx onto X and satisfying the following conditions. The first, for X, the fiber Bx equals to the inverse of pi x carry a balance space structure with the long topology agreed in with the subspace topology. And the second, the scale multiplication, addition, and the long on Bx are all continuous whenever they are defined. And third, if X belongs to X and Bi is annate in S such that the norm of Bi approach to 0 and pi Bi approach to X, then we have Bi approach to element of Bx. And we call a balance bundles Hilbert bundles if all Bx are Hilbert space. Now we consider the balance space of continuous vector sections from X to Bs, and the function is continuous and vanishing in the infinity. We denote with C0 X Bs. And we see that the condition 3 ensure that the zero section is in C0 X Bs. For Hilbert bundles Hx pi x over a locally compact space X, the balance space C0x Hx of continuous vector section form a Hilbert C0x modular with modular multiplication. Alpha f in X equals to alpha x times fx, or alpha belong to 0x and then or f belong to 0x Hx. And the C0x inner product is defined by following. Moreover, we define the absolute value of f. So we conversely, if H is the Hilbert C0 modular, then there is a Hilbert bundle Hx types such that the equivalence hold. We show the linear M-God preserve of Hilbert bundles. We see elements in Hilbert bundles or equivalently a C0x modular H a continuous vector section from a fiber Hilbert space Hx. Then the angle between F and G we can naturally consider as the continuous field by x to cosine inverse reflection whenever defined. And we have a formal definition. The X be a locally compact space and the H be a Hilbert C0 X modular. A continuous scale function U belong to CS with U in the interval 0 to 1 is said to be the cosine of an angle between F and G, and write by amusing notation cosine of angle F and G equals U if the question holds. My caution is such a U assumed to be arbitrary or multiple value whenever F absolute value of F or absolute value of G vanish. And we define the modular map. A linear map T from H to K between Hilbert A modulus is a modular map if T of FA equals TF times A, for F belong to H and A belong to A. And number 3, let H and K be two Hilbert C0 modular. A linear map from H to K is a modular map if I know if there is a fiber linear map TS from HX to fiber KS such that TF in X equals to TS of Fx for H for F it belong to H. And we have the important theory. Let T from H to K be a complex linear local map between two full Hilbert C0x modular with degenerate range. Suppose that U and V are continuous function on S with U and V in an interval from 0 to 1, but not include 1. And cosine of angle of L and G equals to U implies cosine of angle of TF/TG equals V for F and G belong to H. Then we have 3 conclusions. The first, that U and V, the two continuous functions, will be equal. And the second, T can be represented as alpha times J. For alpha is a continuous function, strictly positive bounded continuous function. And J is a subjective modular isometry from H to K. And now we work on a linear angle preserver between Hilbert C star modular over different commutative C star algebra C of X and the C of Y. The X and Y are different. Let T from H to K be a by JT complex linear map from a complex Hilbert 0x modular H into a complex Hilbert 0y modular K, and we say T is a coincidental if the following is whole. The support of T inverse belong to the support of F. For F belong to H, and for beta prime belong to 0y. And it's clear that if X equals Y and T is an 0x modular map, then T is coincidental as TF beta prime equals T of F beta prime. And now we have an important theory about a different space. Let H from H to K be a by JT complex linear map from a full compressible serial modular onto a full compressible serial Y modular K. Here X and Y are different, and such that the both T and T inverse are coincidental. And suppose that U belong to Cx continuous function on X, and V belong to Cy, the continuous function on Y, such that U and V are in the interval from 0 to 1, but not including 1. And cosine of angle of TF and TG equals U if and only if cosine of angle F and G equals V, for F and G belong to H. Then there is a homeomorphism phi from Y into X, and the weighted function alpha belong to C. Bounded continuous function Y away from 0, and the unitary fiber mass JY from KY into H phi Y, such that TF in Y equal to the alpha Y times JY of F phi Y, for F belong to H and for Y belong to Y. Thus, T can be represented as alpha times J for subject T isometry. Or J will be equal to the direct sum of the JY for Y belong to Y. Thank you, everybody. That's all my speech. Thank you.
Thank you, Dr. Tuang. Thank you for your nice presentation. So, is there anybody for having some queries from Professor Wong? Is there any queries from the audience?
Yeah.
Is there any query? Hello, is there any query from the audience?
And I finished there.
Okay, so actually, Dr. Huang, I have some queries. Okay.
Yes.
Yes. So, can we define the it is the orthogonality or orthonormality in such Hilbert bundles or Hilbert modules? Can we define orthogonality or orthonormality?
Define what?
Now, my question is that whenever you define the product, inner product like that, so can we define the orthogonality of vectors or orthonormality of vectors? So have you understood my question?
Maybe I can make a comment. This is a general theory about angle preserver, and the angle including right angle. So orthogonality is special case of the result. So when you x equals 0, that means the angle is right angle. So in this case, that means the vector section are orthogonal to each other. So this result include as a special case orthogonality preserver, and orthogonal preserver is already done a long time ago in other papers. So this extension of this orthogonal preserver. Yeah.
So my other question is that are the two Hilbert modules are isometrically isomorphic? Are the two Hilbert modules or Hilbert bundles?
Sorry, I think the speaker may understanding your question. Well, depend on the structure of the linear preserver. If the preserver is bijective, then the underlying Hilbert bundle are isomorphic. But if the operator T can be non-injective or non-surjective. So in this case, the underlying Hilbert bundle are not isomorphic, but maybe there's some embedding. The embedding is an isometrical embedding. This his result say.
Okay, so can the capital M, that is the square integrable functions LP space, are the Hilbert modules or Banach modules?
The journal theorem can be extended to the Banach bundle, but in the Banach bundle case, it's not easy to define the angle. So the angle between a section in Banach space is not well-defined concept. So, but for Hilbert bundle, it's easier to say. So this presentation is emphasize on the Hilbert space part.
Okay, thank you. Okay, thank you, Mr. Wong.
Thank you.
Now I invite the next speaker, Rita Paul.
Yeah, I am here.
Okay.
Yeah, good evening, everyone.
Yes, good evening.
Yeah, let me present my screen. So I think, is it visible to you all?
Yes, it is visible.
Yeah. I am Rita Pal from Mumbai University. Gives me immense pleasure to present my paper in front of you all. And the topic of my paper is that application of fixed point theorem in digital metric space. And the topics which I have included in this today's presentation are abstract introduction, literature review, main result, and then after that application, and then conclusion, and then last reference is also mentioned over there. So now in abstract, that is in research paper, some fixed point theorems for digital images. So the main purpose of the paper is to present another generalization of the well-known Banach contraction principle for digital images. So the basic concepts about the digital images and an application of fixed point theorem to compression of digital images and fractal image compression are mentioned over there. So in the introduction part, I have included that is Banach contraction principle, that is a very well-known. So for that, I have described here for that SBA mapping from a complete metric space XT into itself, which satisfies the distance of SSX SSY is less than equals to alpha times of distance of XY for all XY belongs to X, where alpha lies between 0 and n. So in this case, the S has a unique fixed point, which is already reference, that is in 12. It is given in that reference. And then now I come to that topology is the study of geometrical and topological properties of digital images. So the topological fixed point theory involves the study of spaces with the fixed point property. So in topology, generally we consider infinitely many points in arbitrary small neighborhood of a point. To consider finite number of points in a neighborhood, the concept of digital topology was introduced by Rosenfeld, that is given in the reference 13 number. So in fact, digital is using geometric and algebraic topology. So digital topology is the study of topological properties of image arrays. The results provide a sound mathematical basis for image processing operations such as image thinning, border following, contour filling, and object counting. So basically the digital images have been used in computer science such as image processing, computer graphics. Digital topology also provides a mathematical basis for image processing operations. So further, digital topology is a developing area in 2D and 3D digital images. So basically I have used that paper, that is Egg and Karta, which I have taken as a reference to define a digital metric space and prove the Banach contraction principle for digital images. So in this paper, we introduce contractions and contractive mappings on digital metric spaces. So we prove the existence and uniqueness of fixed point in digital metric spaces. So now that literature review, it is given like this. So these are the definitions and propositions which I have used. Now come to the main result, that is theorem. So now here that is X is a digital metric space defined is mapping from X to X. Suppose distance of txy is less than equals to theta times of distance of xy for all xy belongs to X, then T is called a digital theta contraction, then T has unique fixed point. So here I have proved this one, let x0 belongs to x and suppose xn plus 1 that is equals to xn for n equals to 0, 1, 2, 3 up to. So we suppose that xn is not equals to xn plus 1 for n equals to 0, 1, 2. So otherwise xn is a fixed point. So here I have proved by this using this one. Now this lemma is also used. Now the next theorem is that that is x is determinant T is a mapping from x to x such that distance of txy is less than or c times of mu xy for all xy belongs to x and x is not equals to y, where mu xy that is equals to maximum of half of distance of y ty 1 plus distance of tx. That is the theorem for this. And then here also I have proved that T has a unique fixed point. Now the main thing is that the application of fixed point theorem to digital images. So in this section we discuss the application of fixed point theorem that we have proved in the fractal geometry has attracted the attention of many mathematicians. So Mandler first considered the term fractal. So roughly a fractal is a geometrical shape, every part of which is a reduced copy of the whole. So the following are the examples of fractals. So many real world objects such as coastlines, mountains, trees, clouds are approximated by using fractals. So many real world objects such as coastlines, mountains, trees, clouds are approximately by using fractals. Now in 17th, they initiated the theory of iterated function system. So Barnsley first recognized the potential of the fractals for the image compression and applied the theory of IFS. And it has been observed that all the images in nature contains a considerable amount of. So the affine redundancy means the large segment of the image look like the small segment of the same image. So large segments are known as the domain blocks, whereas small segments are range blocks. So we can find an affine transformation that transfers a domain block to the suitable range block. So the parameters of the transfer constitute a fractal code. So thus a range block is approximated by applying an affine transformation was suitable to choose a domain block. Since the mapping reduces the size of the domain block, it is a contractive mapping. So now fractal image compression works as follows. So first one is that image is partitioned into non-overlapping range blocks. Generally, the partition of an image may have an arbitrary shape, that is square, rectangles, triangle, quadrilaterals, or any polygon. So now the second, that is the same image is partitioned into overlapping domain blocks. So domain blocks are larger in size than the range block in order to maintain contractive condition. Third one is that finally the image is enclosed by using a suitable affine transformation which maps a domain block to a best fitted range block. Fourth one is that to achieve the decompression, exactly the opposite is done. So inverse affine transfer is applied to recover the image. The iteration starts with an arbitrary image, successive application of the affine map which gives the sequence of images that ultimately converges to a fixed image. So thus the contractive mapping and fixed point theorem is at the core of the fractal image compression. Important aspect of the fractal image decoding is resolution independence. So that means if you comprise a 128 image that decompresses to in size of say 64 to 60 or 256 by 250. So fractal image compression produces better reconstructed image than that of JPEG. So original file is that of 103 size byte and it is compressed to an image of 996 bytes in 5 seconds. So these are the figure that I have taken. So the conclusion is that our purpose is to give the digital version of Banach fixed point theorem by introducing theta contractive type mapping. So these results are the application of fixed point theorem in digital metric space. It will be useful for digital topology and fixed point theory. So in the future, we will also use the fixed point theory to solve some problems in digital images. And these are the references which I have used while making the paper.
Thank you, Dr. Paul, for your nice presentation. So, is there any questions from the audience?
I think some questions should be there. Okay, I could not go properly or talk anyway, presentation. So, digital image. Okay, digital fixed point means what? Can you just...
Yeah, here that is contractive mapping I have defined, and then fixed point theorem concepts I have used over here.
So how it is related to, say, any digital, say, any image?
Yeah, like that here I have described about that.
Okay, these are the application of fixed point, I know.
Yeah.
Now, how you are going to tackle
say the problem which we are talking about.
Yeah, for that sub coding is also applicable. So still I am working on that.
So which particular theorem you are going to use here?
That is our first
Or
theorem,
concept.
that is 3.1.
Is this basically the iteration process you are interested, or convergence, or what type of thing you are actually dealing with?
Yeah, that is convergence also.
Okay, convergence. Certainly convergence. Oh, these are some simple. Where you are applying these results and how you are applying. These are only two questions.
Yeah, for digital images and for fractal images.
Hello.
Yes, sir.
This is the nice application of the contraction principle. Just I would like to know one thing, that what is your contribution in your presentation? What is your work? Do you have some work here, or this is just the beginning of the some fundamentals?
Sir, I have derived that theorem.
Which theorem?
Related with that digital. First, I have defined that contractive mapping in digital metric space, and then I have proved that fixed point theorem on that.
How this digital metric space is different from normal metric space?
Yes, sir. For that, here definition I have given.
Okay. Maybe in future you will.
Yeah, that is X is
so
a
many
subset
things.
of Z and D with a Euclidean metric on Z to the power. So XD is a metric space. Suppose X beta is a digital image with beta adjacency, then XD beta is called a digital metric space. So first I have defined this one. And then after that, it is defined in digital, that is a Cauchy sequence.
Okay, we'll see later because we have other presenters. Okay, fine. It's a good initiative. Certainly, I think you will get something more. We will get something more from you later.
Okay, thank you, sir.
Okay, thank you. So, Dr. Paul, I have some question. Suppose I think that that is the image distance and pre-image distance. That is the digital images.
Yes,
will be in the some ratio. That is less than some constant, right?
Okay, sir.
So if we take the sequences of mappings, and each and one have a fixed points.
Okay.
So could you get a single mapping that converts to that same point? Suppose you are given a mapping T1, T2, T3, and all in a digital metric space. So each and every one mapping has a fixed point. Suppose if we get the Ti converges to another mapping.
Yes, sir.
So does this mapping T have the same fixed point? That is the point. That is also have a fixed point under the same conditions, and that numbers of fixed points in terms of the sequence of operators that converge to the same point of the under the mapping T.
Yes, sir. So in that sense, we will collectively we can think about the union of mappings like that.
Later we shall discuss. So it is not. It is not clear to me. So let's see. So have you any? So are there any works of the recent works? Are the digital metric space images?
No, sir. Yeah, I am working on that, sir.
Okay. So have you published any paper?
Yeah, for not on that is different fixed point theorems. I had in different spaces. I have published.
Actually, I think that the proofs are very parallel to the classical proofs, the Banach context. I think so.
Yes, sir. Yes, sir.
So proofs are not different. Just x theta, x d, and theta. Theta is a parameter, d is the metric, and image under the mapping. Right. So the proofs are going in parallel way. Okay, whatever. So it is a good initiative. So let's see and let's hope for the best. Okay.
Okay, sir. Thank you, sir.
Next speaker, K. Mahalik. K. Malik. Hello. Next speaker.
Hello.
K.
Hello, sir.
Malik.
Yes,
Hello,
sir.
are
I'm
you
here.
here?
Yes, sir. I'm here.
Okay, okay. Please start your presentation.
Yes, sir. Okay. Good evening to all. Myself Kartik Malik from Department of Mathematics, IIT Kharagpur. This evening, I will present this article entitled as Solvability of System of Implicitly Generalized Order Complementarity Problems. So, these are my outlines of my presentations. So before talking about any problem, we have to know whether that problem actually exists, whether the solution of that problem is exist. That particular thing should be known. So that is called existence theory. So anything you do with the problem, before that you have to first study its existence. So here we will study some sort of existence theory of order complementarity problem, and there are different methods, different techniques to study existence results of complementary problem. But here we will study the existence theory of complementarity problem through topological degree aspects. So what actually complementary problem is? So in fact, we know optimization problem. So what actual optimization problem is? The optimization problem, we have objective functions and we have some sort of constant sets, but we are not dealing with that. What we are doing here, we will do the analysis of constant sets, like product of two constant sets are going to 0, or in some sort of, we can say inner product of constant sets are going to 0. That particular conditions are actually called complementarity conditions, right? So here we don't need objective functions, we only discuss the analysis of constant. So like here, it's very classical problem. It's called complementary problem of a non-linear type. So here what is happening here, we have to find out such x0 which belongs to this Rn plus, and the functions may be continuous, may not be, such that this particular condition is going to be 0, right? This particular thing is complementarity condition. You can think it is also inner product type of thing. Like in inner product space, you can say 1 0 0 1, that is complement to each other, right? So later these things are generalized to linear complemented problem, where we deal with a linear functions, like here L x0 plus q belongs to K star. K star is a dual cone of a particular cone, like here K is closed convex cone, and duality of a cone is defined as here, and here this particular condition is going to satisfy. This particular conditions is known as complementarity conditions. And Smith actually give a new approach called exceptional family of elements to study the complementary problem. Okay. Let's discuss some notation. I need a Banach space first of all. Banach space. I need a closed convex pointed cone, and I need a order, which is order is simple definitions like reflexive, antisymmetric, and transitive also. And this cone can induce a natural relations if I set my order in this way, and this vice versa. If the order can be also induced from a cone, we can say that if it is invariant order translations, scaling, and continuity. These are the usual notations of analysis. So now I have Banach space and I attach with a cone. I will tell this triplet as order Banach space, and in the order Banach space, with my supremum with respect to the order and infimum with respect to the order, if exists for any arbitrary element I will take from the space X, then that particular space is called vector lattice. And in the entire discussion, our space is a vector lattice. We suppose that. And here some literatures I want to introduce here. So this is called order complementary problem, studied by Brown and Dempster. This particular problem is called order complementary problem, and this is an infimum of two constant. We can say that it's going to 0, right? And 0 is anyway the element from the space X, 0 element. And here f is linear. F is just assume linear. If f is non-linear, then it's a nonlinear order complementary problem. G. Isaac also studied this particular problem called nonlinear order complementary problem. And here fi are in this fashion. Fi x minus ta and t are nonlinear mappings. Later, this particular problem also considered by Isaac and Kostrup. And this particular version problem is this particular problem is called generalized order complementary problem. You can think it's 2. Now it is generalized to up to m functions. Okay. So now this is also this particular problem is also called implicit generalized order complementary problem, and it was discussed by goal 11D. Right. So now these are very old problems. Now we can generalize this problem to some sort of, say, to multi-value mapping. These functions, if you set these functions f from x to x such that this f are in this fashion, but t I just mapping from x to 2 to x. So now the functions are multi-valued. So we can also deal with this problem. This problem also discussed in the literatures. So now in 2011, Nimit first give the existence theory of order complementary problem by using Larry's order alternatives and order exponential family of element. What actually order exponential family of element? That is this is the definitions. The definition is that sequence of element satisfy this particular two conditions. One condition is the norm of XR is going to be infinity, and this particular conditions set of, right. This if this condition satisfied, then we say that this family of elements is order exponential family of element. Later, let us see. This is just set up of problems of m functions we have. But here, Java APL consider the system of a complementary problem. Right? It is to find out such y star z star so that this particular condition satisfied. Right? So we can and here Java also suggests this particular existence theory by using the order exponential family of elements. So now there are more literature also. Fang YPT also studies some system of implicit generalized order complementary problem. So now I need some definition. Completely continuous. Usual definitions of operator theory. So topological degree, I want to introduce this thing. So I need a C1 functions, and I need a n-dimensional space, that is Rn. Here I define a point P called a regular value if j of x is not equal to 0. J of x is the Jacobian of f, and this is not equal to 0 at the points where P satisfied P I can induce. I mean it is not equal to 0 for all x belongs to f inverse P, and f inverse P is the points where I will generate P if I apply f. Right. So this Jacobian, right? So Jacobian you can find out because this function from Rn to Rn. So Jacobian you can find out. Right. Right. So for this particular, if this condition is satisfied, then we say that this P is actually a regular value. And in fact, if P is a regular value, we can define degree of a functions f that is in this fashion, summation of signal function of Jacobian of fx, and x is calculated in the form of x are from f inverse P. Right. As far as the signal function is concerned, one can think it is an integer because signal function has three values: 1, 0, and -1. Right. So it is an integer. So this is an example. We can think it is the degree of a functions from R to R defined as this one. And if I take P equal to 0, and we check that this P is regular value, and if this is a regular value, then we can find out its its degree. So what actually it means? It means that I have 2 points inside D, which gives me 0 if we'll apply the points on F by F, right? So number of elements inside D is 2 to which generates the value 0. Right. So the existence of this particular definition is actually proved in nonlinear analysis. So this is also when it is negative. If I make the sense of rotations, then that time it may come as negative. So this is on finite dimensional space. So in fact, we can also generalize this concept to infinite dimensional space. So these are some theory. I don't want to go inside this. So these are some other theorems. Suppose if the mapping is a homotopy, then that time the degree is going to be constant, right? So if the functions in place of function, if I set a homotopy, then if I calculate the degrees, then that time is constant. And this is also another theorem. This is called Kosten-Koch theorems, and this is called identity theorem. If I put my identity functions, so there is only one possibility. So that's why the degree is going to be 1 here. So my work. So this is my work. So I want to discuss this problem. So this is we call it system of implicit generalized or a complementary problem, and for this I need m functions mapping from Cartesian product of x plus x to x, right? So I need it. So for that I have to find out such y star z belongs to s cross x, and s is here a non-empty closed convex set. So this thing going to search why I'm interested in this problem. I'm interested because if I set this particular substitutions, then I will all previous literatures can be induced, right? But all previous literatures deal with very classical method of nonlinear analysis. They studied the existing results in the classical theories, but what I'm doing here, I will use topological degree method to deal with the existing results, and this is the main results here. So this results is suggested my problem has any solutions, or it has an order exponential family of elements. So it is an alternative way we can think it. So it has either we did it partially. We can think it. So it has either solutions or it has order exponential family of elements. So from the theorem one can see that it's easy to derive that. If anyway I will prove that it has no order exponential family of element, then I will conclude that it has solutions, right? So at what time it has no order exponential family of elements. So if I put this condition 1, right, this particular conditions, right, or this particular conditions, these two conditions gives me that it has no order exponential family of element. In fact, if it has no order exponential family of elements, we can say that it has a solutions, right? So these are the proof are available. So these are certain. So actually, in fact, the results of limit can be derived from our results, right? The result of Zhao et al. Also, the results can be derived from our results also. Results of Pang y et al. Partially, we can say we can deduce the results of Pang y et al. Right? And this is an example to convince the main results. The example is a little bit constructive here, and we take the space here Rn with p nums, and we take the product space Rn as Rn and the p num product num in this way, right? And we set all this S, C, and all these are set it accordingly, right? So at the end, all the things are satisfied with the main results. That's why you can say that it has also an impact. One can check that 0, 0 is a solution here. So there is a comparison here, which is Zhao et al. Results. So 0 is not required in our case. I don't need 0 in S. There is no advantage. And in Zhao et al. Results, this particular conditions is actually needed for index 1 to m. But I don't need that. I need a very weaker conditions. Right, I need only for index m, only one index I need, right? So this is an advantage, right? And so these are some conclusions, right? So there are possibly hope for future research. All the things are mapping from x cross x to x, So we can make it to express x to 2 to power x. That will be appear as set value, right? That is one possible research, and we need more sufficient conditions so that we don't have other external family of element by which we can say that it has solutions, right? So we are talking about solutions. It means uniqueness is a thing to research at what time and what condition I will supply, so that I will generate unique solutions. That is also a future hope. And we are not discussing anything about how to find out solutions. That is also one thing, possible thing to research, how to find out solution. That is also some sort of research problem. So this entire discussion can be found out in this particular article, solving the system of increases general and complementary problem, right?
Yes,
And
sir.
so
Hello.
and the
Hi, I'm coming.
right. So these are my reference.
Hello, sir.
Thank you. Thank you.
Hello, Mr. Malik. You have a nice presentation. Is there any questions? Is there any question from the participants? Is there any question? Hello, Mr. Malik. I have a question. So
Yes,
actually, you have used the degree theory, topological degree theory. Initially, whenever the soda fixed point theorem, power spin fixed point theorem, degree theory was used, right?
Yes, sir.
So there is a very good connection between the implicit functions results and fixed point theory, right? So could we get the results of the simultaneous fixed point theorem or coincidence point theorem with this supposition, with the assumptions, whatever we assumed here?
So not exactly, but to some extent we can say that. Not all things we derived here, but to some extent we can say that that thing here may be possible. We can say that.
Okay, so whatever you have defined on the mappings, either they are the continuous or discontinuous. So could we get the same result for the discontinuous mappings?
So here I use actually completely continuous, right? So it means
that is the compact operator. Just compact
yes.
operators, right? There is every bounded set maps into relatively compact set, right? Because there is compact.
Yes, sir.
So if we drop that this just is there any kind just I am assuming
actually, if you drop that, I actually use these theorems, actually this point pair whole theorems, and this particular theorem to apply this, I need completely continuity. So I think I can drop that one, right?
So we can drop it, right?
No, we can't drop it. We cannot, because I need completely continuity. So
actually, these conditions are sufficient. So are the conditions necessary?
Conditions are necessary. I don't know, but I think.
So if not, so you should have you any counter example?
Example one can produce, but right now I don't have example. But these are necessary conditions. These are you are talking about necessary conditions, so we can handle that thing by some other ways, maybe.
So if you think so that it is a necessary condition, so why haven't you proved the results as if and only part? So just I am saying that only one part is given, so other part is not given.
Yes, exactly. That may be considered to a research way. I will consider that thing. I will think of that.
Okay, thank you very much. Thank you, sir.
Thank you, sir.
So the next speaker is Muhammad Asad.
Hello, sir.
Yes.
Good evening, sir.
Good evening.
Is my screen visible?
Not yet.
Is my screen visible?
Now it's visible. Now it's visible.
Okay.
You are good to go.
This side Muhammad Asad from Department of Applied Mathematics, Faculty of Engineering and Technology, Aligarh Muslim University, Aligarh. Today Topic of this talk is strong convergence algorithm for the split problem of variation inclusion, split generalized equilibrium problem, and fixed point problem. This talk consists 6 sections: abstract, introduction, preliminaries, main result, numerical discussion, and references. Now we start with abstract. The purpose of this paper is to recommend an iterative scheme to approximate a common element of the solution set of the split problem of variation inclusions, split generalized equilibrium problem, and fixed point problem from non-expensive mappings. We prove that the sequences generated by the recommended iterative scheme strongly converge to a common element of the solution set of stated problems. At the end, we provide a numerical example to support and justify our main result. Now come to the next section, which is introduction. We start with introducing some necessary notations. Let H1 and H2 be two real Hilbert spaces, and C and Q be the non-empty closed and convex subset of H1 and H2 respectively. Let us define some basic definitions. Tau Lipschitzian mapping. A mapping F from H1 to H1 is called tau Lipschitzian if there exists a constant tau greater than or equal to 0 such that this inequality hold for all xy in H1. Non-expansive mapping. A mapping U from H1 to H1 is said to be non-expansive if this inequality hold for all xy in H1. The solution set of non-expansive mapping U is defined by this equation: fix U is equal to x in H1 such that Ux is equal to x. Strongly positive mapping. A mapping A from H1 to H1 is called a strongly positive mapping if there exists a constant zeta positive such that this inequality holds for all x in H1. Now define problem. Problem 1. In 1994, Sensor and Fink proposed a split feasibility problem in the finite dimensional space, which could be characterized as find x in C and Ax in Q. Due to its vast application in science and engineering, such as signal processing, image reconstruction, medical specialties, engineering, geophysics, etc., much attention is paid to this problem. Also, problem 1 is strongly related to some general problems like the convex feasibility problem, the multiple site split feasibility problem, the split feasibility problem, and the common fixed point problem. The solution set of split feasibility problem is denoted by gamma is equal to x in C such that Ax in Q. For finding a solution to problem 1, Bayanni proposed CQ algorithm, which is formulated as follows. CQ algorithm: take any x0 in H1, define xm plus 1 by this equation for all m greater than or equal to 0. Here PC and PQ denote the projection operators on C and Q respectively. Afterwards, several different techniques were proposed to solve the problem 1. In 2013, Zhu et al. Proposed the following problem, which is defined by problem 2, where U and V are non-extreme mappings on C and Q respectively. Under some appropriate conditions, the sequence generated by their algorithm converges strongly to an element of the solution set of problem 2. Let E1 and E2 be two multi-valued mappings with non-empty values, and let F and G be two mappings. Inspired by the work of Sensor et al., Mudafi proposed the following split monotone variation inclusion problem defined by 3 and 4. Under some acceptable conditions, Mudafi proved that the sequence generated by his algorithm converges weakly to a solution of the problem 3 and 4. Inspired by the work of Mudafi, Ansari and Rehan considered the following problem defined by 5 and 6. Under some suitable conditions, they proved the weak convergence of their algorithm. If we take f and g is equal to 0, the problem 5 and 6 reduces to the following split variation inclusion problem, in short SVIP, defined by 7 and 8. The solution set of problems 7 and 8 is denoted by solve E1 and solve E2. In the past few years, many authors have studied and found solution for SVIP. In 2018, Maji et al. Considered the following SVIP and fixed point problem defined by problem 9. They define a sequence XM as follows defined by algorithm 1. Also, they establish a strong convergence of their scheme under some appropriate conditions. Now define problem 10. Let G from C cross C to R be a nonlinear bifunction. An equilibrium problem is to find a point P in P bar in C such that this inequality 10 holds. The solution set of problem 10 is denoted by EPG Takahashi proposed an iterative method to find a common element of the solution set of problem 10 and the solution set of fixed point problem of a non-expansive mapping in a Hilbert space, which is defined by algorithm 2. Obtaining motivation from the work of Marino and Zhu and Takahashi, Fleming and Pumping proposed a general iterative method to find a common element of solution set of problem 10 and a fixed point problem for a non-expansive mapping in a Hilbert space, which is defined by algorithm 3. Under some acceptable conditions of sequence sigma n and Rm, they proved that the sequence generated by their algorithm converges strongly to the unique solution of the variational inequality problem defined by 11. To find a common element of solution set for AP10 and a fixed point problem for a finite family of mu strictly pseudo-contractive mappings, Peng et al. Introduced the following iterative scheme defined by algorithm 4. Modafi introduced the following split equilibrium problem defined by 12 and 13, where G1 and G2 are the nonlinear bifunction and A is a bounded linear operator. In 2017, Maggi et al. Considered the following split generalized equilibrium problem defined by 14 and 15. They denote the solution set of problem 14 and 15 by S is equal to P in EPG1 phi 1 and such that AP in EPG2 phi 2, where EPG1 phi 1 is the solution set of problem 14 and EPG2 phi 2 is the solution set of problem 15. Further, they define a sequence XM by algorithm 5. Maggi et al. Established the strong convergence of their same under some appropriate conditions. Motivated and inspired by the above-mentioned works, we suggest and study an iterative scheme to approximate a common element for the solution set of split variation inclusion problem 9, split generalized equilibrium problem 14 and 15, and a fixed point problem for non-expansive mapping in a real Hilbert space. Also, we prove a strong convergence of the iterative method we used, which is prudent than weak convergence. Further, we provide a numerical example to support and justify our work. These are some preliminaries which we use throughout this paper. Definition, lemmas, semi-closeness principle. These are some assumptions for bifunctions G. Now come to the main section, main result. In this section, we define our algorithm and provide its convergence analysis. Suppose H1 has to be two real Hilbert spaces, let C and Q be two non-empty closed and convex subset of H1 and H2 respectively.
So, a little interruption, Mohammed. Sir, can you conclude it a little early?
Yeah, definitely. Let G1 phi 1 G2 phi 2 be nonlinear bifunctions satisfying assumption 1, phi 1 phi 2 be monotone and G2 be upper semi-continuous in the first argument. Assumption 1, A1, A2, A3, A4, A5, A6, B1, B2, B3. Supposing the assumption 2, A1 to B3 are satisfied, we suggest the following algorithm to approximate a common element for the solution set of SVIP 9, SDAP 14, 15 and a fixed point problem in a real Hilbert space. Algorithm 6. This is our main algorithm. Then the sequence XM strongly converges to P star in F, which is a unique solution of the following variational inequality problem 26. Now, theorem 1. Let P in F, then the sequence XM, WM, FXM, and WWM generated by algorithm 6 are bounded. Theorem 2. Let P in F and XM be the sequences generated by the algorithm 6, then A and B hold. Theorem 3. The sequence XM generated by algorithm 6 strongly converges to P star, which is a unique solution of the variation equality problem 26. This is a numerical. This is a numerical table showing the convergence of our result. The graphical representation of the convergence of our algorithm. These are the references that we use throughout this work. Thank you.
Thank you, Mr. Rashad. Is there any questions from the participants? Is there any question? So since there is no question, so I think.
Thank you, sir.
So your business is finished.
Okay, thank you, sir.
Okay.
Thank
The
you.
next speaker is Tirth Ram.
Yes, sir. I am here, sir.
Okay. Hello.
Yes, sir. Yes, sir. My
Please
screen.
start.
Yes, screen is visual, sir.
Yes, visible.
So, good evening, everyone. The topic of my paper is on non-smooth univax functions and vector variation-like inequality. In this paper, we established the relationship between vector variation-like inequality problem and vector optimization problems under non-smooth univax functions. We also identify the vector critical points, the weakly efficient points, and the solutions of non-smooth weak vector variation-like inequality problem. So, this is the overview of my paper. Introduction, preliminaries, a relationship between non-smooth vector variation-like inequality problems and vector optimization problems. Conclusion, and finally, I have presented the references. In 1980, Gyanasi established the notion of vector variation-like inequality, vector variation inequality. The concept of pre-univax functions, univax function, and pseudo-univax functions was introduced by Vector as a generalization of univax functions. Preliminaries. In this section, we recall some notions of non-smooth analysis. Suppose Rn be a n-dimensional Euclidean space. This is Rn positive is a non-negative orthogon. The following stipulations for equalities and inequalities will be used throughout this paper. If xy belongs to Rn, then we define this inequality and inequality. A function f is said to be Lipschitz near x in x if this norm is less than or equal to k times norm of y minus z for some k positive and for all yz within a neighborhood of x. We say that this function f is locally Lipschitz on x if it is Lipschitz near any point on x. Next definition, suppose f is a Lipschitz at x in x, the generalized directional derivative in case of Clark at x in the direction of v is denoted by this symbol f naught xv and is defined as provided this limit of this supremum exists. The Clark generalized subdifferential of f at x is denoted by this symbol delta fx and is defined as follows: del fx set of all xi in Rn satisfying this inequality. These definition and properties can be extended to a locally Lipschitz vector valued function. The Clark generalized subdifferential of f at x is this set delta fx, product of the subdifferential. Suppose x be a subset of Rn, then x is said to be in vex set with respect to eta if this conditions satisfied for all xu in x. The non-differentiable function f is univex with respect to eta, phi, and v if this inequality is satisfied for every xi I in this subdifferential. The non-differentiable function f is said to be strictly univex with respect to eta if this inequality is strict. It is said to be pseudo-univex with respect to eta, phi, and v if this is less than 0 implies this part also less than or equal to 0 for every xi I. Every invex function is univex where phi can be defined but not conversely. For this we have this example. Suppose f be a real valued function defined by this fx equal to x3 and b and eta defined in this way. Suppose f be defined by phi t equal to 3t, then the function f defined above is univex but not invex because for x equal to -3 u equal to 1, this is less than this inner product. Every convex function is univex, where phi can be defined in this way, but not conversely. For this, we have the example. The function considered in example 9 is univex, but not convex, because for these value of x and u, this inequality, the conditions for convexity. Now consider the following non-smooth vector optimization problem. Minimize this function such that x in x, where fi are non-differentiable locally Lipschitz functions. Given an open set x and a function f, a point z in x is said to be efficient if and only if there exists no y in x satisfying this inequality, these conditions. It is said to be weakly efficient if this inequality is strict. A vector variation-like inequality problem for non-smooth case is to find a point y in x, and for any xi in this, there is no x in x satisfying this. Moreover, big vector variation-like inequality for big case of vector variation-like inequality, this inequality is strictly less than 0. Now next, a relationship between non-smooth vector variation-like inequality problem and a vector optimization problem. Suppose f be a locally Lipschitz and univex function with respect to eta, phi, and b, with phi t less than or equal to 0 whenever t less than or equal to 0. If y is a solution of a vector variation-like inequality, then y is also an efficient solution to non-smooth vector optimization problem. Next, suppose f be a locally Lipschitz and minus f is a strictly univex function with respect to eta, phi, and b with this condition. If y is a weak efficient solution to non-smooth vector optimization problem, then y is also solution of vector variation-like inequality problem with respect to same eta, phi, and b. As every efficient solution is also weakly efficient solution to non-smooth vector optimization problem, the following result is trivial to prove. Suppose f be a locally Lipschitz and minus f is a strictly univex function with respect to eta, phi, and b with this condition. So if y is an efficient solution to non-smooth vector optimization problem, then y is also solution of vector variation-like inequality problem with respect to same eta, phi, and b. Suppose f be a locally Lipschitz and pseudo-univex function with respect to eta, phi, and b satisfying this. If y is a solution of a weak vector variation-like inequality problem, then y is also a solution of then y is a weakly efficient solution of non-smooth vector optimization problem. Suppose f be a locally Lipschitz and a strictly univex function with respect to eta, phi, and b with this condition. If y is a weak efficient solution to non-smooth vector optimization problem, then it is also efficient solution to non-smooth vector optimization problems. We need the following definitions and lemma. A feasible solution is said to be vectorial critical point to non-smooth vector optimization problem if there is a vector lambda in RP with lambda greater than or equal to 0 satisfying this condition. So this is the Gordon theorem. If A is m by m matrix, then we have either Ax is less than 0 for some x, or this inner product equal to 0 for some non-zero y in Rn, but not both. Suppose by be a vector critical point to the non-smooth vector optimization, and suppose f is a pseudo univax on x with respect to eta phi and b with this condition, then by is a weakly efficient solution to the non-smooth vector optimization problem. Now all vector critical points are weakly efficient solutions to the non-smooth vector optimization problem if and only if f is a pseudo univax on x with respect to eta phi and b with this. The following corollary can relate the vector critical points to the solution of weak vector variation like inequality problem using theorem 17 and 22. Let f be a locally Lipschitz and pseudo univax function with respect to eta phi and b with phi t less than equal to 0 whenever t less than equal to 0. Then the vector critical points, the weakly efficient points, and the solution of weak vector variation like inequality problems are equivalent. So conclusion, in this paper, we introduce the concept of non-smooth univax function as a generalization of invax function and discussed the relationship between vector variation like inequality problems and vector optimization problems under univax functions. We have also established that the vector critical points, the weakly efficient points, and the solution of weak vector variation like inequality problems are equivalent under pseudo univexity assumptions. Finally, I have presented the references. Thank you.
Okay, thank you, Mr. Tithuram.
Jesus.
So is there any question from the audience? Is there any question? No. So since there is no questions, let us have a big thank to Mr. Tithuram. Now I invite Sikhar Sharma. Yes, Sharma.
Yes. Thank you, Professor.
Yes. Please start your presentation. So we are so late. So we have to start the next session at 7:30. So please hurry up.
Is my screen visible?
Hello.
Is my screen visible?
Hello. So anything is not visible. So your presentation is not visible. Do you like to share your presentation? Hello.
Yes. I shared my.
Hello.
It is not visible.
Hello.
Hello.
Ajay, you send it to the conference. Acha, now it is coming.
Okay. Okay. Now is it visible?
Okay. Good evening, everyone. Myself, Sikhar Sharma. I'm going to present my paper started with splitting algorithms for solving inclusion problems on Herman manifold with application. These are the outlines of my presentation. First, we start with introduction. Inclusion problem. The inclusion problem is to find x belongs to C such that x belongs to A inverse 0. There is a self-valued operator defined on a Hilbert space. And the basic inclusion problem is to find x belongs to C such that x belongs to A plus B inverse 0. To find the solution of problem 2, it is equivalent to find the fixed point of the map J lambda AB defined by 3. In 2007, Agbal and Kao introduced the assertion method. Later in 2011, Kao introduced the normal assertion method. Due to applicability and better performance of assertion and normal assertion, in 2020, Sahu proposed forward-backward splitting algorithm for solving the inclusion problem with the setting up Herman manifold. Algorithm 4 is assertion-based forward-backward splitting algorithm, and algorithm 5 is Now, excitation-based forward-backward filtering algorithm. The last decade, several years from relay cases and extended to the manifolds. In 2017, Pereira considered the inclusion problem for a sum of two vector fields in the setting of manifold H follows. To find the solution of 6 is equivalent to find the 6th point of the map J lambda AB, where J lambda is a determinant of the vector field A. In 2019, Al-Hamoudin, Ansari, and Babu proposed the Mann-based forward-backward splitting algorithm defined by Sesion. These are the basic concepts from the remaining manifold. It is a differentiable manifold M. The remaining metric is called remaining manifold. A complete, simply connected remaining manifold of non-positive suction curvature is called a Hadamard manifold. Proposition 2.1 describes the relation between basic and exponential map on Hadamard manifold. If subset C of a Hadamard manifold is set with geodesic convex, the geodesic segment joining 2 points in that set lies in that set. This is the definition of the convex function. The projection of PC by defined by 8. Proposition 2.2 describes the geodesic connectivity of the remaining distance function, which is defined by 9. This is a very important theorem in Hadamard manifold, comparison theorem for triangles. For x by z belongs to M and B belongs to TPM, inequality 13 will always hold. Lemma 4 describes the relation between geodesic triangle and triangles in R2. For a set value vector field A, we call it monotone if this inequality satisfies. We call it strongly monotone if this inequality satisfies, and maximum monotone if this inequality satisfies. For a single value vector field A, we call it LHH if inequality 14 holds, and we call it eta inverse strongly monotone if 15 holds. For a set value vector field A, its resolvent is defined by 16. For a real valued function defined on a manifold, its direction derivative is defined by dfu, and its gradient is defined by grad f. For a tight differentiable function, if its Hessian is bounded, then the gradient vector field will be Lipschitz continuous. For a real valued function defined on M, its subdifferential is defined by 17. For a real value function, if it is low semi-continuous geodesic convex, then this subdifferential will always be a maximum monotone vector field. For a eta inverse strongly monotone vector field, the mapping defined by G lambda V is a non-extensive mapping. The set of all singularities of A plus B is noted by A plus B inverse 0. Therefore, our main problem is to find that X star belongs to M, such that X star belongs to A plus B inverse 0. Proposition 2.10 says that to find the solution of Bayesian inclusion problem in Hadamard manifold is equivalent to find the 6th point of the map J lambda AB. Lemma 14 is the resolvent identity in the sense of Hadamard manifold. For a closed geodesic convex subset C, if A is a maximum monotone vector field, P is a eta inverse strongly monotone vector field, and Xn is a bounded sequence, then inequality 20 will hold. To prove our convergence analysis, for the convergence analysis, we have used the following approach called the leaf point property. That is the limit existence property defined by D1 and approximate fixed point property defined by D2. This is a closed subset of a Hadamard manifold. If Xn is a sequence satisfying the leaf point property and our map T is a non-constant mapping, then the sequence Xn will converge to a fixed point of map T, fixed point of the map T. We introduced the forward-backward splitting algorithm based on excitation techniques and their convergence analysis in this section. This algorithm 3.1 is S iteration based forward backward splitting algorithm. And algorithm 3.2 is normal S iteration based forward backward splitting algorithm. To prove the theorem 16, we have used proposition 3.1. Theorem 16 is our main theorem. Let C be a non-empty closed geodesic convex subset of a Hadamard manifold, and A be a maximum monotone vector field, B be a eta inverse strongly monotone vector field, and X1 is a sequence generated by algorithm 3.1. Then this sequence action converges strongly to a fixed solution of problem at T with assumption on parameters. And similarly, for the algorithm 3.2, the sequence action converges to the problem at T with these assumptions on parameters. To test the behavior of a proposed algorithm, we provided numerical examples. Let R3 is the positive arcane in R3. If we consider a matrix on R3 defined by GXUB, where GX is the matrix defined by this, then this R3 is a Riemannian manifold. And for this Riemannian manifold, geodesic is defined by gamma xt. And exponential maps are defined by this, and distance function is defined by this. The parallel transport for this Riemannian manifold is defined by P by X. We consider the inverse strongly monotone vector field B, which is 1/4 inverse strongly monotone, and maximum monotone vector field A. For this maximum monotone vector field A, the resolvent is defined by J lambda X, which is equal to this. This is the graph of the performance analysis of our algorithm and previous algorithm. Clearly, we can see that normal iteration method is faster than other two. This is a comparison table for the Mann iteration, S iteration, and normal iteration. Clearly, we can see that normal iteration method for this example terminate at D35, S iteration at D40, and Mann iteration is not terminated up to 50. For the application part, we give application to the composite minimization problem. That is to find the minimization of the sum of two convex functions. The minimization problem 24 is equivalent to Bayesian collision problem 25. For this composite minimization problem, our algorithm shapes into 26. In the place of A, we have used maximum monotone vector field del F, and in the place of B, we have used single valued vector field gradient F. This is theorem for this algorithm, and this is algorithm based on normal iteration method for composite minimization problem, and this is convergence algorithm for this algorithm. These are the references. Thank you.
Thank you, Mr. Sharma. Is there any questions from the participants? Mr. Sharma, what is the motivation for such type of the works?
So, motivation is that in real life, not every space is linear. So we have to jump into non-linear spaces. So one of them is K0 spaces, Hadamard manifold. So we have chosen Hadamard manifold.
Okay. So I've seen the numerical table, the rate of convergence, Mann iterations, intermon iterations, S iterations, and so the last iteration, what I will say that the iteration scheme is very fast, right?
Yes.
There is normal S iteration, right?
Yes.
Okay. So is there any applications in differential equations or integral equations in this approach as an application?
No, yet I have not seen any application in differential equation, but I have seen its application in image processing.
Image processing.
But I have no idea how to apply it.
Okay, so actually the iteration scheme, there is you are taking monitoration. So what about the Picard's iteration? If we employ what type the Picard iteration? So have you seen?
Picard iteration is very restrictive. If we consider non-functional mapping, then sometimes it fails. So our motive is to prove this algorithm for non-functional mapping. So sometimes Picard iteration fails to converge.
Okay. So the conditions assuming the theorems are sufficient. So could you provide any are the conditions necessary?
What, sir?
The conditions assumed in proving the theorems are sufficient, right?
Yes, sir.
So are the conditions necessary?
No, not necessary.
So if not so, could you give any counter example?
No, I don't. Not.
Okay, thank you.
Thank you.
Next speaker is M.U. Thiroshala.
Yes, sir.
Yes. Please start your presentation.
स्नेहा बोल दो स्नेहा तुम्हारा भी में
Hello.
Hello.
Hello. Actually, I just want to say that Sneha, are you here?
Yes, ma'am.
Actually, your talk is in session B.
Okay, in session B.
Yes. Your talk is in session B, so please join that link. Okay.
Okay. Yeah, okay.
Thank you.
Is my visible the screen?
Hello.
So is my visible my screen?
No, it is not visible.
Okay, sir. Visible, sir?
No. Right now it is coming, I hope. No, it is not visible. Yes, coming.
Visible, sir?
Yes.
Okay, sir. Good evening, sir. My name is Mumbai. I'm presenting a research paper, which title name is Inertial Krasnodesky Man-type iterative method for finding a common solution of hierarchical fixed point problem and split monotone Vachier inclusion problem. Presented by me, Department of Applied Mathematics, Zakir Hussain College and Engineering Technology, Aligarh Muslim University, Aligarh. This outline is contain 8 sections. Now come to the abstract. Abstract is the primary goal of this paper is to present and study an inertial Krasnodesky man-type iterative method to approximate a common solution of a split monotone Vachier inclusion problem and hierarchical fixed point problem of a finite family of k strictly pseudo-contractive non-self mappings. Furthermore, we show that the sequences generated by the proposed iterative method converges weakly to a common solution of these problems. The method and results presented in this paper extend and unify certain recent known results in this field. Finally, a numerical example is used to demonstrate the convergence and analysis of the sequences generated by the proposed iterative method. Now come to the introduction. Let H1 and H2 be two real hypotheses with the inner product is represented by this symbol and the induced norm which is represented by this symbol. Let C is a subset of H1 and D is a subset of H2 be two non-empty closed and convex sets. Definition 1. A non-self mappings T from C to H1 is said to be K strictly pseudo-contractive if there exists a constant K which belongs to close 0 open 1 in such a way that satisfies this inequality. And definition 2. A mapping from H1 to H2 is said to be monotone if inner product Tu minus Tv, U minus V is greater than or equal to 0 for all UV belong to H1. Definition 3. T is said to be alpha inverse strongly monotone if there exists alpha is greater than 0 such that satisfies this inequality for all UV belong to H1. Definition 4. T is said to be non-expansive if norm of Tu minus Tv is less than or equal to norm of U minus V for all UV belong to H1. T is said to be perfectly non-extensive if satisfied this inequality for all UV belong to H1. Definition 6. A multivalued mapping M is called monotone if for all U1, U2 belong to H1, V1 belong to MU1, and V2 belong to MU2 such that inner product U1, U1 minus U2's V1 minus V2 is greater than or equal to 0. A monotone mapping M is maximal. The graph of F is defined by GM is not adequately included in the graph of any other monotone mappings. Remark, it is commonly known that a monotone mapping M is maximal if and only for U1 V1 in H1 times H1. Inner product U1 minus U2 V1 minus V2 is greater than 0 for each U2 V2 in graph of M implies that V1 belongs to MU1. Definition 7. Let M be a multivalued maximal monotone mapping, then the resolvent operator from H1 to H1 is defined by 1. For some lambda 1 is greater than 0, where I denotes for identity operator on H1, we notice that for all lambda is greater than 0, the resolvent operator J is single valued, non-expansive, and firmly non-expansive. Definition 8. A mapping T is from H1 to H2 is said to be average mapping if there exists some number alpha in 0, 1 such that T is equal to 1 minus alpha I, alpha S, where I is the identity mapping and S is non-expansive mapping. And average mapping is also a non-expansive mapping and fix of S is equal to fix of T. Definition 9. A sequence M of maximal monotone mappings defined on H1 is said to be graph convergent to M if sequence of graph of MM converges to graph M in the Kuratowski-Penley sense, which is defined by 2. Now come to the problem. Fixed point problem FPP for a mapping T is defined as find U in C in such a way that E to U is equal to E. U. The solution set of fixed point problem is denoted by fix of T. For a finite family of k-strictly pseudo-contact mappings Ti from C to H1 such that intersection of finite family of fix of T is not equal to 5. With respect to the non-expansive mappings S, we consider the hierarchical fixed point problem in short HFPP as follows by 4. We denote the solution set of HPP 4 by 5. If we take Ti is equal to T, then HFFP is reduced to the following hierarchical fixed point problem, which is defined by 5. For non-expansive mapping T with regards to another non-expansive mappings S, which is proposed in 2006 by Modafi and Myang, it can be easily seen that solving hierarchical fixed point problem is similar to the solved fixed point problem, which is defined by 6. Assume the solution set of hierarchical fixed point problem 5 by 5.1. Modafi proposed the Krasnodebski man-type algorithm to solve the hierarchical fixed point problem 5 as follows. For a given x not belong to C, the sequence xm generated by 7, where alpha and time are two sequences in open 0, 1, some algorithm in signal processing and image reconstruction may be represented at Krasnodebski man-type algorithm, and the fundamental characteristics of its associate convergence theorem provides an uniform frame for analyzing various concrete algorithms. On the other hand, Modafi proposed the split monotone variation inclusion problem as follows by defined by 8 and 9, where M and N2 are multivalued maximal monotone mappings, F1 and F2 are two mappings, and A is boundary linear operator. The solution set of split monotone variation inclusion problem 8 and 9 is denoted by omega. Modafi proposed an iterative method and studied the weak convergence theorem for split monotone variation inclusion 8, 9 as follows. For a given x not belong to H1, compute iterative sequence xm generated by 10. where U and W is defined by this, and gamma in 0, 1 by L. L is being spectral radius of operator A star A. A star is the adjoint operator of A. The split feasibility problem, split zero problem, split fixed point problem, split Bayesian equality problem are a special case of split monotone Bayesian inclusion problem. They have been analyzed by a number of authors and solved real-life problems such as essentially in modeling of inverse problem, sensor networks in computerized tomography, data compression, and radiation therapy. Khamsi et al. Proposed an iterative method as follows for a given x0 in C, compute iterative sequence xm generated by 11, where U and W defined by this and ST are non-extended self mappings on C. Step size is gamma 1. Under some certain conditions, the sequence xm generated by 11 converges weakly to common solution of hierarchical fixed point problem 5 and split monotone Bayesian inclusion problem 8, 9. The convergence rate of cross-sectional SQ type iterative method is slow in general. In particular, the term theta m xm minus xm minus 1, also known as inertial extrapolation term, was introduced as a useful tool for spreading up the convergence rate of iterative methods, and many authors have investigated and improved the inertial type algorithm in various forms. Motivated and inspired by the work of Modafi and Khamsi et al., we proposed and analyzed an initial rationalistical man-type iterative method with the help of average mappings for finding a common solution of SMVIP 89 and HSVP4 for a finite family of k-strictly pseudo-contractive non-self mappings in the setting of real Hilbert space. Furthermore, we showed that the sequences generated by our proposed iterative method converges weakly to common solution of these problems. The iterative method and results discussed in this article are new and can be considered as a generalization and refinement of the previously published work in this field. These are premises which used in the proof of the main result. One is important lemma, demi-closeness principle. Assume that T is non-extensive self-mapping of a closed convex subset C of a Hilbert space H1. If T has a fixed point, then I minus T is demi-closed. Such that whenever xm is a sequence in C weakly converges to some U in C, and sequence I minus T xm converges strongly to some U in C, then I minus T U is equal to U. Now come to the next section, main result. In this section, we prove a weak convergence theorem based on proposed iterative method to approximate a common solution of HFPP and split SMVIP 89 of a finite family of k-strictly pseudo-contractive non-self mappings in real Hilbert space. Theorem: let H1 and H2 be two real Hilbert spaces and C and D be non-empty closed and convex subset of H1 and H2 respectively. Let A from H1 to H2 be a bounded linear operator with its adjoint operator A star. Assume that M and N be two multi-valued maximum monotone mappings and F1, F2 be eta 1 and eta 2 inverse strongly monotone mappings respectively. Let S from C to C be non-extensive mappings and Ti from C to H1 be K strictly pseudo-contractive non-self mappings. Assume that J is equal to omega intersection phi. This is a solution set of intersection of two problems. Define a sequence xm is defined by 12, where U and W is defined by this gamma in this interval, Ti defined by this inequality delta I m belong to 0, 1 for I equal to 1 to n. Let alpha m tau m be two real sequences in 0, 1. Vm is a set of closed 0, V for some V belong to close 0, 1 open and lambda 1 belong to open 0 alpha, where alpha 2 times minimum of eta 1, eta 2. Also, the following conditions are satisfied: first, second, and third. Then the sequence xm converges weakly to x star in solution set J, which is a common solution of two problems. Next is corollary. In algorithm 13, we replace finite mapping of this with single mapping T is non-extensive mapping, and some condition are removed, and also satisfy the condition first, second, and third. Then the sequence XM converts weakly to solution set. These numerical examples. We give a numerical example which justify the theorem. We suppose H1 and H2 the set of real numbers, C and D is in the open closed interval 0, open infinity. Let M and define mu is equal to 3u and N is defined by N u is equal to 5u. F and Fu 2u and F2 is equal to 4u. For lambda 1 is equal to, we can compute that u and w, and these are some mappings which is defined by this. And it is easy to check T1 and T2 are 0 strictly pseudo-quantitative mappings, and S is non-extensive, and A is boundary linear operator. A star such that norm of A is equal to norm of A star is equal to 9 by 4. We can see that fix of T1 is fix of T is equal to 0, and solution set is this. Therefore, J is equal to omega intersection phi is equal to 0. 0 is the fixed point of intersection problem. This table for algorithm, these are 15 iterations for two another initial values x0 and x1. This is graph which converges to 0. We can compute that from the graph and table, the sequence xm converges to 0. These are references. Thank you.
Thank you, Mr. Kerala, for your nice presentation. Is there any question from the audience? So I have a question, Mr. Kerala.
Yes, sir.
So you have used the Krasnodębski Mann iteration. So if I could use the Krasnodębski type Ishikawa iteration, so is there any significant difference between that type of the results regarding the iteration scheme?
Yes, sir. Yes, sir.
So why have you not used
in our proposed our main result? Wait.
Now, what do you think that regarding the rate of convergence, either
the rate of convergence of our algorithm is spreading up to another result, which is used in this paper. Fastest result in this paper, in my paper.
Actually, what I have seen that in user matrix spaces, so we have seen the Mann iteration, Ishikawa iteration, right? And Krasnodębski, just you have just computing the results just parallel with it, just using this type of the schemes, iteration schemes, right?
Yes, sir. Yes.
So, what is the motivation in taking such type of the problems?
Sir, motivation is that. So, motivation in our algorithm is most generated and previous paper and which used in this paper.
So that's the different aspect. So what type of the applications?
Sir, applications mentioned overall.
Have you got any such applications in using these theorems, your theorems?
Yeah, yes, sir. Yes, sir. Sir, in image reconstruction, signal processing, and inverse problem.
Now, actually, these are the non-expensive instances, the monotone operators. So, using your iteration schemes, have you got any applications? Just I have seen your just only numerical examples.
Sir, only numerical example.
Mm-hmm. Just I have seen a numerical. So, is there any applications?
Sir, applications, but is in this paper I have no application.
Okay. Thank you very much. Thank you for nice presentation. So let us have a big thank to Mr. Kerala.
Yes.
So next speaker is Ukuba Rafat. Ukuba Rafat, are you here?
Yes, sir.
Yes. Please start your presentation. So we are so late. Please start your presentation.
Am I audible to everyone?
Yes, yes, you're audible. Yes, let's start. Hello? 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 Hello, am I audible?
Yes, sir.
So your voice is not audible. Please start. Mr. Ukbar Rafat.
Yes, sir. I'm sharing my screen.
So screen is not coming. Hello?
Yes, sir. My screen is visible to
Yes,
everyone.
yes, I think so. Okay. Okay, start, please.
It is okay, sir?
Yeah, no, right now it is okay. You start.
Good evening, sir. And good evening to everyone. This side Ukbar Rafat from Aligarh Muslim University, presenting the research work on the title Algorithm for Higher Order Rational Inequalities in Hadamard Manifold. This presentation is structured as follows. The first one is abstract, then is introduction, some preliminary results, main result, then references. In the abstract, I describe my work. In the context of Hadamard manifold, we introduce the concept of higher order variational inequality. Then under certain assumptions, we propose and investigate a method for solving higher order variational inequalities. Finally, we suggest a two-step method for solving variational inequalities on Hadamard manifold. The next section, introduction. There has been given a lot of interest in studying variational inequalities and related problems on Riemannian and Hadamard manifold. This framework is useful for the advancement of many fields in non-linear setting. Several ideas and techniques from Euclidean space have been extended and generalized to this non-linear framework of Hadamard manifold, including hyperbolic spaces and geodesics. Some authors like Tang, Chol et al. Have considered the variational inequalities and equilibrium problems on Hadamard manifold. In particular, some study is also going on the existence of the solution of the equilibrium problem under suitable conditions. In this paper, we considered the problem of finding a solution of a new type of variational inequality problem defined on a Hadamard manifold. Although we use the implicit method for solving the variational inequalities on the same Hadamard manifold, we showed that a convergence of this method requires only partially relaxed strongly monotonicity, which is a weaker condition than monotonicity. Our results present the refinement of the previous known results for variational inequalities. We hope that the technique and the idea of this paper may stimulate further research in this area. This is some tools. Let M be a simply connected n-dimensional manifold. For a vector x belongs to M, the tangent space of M at x is denoted by Txm, and the tangent bundle of M by Tm. The union of all such tangent spaces and a vector field A on M is a mapping of M into Tm, which associates to each point x belongs to M, and a vector Ax belongs to Txm. We always assume that M can be endowed with the Riemannian metric to become a Riemannian manifold. The scalar product on Txm is denoted by this, and the associated norm is this. Given a piecewise smooth curve gamma from an interval a comma b to m joining x to y, by using the metric we can define the length also, length of the this map from integral a to b norm of gamma dash t dt. Then for any xy belongs to M, the Riemannian distance dxy, which includes the original topology on M. Then the exponential map. The exponential map is the important tool in the Hadamard manifold, which is defined from a Txm to M at x is defined by exponential at v over x from gamma 1 to x for all vector v belongs to Txn. Now, next section contains some definitions. A subset K of M is said to be convex if for any 2 points x, y belongs to K, the geodesic joining x and y is contained in K. That is, gamma from interval A to B to M is geodesic such that the image of A is x and the image of B is y under gamma. Then the image of A plus T, B minus A also belongs to the subset K of M for all T belongs to 0, 1. Now, what is a convex function? A real valued function f from K to R is said to be convex function if for any geodesic gamma on M, the composition function f defined by this f composition gamma from R to R is convex, given by 1. Now, the strongly convex function, a function f on the convex set K is said to be strongly convex if there exists a constant eta positive such that the expression 2 holds for all xy belongs to K and T from 0 to 1. What is higher order strongly convex function? The higher order strongly convex function is said to be for eta greater than 0 such that the expression third holds for all xy belongs to K and T belongs to 0, 1, where this P is greater than 1. Monotone operator with respect to the Hilbert manifold is defined as T from M to Tm is said to be monotone if and only if the inner product of Tx minus Ty and the exponential map is positive for all xy belongs to M. This is our main result. Higher order strongly variational inequality. For an operator T, considered a problem x belongs to K for an constant alpha greater than 0 such that the equation 5 given by for all y belongs to K and P greater than 1, which is called the higher order strongly variational inequality. Now the next one, some particular cases of the problem 5 arises. If alpha is 0, that is alpha is 0, this one, then the 5 is equivalent to the same as Stampacchia variational inequality. The inner product Tx and exponential map is greater than 0 for all y belongs to K. Now, if P is equal to 1, this P is equal to 1, then the problem 5 reduces to the problem of finding y belongs to K such that the inner product this and the norm of this greater than 0, the summand is greater than 0, which is called an approximate variational inequality. The third case is for P equal to 2, then the problem 5 reduces to the problem of finding y belongs to K such that these expressions hold, which is called the higher order variational inequality. This lemma is work for as a tool in our proof, and this is the proof of this lemma. I skip the proof because I know the lack of time. The variational inequality 6 is this variational inequality 6 is also known as the dual of the inequality 5, the main result. Now, what is the auxiliary higher order strongly variational inequality? For a given x belongs to K satisfying 5, consider the problem z belongs to K such that the expression 7 holds. This problem is known as auxiliary higher order strongly variational inequality. This is the algorithm to solve our problem. This is the next algorithm. We need the definition of pseudo monotone operator because we replace T monotone operator by pseudo monotone operator. The operator T is said to be pseudo monotone with respect to this if these two conditions hold. Now this is the theorem. Let x belongs to K be the solution of 5 and xn plus 1 be the approximate solution of algorithm 1. If T is a, now we use T is a pseudo monotone operator with respect to this, then this expression hold. This is the proof of the theorem. The next theorem is the converging theorem. Let the operator T be the pseudo monotone if xn plus 1 is the approximate solution obtained from algorithm 1 and x belongs to K is the exact solution of 5, then limit n tends to infinity x1 equals to x. This is the proof of the theorem. Now we suggest the two-step method also for solving such problems. The conclusion, in this paper we have characterized the class of variation inequalities. The result motivated to introduce and study a new class of higher order strongly variation inequalities. Using the auxiliary principles technique, some implicit iterative methods are suggested for finding the approximate solution. Using the pseudo monotonicity of the operator, convergence criteria is discussed. It is an interesting problem to explore the application of higher order strongly variation inequalities in various branches of pure and applied sciences. These are the references. Thanks to all for your attention.
Thank you, Mr. Rafat.
Thank you, sir.
For a nice presentation. So is there any question from the audience? Actually, Mr. Rafat, you have taken the operators like the monotone operators and with the exponential operator, right? Hello? Hello, Mr. Rafat? Hello? Hello, Mr. Rafat? Hello? Mr. Rafat? Do you hear me? Hello, Mr. Rafat?
Sir, I think he left the meeting actually.
Okay. Okay. So can I call the next one?
Sure, sir.
Okay. Okay. The next speaker, Bandana Tiwari.
Yes, sir.
Okay. Okay. Ma'am, please start your
Sir, namaste.
Yes, Mr. Rafat. Hello, sorry. Hello. So I am interrupting Ms. Tiwari. Hello, Mr. Rafat. Are you here? Okay. So, ma'am, start. Bandana Tiwari.
Yes, sir. I am sharing screen.
Okay.
Megha, are you hearing? Megha?
Yes, ma'am.
I am unable to share actually.
Okay, sure, ma'am. I'll share your screen.
Okay.
Okay, ma'am.
Okay, share.
Thank you.
Okay. So good evening to all of you. Myself, Dr. Bandana Tiwari, Assistant Professor, Department of Mathematics, GSPG College, Samutpur, Jaunpur. Today I am going to present my paper on Higgs contraction using a control function. Megha, next slide. My presentation is divided into 4 parts. First part is introduction and mathematical preliminaries. Second part contains main results, and third part is conclusion, and fourth reference. Next slide. Next, Megha. Okay. The structure of now I am going to give introduction. The structure of Menger spaces are inherently flexible, and there have been extension of several results obtained on metric spaces. Particularly, Higgs has given an extension of Banach contraction, which is very different from the mapping given by Sahagal contraction. This contraction given by Higgs is known as Higgs contraction or C contraction. Next slide. New domain of study in probabilistic fixed point. Megha, next slide. A new domain of study in probabilistic fixed point theory initiated after the introduction of control functions by Chaudhary et al. This parallels a corresponding development in metric spaces initiated by Khan et al. And elaborated through several works given by other authors. One type of control function, other type of control functions have been used by several authors like Sirik, Jachimsky, and Fang, etc. In our paper, we obtain a generalization of probabilistic contraction mapping principle by using, next slide, Megha. Next slide. In our paper, we obtain a generalization of probabilistic contraction mapping principle by using a control function introduced by Fang. Specifically, we introduced a generalized phi C contraction and proved corresponding fixed point result in Menger spaces. Method of the proof is different from existing one. Next slide. Just preliminaries. Okay. Now I am giving some preliminaries, definitions and concepts which are needed in further discussion. Distance distribution function. It is a map F from R to close interval 0, 1, which is left continuous, non-decreasing with infimum over X in R is 0 and F0 equal to 0. Next. Menger distance distribution function is a, if in addition it will satisfy the supremum over T equal to 1. Let D plus denote the set of all such functions, and D plus, if D plus is partially ordered with usual pointwise ordering of function, then the maximal element of D plus is given by St equal to 1 when T is greater than 0 and 0 at T equal to 0. Next slide. T norm. Next. Megha, next. Okay. Now I am giving the definition of T norm. It is a binary operation on closed interval 0, 1, which is associative, commutative, and has a unity and is non-decreasing in both the argument. Example of such type of T norms is minimum T norm and product T norm. Now Menger spaces. A triplet except delta is a Menger space where F is a mapping from X cross X to D plus, which satisfy F at 0 equal to 0 for each xy in X and F xy T equal to 1 if and only if xy equal to Y. It is symmetric with respect to xy, and fxy T plus S greater or equal to delta fxz T fzy S. Next. Now I am giving the sequence and Cauchy sequence and convergence concept in probabilistic metric space. A sequence xn is in this space converges to X in X if limit n tending to infinity f x n x T equal to 1 for each T greater than 0. Next, the sequence xn in this space is said to be Cauchy sequence if for any epsilon greater than 0 and lambda strictly greater than 0 and less or equal to 1. There exists a positive integer n depending on epsilon lambda such that fx and xm epsilon greater than 1 minus lambda. Menger space is complete if each Cauchy sequence converges in this space. Next. In 2015, J.X. Fang introduced a new class of control function defined by phi from R plus to R plus such that for each T greater than 0, there exists R greater or equal to T such that limit n tending to infinity phi and R equal to 0. An example of this type of high function is given as below. Next. We define the following L convergence criteria. It is we define the L convergence in Menger space. The sequence xn and a positive real number sequence Tn satisfying fxn xn minus 1 over Tn is converges to 1 as n tending to infinity gives that the sequence xn is convergent. Then we say that this Menger space satisfies the L convergence criteria. Now we give a lemma. Next. Megha, next. Megha, next slide, please. Lemma. There exists, this lemma is given by Fang. There exists R greater or equal to T such that phi R is less than T for each T greater than 0 and phi in class of the Fang functions. Now the main result. Let L convergence criteria satisfies in Menger space except delta with a continuous T norm delta. If T is a map from X to X, if it satisfies the probabilistic phi C contraction, that is fxyt greater than 1 minus t imply ftx ty phi t greater than 1 minus k t for is t greater than 0 and xy in x, then t has a unique fixed point in x. Next this is proof. I'm skipping this. Next this is proof. Skip these slides. Thus corollary. Now this is corollary of our main result. Suppose except delta be a Menger space with continuous T norm delta satisfying L convergence criteria, and let T self map on X such that fxy are greater than 1 minus delta imply ftx ty k are greater than 1 minus k lambda, where r is greater than 0 and lambda in open interval 0 1. Then the mapping T has a unique fixed point. Next, the conclusion slide. The flexibility of defining probabilistic metric space, it is possible to suitably orient the definition to fulfill the specific purposes. Recently, one such application can be found in reference number 9, where nuclear fusion related problem is considered. Also, the different choices of T norm radically alter the characteristic of the space, this space. It may be seen in future work how our result presented here is varied with different choices of T norms. Now, the reference of our work. Next slide, Megha. Okay, sir, this completes my presentation.
Thank you, Madam Tewari.
Yes,
Is there
sir.
any questions from the audience? So, Madam, I have a questions, right? So,
Yes,
it has been done in the probabilistic metric space, right?
Yes, sir.
Okay, so this is just has been shown just in parallel way what we have seen in metric spaces by Banach contraction principle, right?
Yes, sir. Yes, sir.
Okay, so if such in probabilistic metric space of such contraction mapping for a mapping T holds, the result
Yes, sir.
for
Yes, sir. Yes, sir.
does the result hold for the any iteration for any positive integer n t to the power n? Does it hold here?
Sir, in last, at the last, I am not getting you. Actually, please repeat it. Last question.
Actually, if T is a contraction mapping in such
Yes, sir.
probabilistic
Yes, sir.
mapping,
Yes, sir.
and
Yes, sir.
so T to the power n is a contraction mapping.
Yes, sir.
So does the converse hold?
No, sir.
Do you have any example?
Actually, this time I am not.
Actually, I think so that the yes, I think that the converse is not true, right?
Yes, sir. But I know it. But this time I am forgetting example, particular
Okay, so these
example.
conditions are sufficient, right?
Yes, sir. Yes, sir.
So does the condition necessary? If not so, you should have to cite an example, right?
Yes, sir.
I think so that in this probabilistic metric space, if I do not assume that the completeness property, right?
Yes,
so
sir.
if suppose is such T is continuous, then the and all other contraction condition holds, then T has always a unique fixed points.
Yes, sir.
So have you studied here?
Yes, sir. I studied it.
You studied it. So have you got the result in published form?
No, sir.
Okay, thank you.
Okay, sir. Thank you, sir.
So is there any questions? Okay. So thank you, Madam Tewari. So next and final speaker is Obhik Digar.
Yes, sir. Is it audible?
Yes, you're audible.
Yes, sir.
So please start your presentation. So actually we are so late. So you are the last speaker. So you have to finish by 8 o'clock. So I'm requesting you. Okay.
Yeah, I'll try, sir.
Okay.
Yeah, so I'm sharing my screen. Shall I start?
Yes, yes, yes.
Yeah, thank you, IIT BHU, for giving me this opportunity to present here. I am Movik Digar, a research scholar in the Department of Mathematics. Today, the title of my talk is on proximal uniform normal structure. So this is a brief outline of my talk, the notations, introduction, some well-known fixed point theorems, followed by some best proximity theorems, and then we will discuss on proximal uniform normal structure. So this is the notations that we'll assume that X is a non-linear space unless otherwise specified. A and B are two non-empty bounded subsets of X. And let U be a fixed but arbitrary point in X, and a gamma is a positive real number. A naught is collection of all elements X in A such that norm of X minus Y equals to distance between the sets A and B for some Y in B. Similarly, B naught can be defined. And delta UA is the maximum distance from U to the set A. RA is called the Chebyshev radius of the set A. It is the infimum of all such delta UA such that U belongs to the set A. RAB is the Chebyshev radius, relative Chebyshev radius with respect to the set A. It is infimum of set of all delta XB such that X is in A. Similarly, RBA can be defined, and if we take maximum of these two, we will get capital RAB. It is called relatively Chebyshev radius for A and B. Delta A is the diameter of the set A, and delta AB is the maximum distance between the sets A and B. First, we can see an interesting result that if we take a continuous mapping F on the compact interval 0, 1, we say that this that graph of this function will touch the line y equals to x. So at this point, we see that x is equals to fx. So the points for which x equals to fx are called fixed points. So here we are giving a few examples. First example shows that every point is a fixed point in R. Second example saying that only x equals to 1 is the only fixed point. And third example is showing that none of the element is a fixed point. So as we have started with some continuous functions, we are here we see some special kind of continuous function that is called Lipschitz mappings. Let X is a metric space and T is a self map on X, and T is Lipschitz mapping if distance between Tx and Ty will be less than or equals to some alpha times distance between xy, alpha positive. Now, if alpha is strictly less than 1, we call this is a contraction mapping. Banach contraction principle is saying that if we take the metric space X is complete and T is a contraction mapping, then it has a unique fixed point. Moreover, that unique fixed point can be achieved by successive Picard iterations. Now, alpha is equals to 1, the mapping is called non-expansive mapping. So natural question is what will be fixed point for the non-expansive mappings. So directly we may not get that fixed points, but we need some geometrical concept that is called uniform convexity and a normal structure. So to define uniform convexity, we'll try first we look at what is strictly convexity. Let X be a nonlinear space. Strictly convexity means, so if we take its closed unit ball, and if we take any different 2 points X and Y on the unit sphere, and if we join these two by a line, that interior of this line should be totally contained inside in the ball itself. So then the space is called strictly convex space. Uniformly convex space is, now question is how much this midpoint will be inside that ball. That is measured by modulus of convexity. So it's a function from the compact interval 0, 2 to 0, 1. This is defined by this. So the space is called uniformly convex if delta epsilon is bigger than 0 for epsilon bigger than 0. Another geometric structure that is called normal structure. Let us take D is a bounded and convex subset in a Banach space. And if S is any bounded closed convex subset in D that has at least 2 elements, then there exists a point X in S such that maximum distance from X to S will be strictly less than delta S. So this is a geometrical representation of normal structure. So naturally, uniform normal structure will come into picture. So it is, if we take the supremum of the ratio that Chebyshev radius of S by and the diameter of S, where S is closed bounded convex subset of the set D, which S with S contains at least 2 elements. Then if the supremum is strictly less than 1, then we call the spaces that set D has uniform normal structure. Now using the normal structure and strict convexity and normal structure and uniform convexity, Browder, Gode and Kim 1965, they have proved that fixed point result for non-expansive mapping. Browder proved that if we take a Hilbert space and K is a closed bounded convex subset and T is a self map which is non-expansive, then T has a fixed point. Browder and Gode proved that, well, we may take even uniformly convex space, Banach space also. The result will be same. Kirk proved that if K is a bounded closed convex subset of a Banach space that has normal structure and T is a non-expansive mapping on set K. Further, if we assume that X is a reflexive Banach space, then T has a fixed point. So till now we have discussed on the Lipschitz constant K is equals to 1. Now what will happen? The fixed point result for K bigger than 1. So Goebel and Kirk in 1973, they have defined a new class of mappings that is called uniformly K-Lipschitz mapping. So this is defined by norm of Tnx minus Tny is less than or equals to K times norm of x minus y for x for all xy in K, and K is bigger than 1. So they proved that if we are having that a K is a closed bounded convex subset in a uniformly convex Banach space and T is uniformly K-Lipschitz mapping on K, further assuming the constant K and the modulus of convexity delta, if they are related by this relation, then T has a fixed point. So now natural question is what will happen if T is not a self map? So well, we may not expect a fixed point, but we can give it a best approximation. In 1965, Kiffen proved that if K is a compact convex subset of a norm space and T is a map from K to set X, which is a continuous mapping, then there exists a best approximation. So X is a best approximation if X satisfies this. So this is a geometrical representation of Kiffen's theorem. So Biramani et al. In around 2000, so they have defined a new class of mappings that is called cyclic mappings. So they have, instead of taking one set, they have taken two sets. Let us take a T is a mapping on the union of A and B that maps A to B and B to A. Those mappings are called cyclic mappings, and a pair XY in AB is called a best proximity pair if distance between X and TX will be equals to distance between A and B equals to distance between Y and TY. So for this mapping, they have proved some best proximity results. So for that, let us recall the definition of proximal pairs. A pair AB in a Banach space is proximal if given a point X in here, Y in here, there exists a point U in here, V in here, such that distance between XU and YV will be distance between the set C and V. Proximal normal structure is a two-set extension of normal structure. A pair K1, K2 in a Banach space is said to have proximal normal structure if given any pair H1 and H2 which is closed bounded and convex proximal pair, such that distance between H1 and H2 will be distance between the set K1 and K2, and maximum distance between H1 and H2 should be strictly bigger than distance between the set H1 and H2. Then there exists a...
Sorry for the interruption.
Yeah.
Som sir. Hello.
Hello, Mr. Digar.
Let him finish another 3-4 minutes. Then we will start the next.
Som sir. Maybe they are calling you in session B. Okay, sir. Okay.
Yeah, I am there in session B also.
They are calling you, I think. And your mic is mute actually.
Okay. So Mr. Digar, please try to finish.
Okay, so this is a proximal normal structure, and they have defined relatively non-expansive mapping. This is again a cyclic mapping for non-expansive mappings. So it is also defined naturally, and Kirk, Eldred, and B. Biramani, they have proved best proximity results for this. So we have defined proximal normal structure. This is a two-set extension of uniform normal structure. This is proximal uniform normal structure. Okay, I'll look at its definition. So the mapping, if T is a cyclic mapping on the union of A and B, so this is a cyclic uniform Lipschitz mappings if T satisfies this. Now for this mapping, if A and B are two closed convex bounded subsets in a uniformly convex Banach space, and T is a cyclic uniform Lipschitz mapping on the union of A and B, and the modulus of convexity and K are related by this relation. Further, if T satisfies this condition, then T has a best proximity pair. So if for a pair AB, if gamma AB is the collection of all closed bounded convex proximal pair H1 and H2, with at least H1 on H2 should have more than 1 point, and distance between the sets A and B will be distance between H1 and H2. Then we define the coefficient for proximal uniform normal structure is supremum of capital R H1H2 by delta H1H2, where H1H2 belongs to that collection. So if this is less than 1, then we call the pair has proximal uniform normal structure. Now we are giving some example, and with this, it is clear that proximal uniform normal structure implies proximal normal structure, and we are giving some example that converge is not true for a strictly convex space. Using this lemma, we are proving that if AB is a weakly compact convex pair in a Banach space that has proximal uniform normal structure, and T is a cyclic uniform Lipschitz mapping with Lipschitz constant K is bigger than 1 and less than this, then T has a best proximity pair. So this was the proof, and at the end we are asking some question that in a uniformly convex Banach space, what will be a maximum value for K? That is an open problem. The condition we have taken, whether we don't know this condition is actually necessary or not, and this is a conjecture that based on our example that we have given, that every closed to bounded convex pair in a uniformly convex Banach space will be having proximal uniform normal structure or not. So this is the references. Thank you.
Thank you, Mr. Digar, for your nice presentation. Is there any question from the audience? Mr.
We will
Digar,
not take any question now.
Hello?
Yes.
Maybe one question only.
Yes. Is there any question? Digar, I have some little question. So you have considered the mapping, or there is a base proximity theorem like that. There is a contraction type. So could we extend the result of the Cannon type mapping? So there is norm of Tx minus Ty less or equals to beta sine Tx, and regarding the proximal normal structure, can we adopt it?
Yeah, okay. I have not done it because proximal uniform normal structure just we have defined now. So lot more things to do. So right now we do not have any more results.
So one question is the problem is solved that the every closed bounded convex subset in a uniform has a normal structure.
Yeah.
Right. Already improved by the result of the Smulian theorem, right?
Yes.
So that problem is not yet solved. There is the proximal normal structure hasn't solved yet.
No, but whether it has a proximal uniform normal structure or not, that we don't know.
Okay. Thank you.
Uniformity we don't know.
Okay, thank you.
Yeah,
thank you. So since there is no participant, so the session is closed on behalf of my chairing the session. Okay, thank you.
So let me thank Montu Shaha for nicely chairing the session on the paper presentation on fixed point theory. Now we are coming to the last session today. That is a plenary talk by Professor B.S. Chaudhary, to be chaired by Professor G.B.R. Babu. Please, G.B.R. Babu. He is here. Please unmute, Professor Babu.
Thank you very much, Professor So. Yeah. I welcome Professor Binayak S. Chaudhary. I'm very happy to chair this session. I know him pretty well. And Dr. Binayak Chaudhary is a professor of mathematics at IIST, Shibpur, West Bengal, India. He has more than 3 decades of teaching experience, of which more than 18 years he is in the post of professor. He has published more than 300 research articles in different areas of pure and applied mathematics. He is doing research in fixed point theory also in several directions, and in Menger spaces he also doing in finding proximal points and finding fixed points. Very interesting results he is doing, and I read most of his papers. I follow, and in theoretical physics also he is working, particularly in functional analysis. He has published more than 100 research papers. Till now, 22 students have obtained their PhD degrees under his guidance. Professor Chaudhary has delivered lectures widely across the world. He has served several academic bodies, committees, and countries in India and abroad. I welcome Professor Binayak Chaudhary to deliver his plenary talk.
Thank you, Professor Babu. Namaskar.
Namaste, Professor Chaudhary.
Very happy.
I am also. So definitely, let me go to the talk. Is it visible?
Yes, yes.
Yes. So good afternoon, everybody. Let me begin by extending my heartiest thanks to the organizers, especially to Professor Shom for his kind invitation. So the title of the talk is Cyclic Constructions and Their Applications to Optimization and Fractals. So we have already been familiar with the cyclic constructions through this of section A. As you can see that this is quite an extensive topic which I have chosen. And so I will be able to do justice only by making brief, I should say, some brief indications of the developments in these areas, and especially for the new researchers who are present here in quite a good number. I expect and I hope and trust that this domain will be interesting and maybe useful for their research work in future. So let me go to the technical content. Yes. When we are speaking of contractions, then what first comes to our mind is the Banach's contraction mapping principle. It is a classical result, and it is proved in the most general structure of metric spaces. If Xt is a metric space and this particular inequality is known as contraction inequality, with necessarily k between 0 and 1 excluded. If we include 1, then this mapping becomes non-expansive, and any person having some experience of research in fixed point theory knows how difficult it is to obtain fixed points of such mappings. So for a contraction mapping with 0 less than k less than 1, we have a very elegant result due to Banach. It has a unique fixed point. That is a point with Tz is equal to Z. And there are several generalizations and extensions of this particular principle. And equally, there are several applications. In fact, it will not be an exaggeration to say that this is a result of mathematics which has exerted most, that is, I should say, which has exerted maximum influence in shaping the future of science and technology. Not only being confined in mathematics, it has its implications elsewhere and everywhere in physical science. So anyway, why I am telling all these words is that we will go for how the particular principle gets generalized in the case of cyclic contractions, and this idea of contraction, how they can be put to use in different branches. Only two applications I will mention, but the applications of cyclic contractions are really not confined only to these two domains. And one thing, our discussion will be in the most general framework of metric spaces. Although, for the purpose of bringing out results, both in fixed point theory, is like proximity point, or in other areas where applications are made, we often have to switch over for a discussion in to the framework of more specialized structures like Banach spaces, Hilbert spaces. Often we do that, and especially the Banach space geometry has developed a lot for the purpose of fixed point theory, and fixed point theory was proved in the context of Banach spaces using different types of geometrical concepts of Banach spaces or like that. This is a very vast range of study. We will not concentrate on that. We will just come up with results which are valid in metric spaces without any structure whatsoever, and no specialized metric space I will mention. And so, as you can see, the discussion becomes very restrictive and at the same time very general from 2 points of views. We come next. I think I'm having some difficulty with the movement of slides. I think just give me 1 minute to arrange it. I think it is the next slide. Hello, is this slide visible?
Yes, yes.
Yes. Then what is a cyclic map? A cyclic map is a map from A union B to A union B. The speciality is that T maps A to B, and B is mapped by T to A. It can be generalized. The generalized concept is P cyclic map. So it is like this one, union 1 to PAI goes to union 1 to PAI is called a P cyclic map, when under T, A1 is mapped to A2 and A2 is mapped to A3, and finally AP is mapped to AP plus 1. We equate AP plus 1 with A1. If we want to see it pictorially for the special case of P is equal to 4, then the diagram is like this one. That is, A1 is going to A2, A2 to A3, A3 to A4, and A4 back to A1. In this way, this is cyclic. Now, we can see that this is not a self-map. It is. It can be visualized from here that without any special conditions, we should not expect much out of these maps as regards fixed point results, because until and unless all these 4 sets are having a non-null intersection, there is no question of fixed point of that mapping. And secondly, that too will be definitely under very stringent conditions. But we will see that some cyclic contraction conditions will ensure the fixed point, and in the sequel, it will ensure that such sets on which the cyclic contraction condition is defined should have a non-null intersection. Because without being non-null, and it has an interesting implication, that without having a non-null intersection, such cyclic contractions cannot be defined in this way. This is also an interesting implication of the fixed point result of the cyclic contraction. Now, before going into the details, we should show that what a cyclic contraction is. Yes, we are just illustrating, and we will be illustrating throughout the present with the Meyer-Killer type of contraction. As we know that Meyer-Killer is a generalization of Banach's result. Whatever is true with Meyer-Killer contraction will be true for Banach's contraction. And so it's quite a general one. And so let us consider a p-cyclic map in the sense we have discussed it previously. So, and the point is that it is a contraction. If we take x from AI and y from AI plus 1, two consecutive sets, just like this one, we can take that is x from A2 and y from A3, which will satisfy the contraction inequality, that is in the Meyer-Killer sense, that is given C greater than 0, there exists delta greater than 0, for which this inequality will imply this inequality. Surely, as is well known, that it includes the Banach contraction in its I should say in its definition or in its content. So whatever is true in this theorem, it is true with Banach contraction as well, and also with some other results, which I'm not going to discuss because this result happens to be a generalization of some very important results of fixed point theory. Although it was given in 1960s. But when we are trying with the cyclic contractions, I think it was given in 2009. Yes, 2009. It is a complete metric space. Then T will be from x to x is such that these conditions hold, then T has a unique fixed point inside in X. This is the Meyer-Killer condition. Now, our theorem is an extension, not really our theorem, the theorem we are going to discuss, that is Karpagham's theorem in 2009. It tells us that T from union I from 1 to n AI goes to union I from 1 to p. AI is a p-cyclic map and satisfies that in cyclic contraction inequality, Meyer-Killer type of contraction inequality. Then their intersection is non-empty. And this particular sequence with p fixed, here p is fixed, you can see, and n varying will converge to the unique fixed point of T. So existence of that cyclic contraction will imply that this is non-empty. If you look it back from the opposite side, then without getting it non-empty, you cannot have such a mapping defined on it. Incidentally, this has some implications in the existence of differential equations, which we are not going to discuss. But the point is that the proof is quite interesting. And finally, simple but interesting, finally we could see that this is a Cauchy sequence and it converges to Z. You can see how the sequence is constructed, because I am stressing the construction, but because in several applications this construction is important. When we go into the study of certain applications of the Banach fixed point theorem, then we need not worry about the construction of the iteration, because wherever you start, you end up at a fixed point. Here it is not. You will have to have a very special type of Cauchy sequence. It will remind us of the large, literature of Ban, Ishikawa iteration, starting with these and now getting expanded to many other iterations, where the algorithm leading to the particular fixed point is studied, and its importance is recognized both in theory and applications. Anyway, so this is one result. But let me stress that this is not the only result with cyclic fixed points of cyclic constructions. There are many other fixed point theorems using cyclic constructions of different types of construction inequalities. But interestingly, if we are trying, because there are many construction inequalities which in the case of a map, which is a self map from a metric space to itself, will give you a fixed point. It will not be the case with the cyclic mappings. So cyclic mappings, for the purpose of fixed points, or for the purpose of studying fixed point results, the cyclic mappings are quite choosy. This is an interesting thing with constructions, and if properly studied, we can hope that it can give a classification of the constructions. So, but we have promised to go to application areas. Now we will look into the applications of best proximity point and the fractals. Best proximity points is now a well-known and well-studied area of mathematics. And sometimes in literatures, especially in books written on fixed points, the best proximity points are automatically included either as a chapter or as an appendix or like that. What a best proximity point is? It is like this one, that we are essentially interested in determining the distance between the sets A and B. What is the distance? This is the minimum distance between two points collected, one from A and collected the other from B. Okay, so this is DAB by geometry or by visualization through Venn diagram. We can have some idea of that. Now, a best proximity point is an approach to finding this minimum distance. So that is, we construct a mapping T from A to B. This is a non-self mapping. And in the whole process, we have, if we can find a point set which is such that dz is equal to DAB, that is a point where the minimum distance is realized by this function in some sense. That is, we are taking z here and we cross over to the point tz here. This distance is the same as the distance of the bridge DAB. If it so happens, then we call it a proximity point of the T, of the function T, and it serves the purpose of determining the distance between the two functions. But one thing is important here for pointing out, that is, this determining this distance is essentially a global optimization problem, as you can see from here. We want to just determine this one. So it's essentially a global optimization problem, and many papers which are published on this particular topic are published in optimization journals. Now, best proximity point being optimization, what actually we are doing. Just looking at this equation, we can see that it will not have a solution. Why? Because in the non-trivial case, that is in points of case where interest is, I should say that when A and B are really non-intersecting, then only the problem is non-trivial. Otherwise, if they are intersecting, then DAB is definitely trivial, equal to 0. We are not really interested in those problems. If it is a non-trivial problem of that type. And now look at it. It will not have any solution. But what we are wanting to find here is that we are wanting to see an optimal approximate solution. Z, as you can see, the DAB is the minimum of the value of dz, dz. If this minimum is attained at a point, that is, we are wanting to find an approximate solution of it, and the approximate solution is an optimal approximate solution, then we have a fixed point, we have a proximity point. And so it's an extension of the fixed point. As you can see, it is, if it is overlapping, otherwise also fixed point methods are applicable. One point of caution is here, which was really initially confusing, is that its statement with the statement of Kaifon's best approximation theorem. It's a very famous theorem, and in compact, I should proceed a little faster. Yes. In the context of compact and convex sets and a non-linear space, actually the more general studies in topological vector spaces, anyway, the statement is like this one. But this Kaifon's theorem is not an optimality result, but best proximity point theorems are optimality results. Now, what is the scope of the cyclic contraction? This is a very famous paper, Veeramani. Professor Veeramani is one of the writers of this paper. It is that if for these two sets we have already indicated, these are the two sets. T is a mapping from A to B. And if we assume, if they are cyclic contractions, and if we assume that dtxty is less than equal to k into dxy, there is another part, plus 1 minus k into distance. That is what we have defined as d of AB. For all x belonging to A and y belonging to B, then it is called a cyclic contraction mapping. We have a final theorem like this one, that yes, these are non-empty subsets of a metric space, and this T is a cyclic contraction mapping. Then these sequences are bounded, and finally, I see, perhaps this is written a little earlier. So under these conditions, there exists x belonging to A such that dxtx is equal to dAB. So the sequences are bounded and etc. These are certain conditions which are to be taken in metric spaces, because we don't have other structures. But if we put some more structure on the metric space, like normal structure or like that, or do it in Banach or Hilbert spaces, or at least in some other new structures, hyperconvexity or like that, we impose on this space, then many of the assumptions which are necessary in this study for a study of these things, of these problems in a metric space without a structure, are automatically derivable. But here in metric space with no other structure, you are blessed with no other option but to assume something which is automatically true in some other more complicated spaces, complicated in this sense, having some more structures. So this is the scope, and as you can imagine, actually, a little bit of that type of thing, as you can see that if T is going from here to here, back here, and then iterating this way to here and that way to here, it is quite imperative that we should have some mathematical results. Actually, with this idea in brain, if we approach and if we at the same time, we must recognize that it is not a necessary thing to obtain the proximity point results by consideration of the cyclic mappings from going from here to here and here to here. No, not necessary. There are different conditions like P property or some other properties which can be successfully used to guarantee that there are such proximity points for mappings from one set to other. But these are not our considerations. Our consideration here is the cyclic contractions. So this is these are some glimpses of the development of the use of cyclic contractions in proximity points. We will come quickly, because time is quickly passing away, we will come to the consideration of fractals, how these are obtained. Yes, for that purpose, as we did previously, we have the concept of distance. We addressed the concept of one distance, but here you can see that we have a very separate type of concept of distance. What is it? The Hausdorff distance. This is a very famous type of distance. Let me give some explanations because I see that there are young researchers. So this is like this one, that there are two sets you can see. You take a point A from A to B. So take infimum of that. Sure. And then you take the supremum of the infimum. It will be this distance. You denote it by DAB, and you make the same treatment to obtain DBA, which will be the maximum distance, this one. And HAB is again maximum of DAB and DBA. Pictorially, you can see that if A is juxtaposed on B, or B is juxtaposed on A, that is A equal to B, then these two distances will vanish, giving you HAB is equal to 0. And the other properties of HR are derived, and these properties make H into a metric, but on which set? The set of compact subsets of K, maybe closed and bounded subsets, but we will be interested in only compact subsets of K. And as you can see that in 2 dimensions on which we have a diagram here, these are compact subsets. So essentially, when we are taking a matrix space and we are considering compact subsets of that matrix space, we have a metric H generated from the metric D on the set of all compact subsets. That is, finally, we have a KH, KX and H. H, everything is, as you can see, that XD is the mother metric space from which this is derived from. And if an interesting and very important theorem is that if XT is a complete metric space, then KXH is also a complete metric space. This is one, if it is a complete matrix space, then definitely convergence and Cauchy sequence converging to a particular set under this house dot metric. And here you can see, if you have some idea of fractal, then you can see that it is in the process of the along that sequence generates a fractal like this. And now what is a fractal? We are familiar with these pictures, and sometimes even non-mathematicians, they have the general idea that these are fractals. Why they are fractals? Because there is a self-similarity of the structure. What is a self-similarity? And if you have a, just have a curve, and if you want to see the curvature of the curve, that curvature is not uniform everywhere, then you can magnify it, see it with some magnification and see that, yes, here the curvature is more, here the curvature is less. But in a self-similar structure, you cannot have like that. By magnification, you don't have something very new. You have the repetition of the same structure. You can, the oft-quoted and very simple construction is the Cantor set. Even in your undergraduates, you are familiar with the Cantor sets, and you can see that anywhere and everywhere on the Cantor set, you have the same structure. Now, the fractal was introduced by Mandelbrot in 1975. And what is a fractal? This is, as I'm not going into very detailed study of or definition of fractal, because this definition varies from one discussion to another discussion whenever you vary your framework of and background, mathematical background of discussion. But one thing is invariant. This is a self-similar structure. What do you mean by self-similarity? I will come. This is that it is imaged within itself with the same, with the same texture. That is like that. And for our purpose, it is self-similar for the purpose of the study in metric spaces only. And iterated function systems, what is this one? I will come to the technical definition. And this was given by Hutchinson in 1981, a brilliant approach to the study of fractals in metric spaces using contractions. It is like this one. Yes. Suppose XT is a metric space, fine. And Fn is a finite, mind it, it's a finite collection of contractions Fn on a complete metric space XT. It's called an iterated function system, just a finite collection. And then what happens is that this is Hx, this is the set of all compact sets. This is, we have used this notation, sometimes it has become very standard, so I have preferred to use this notation here, abandoning K that was used just in the previous slide. So this is a set of compact sets to the set of compact sets, a function f, which is defined in this way, Fc. C is a compact set, as you can see, union n from 1 to n, f and c. You can see that this is from compact sets to compact sets, because Fn is a contraction, and contraction is a continuous mapping. Compact sets are under continuous, continuous images of compact sets are compact and tend to a finite union. You will fall in difficulty if you just want to sacrifice this point for finite. And that is a point which is a mathematically challenging point, but we can overcome it by some means or other, by some extra conditions and etc., extra concepts even. Anyway, as a little bit of manipulation will convince you that F is a contraction in this space. With the contraction factor, maximum of S1, S2, Sn. These are contraction coefficients of F1, F2, Fn. And then it has a it has a fixed point. What is that fixed point? That fixed point is a point from the set of all compact sets, that is K. K is equal to Fk. Now what is Fk? By definition, Fc is equal to this one, and union n from 1 to n, F and K. Then what happens now? That is, K is a union of its images under Fn. That is the shuffling of K. You can see with the Fn and then taking the union. So this is actually the self. It can be written as finite union or transformed copies of itself. So these are the transformed copies. What is a transformed copy? Take 0, 1 closed interval. Then x by 2 is the mapping, ft is equal to t by 2. Then 0, 1 goes to 0, half. This is actually a transformed copy of that. And in this way, K can be a transformed copy of these. In fact, 0, 1 and 0, half have the same topological structure, being